Aduh, 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 aduh.
Dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina fungsional peneliti nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian, dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung IPTEK di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan IPTEK, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM IPTEK. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia.
Bismillahirrahmanirrahim. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning to all participants. Welcome to the International Seminar on Metallurgy and Materials 2020 held by LIPI. And for today's session, I would like to remind to all the participants to fill in the attendance list for plenary session day 1. And for today, we have a photo session that later on will be taken by the committee. So I would like to remind to all of the participants to activate all your cameras. And before we begin the conference for today, I would like to remind you all of you again to read carefully the presenter guidelines that are already provided by the committee. Excuse me, the already provided by the committee. So you can read all the guidelines thoroughly and make sure that you fill in again the attendance list and before you presenting your topic for the seminar. Okay, so I think we can begin our first session of today by opening with the national anthem of Republic of Indonesia. Thank you. Okay, and next on the list of our today's schedule is the opening speech from the head of the International Seminar on Metallurgy and Materials, Dr. Nono Darsono. Please, Dr. Nono Darsono, to start the speech.
Okay, thank you. Can you hear my voice?
Yes.
Okay. Yes. Yeah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Welcome, ladies and gentlemen, the honorable keynote speakers, respected guests, Deputy of Engineering Science, Dr. Agus Haryono, Director of Research Center for Metallurgy and Materials, Research Center for Physics, and Head of Research Unit for Mineralogy Technology, Indonesian Institute of Science, and all of our other guests. My name is Dr. Nono Darsono. It's a pleasure to welcome you all to the 4th International Seminar on Metallurgy and Materials. 2020. We are grateful to the organizing committee, the members of the organizing committee who have arranged such a beautiful program. I heartily welcome all the keynote speakers, Professor Dr. Hirofumi Tanaka from Kyushu Institute of Technology, Professor Takeshi Kawai, welcome, Professor Byung-Il Hwang from Chong'an University, Dr. Fatwa Firdaus Abdi, Deputy Director of Institute Solar Fuel, Helmholtz Zentrum, Berlin, Germany, Professor Dr. Insinyur Anne Zulfia Syahrial, Master of Science from Department of Metallurgy and Material Engineering, University of Indonesia, welcome. Professor Dr. Ing Andika Widya Pramono from Research Center for Metallurgy and Materials, Indonesian Institute of Science, welcome. And Dr. Insinyur Bambang Pihandoko, Magister of Engineering from Research Center for Physics, Indonesian Institute of Science, welcome. We are also fortunate enough to get supported by Indonesian Institute of Science and also from our quad management, and thank our media partners. In this opportunity, I would like to report the fourth International Seminar on Metallurgy and Materials, which will be held on November 2 days from 19th to 2020 is the fourth Scientific International Seminar organized by the Research Center for Metallurgy and Material, Research Center for Physics, and Research Unit for Mineralogy Technology. Due to the impact of the COVID-19 and to minimize the spread of the coronavirus, the organizing committee are committed to delivering virtually the symposium to the widest possible audience through online event. The symposium is part of Indonesian Science Expo, aimed to bring together researchers, academicians, and industry all around the world to share information and their research results. This event will also become a beneficial media to exchange their innovative ideas. I will report that total full paper submission around 70 paper, 63 paper accepted, 6 paper is rejected, and 1 paper withdrawn. The accepted paper will be considered for publication in IOP conference series indexed by Scopus. It will be researcher around 53 participants, students 7 participants, and academia from the 3 participants. We will also have a participant from other country, from Philippines and other from other country. We have arranged a plenary session for lecture from keynote speaker and oral presentation opportunity for accepted paper to put forward their reforming to in the fast field. I want to inform our speaker, moderators, and participants to be very strict about the schedule and don't let overrun any session. This event will be widely broadcast from Indonesian Science Expo 2020 website. I hope you all find the seminar highly engaging, fruitful, and beneficial for your future venture. Thank you. Thank you all. Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you to Dr. Nono Darsono for that opening speech. And next on the list is also the speech that will be delivered by the chairman of Indonesian Institute of Sciences, Dr. Laksana Trihandoko, Master of Science. Okay, so please, Dr. Laksana Trihandoko, to begin the speech.
Hello, I am Handoko, the chairman of the On behalf of LIPI, I would like to welcome you all at this international conference. We hope this international conference would open an opportunity for all of you, not only to know each other, but also to open future collaborations. Have a nice, fruitful, and productive discussion during this international conference. Stay healthy. Thank you very much.
Okay, thank you, Dr. Laksana Trihandoko. And next one is another speech that will be delivered by Deputy for Engineering Sciences of Indonesian Institute of Sciences, Dr. Agus Haryono, Master of Science. Time is yours, Dr. Agus Haryono.
Welcome, ladies and gentlemen. Thank you to each and every one of you for being here virtually today at this important 4th International Seminar on Metallurgy and Materials 2020. My name is Agus Haryono, Deputy Chairman for Engineering Sciences, Indonesian Institute of Sciences, LIPI. It is such great honor for me to speak on behalf of LIPI. Let me begin by giving you a warm welcome to this virtual conference. Before we get started, I would like to express my appreciation to the Honorable Chief Guests, respected directors, speakers, and all our other guests. We could not have done this conference without your participation. I am also grateful to all organizing committee members and all the volunteers to have arranged this program. I will kind-heartedly welcome all the participants from academia, students, industrial practitioners, and researchers. We are also fortunate enough to get supported by our partners whom also organized this scientific conference. This conference is a part of Indonesian Science Expo 2020 and aims to bring together researchers, academia, and industries to share information and their research results. I do hope this event will also reach its objective of this conference on accelerate research and innovation on metallurgy and advanced material for inclusive and sustainable industry. As you all are aware of the current situation of COVID-19 pandemic, this event should be conducted virtually. The speakers in this program are uniquely placed based on their topics in advanced material and functional material in the field of energy and metallurgy. I hope you will have the most productive 2 days of interesting and stimulating discussion. I hope this conference will success not only as a chance to share knowledge and experiences, but also discover new opportunities to the still growing area of research on the future metallurgy and material technologies, as well as its collaborative inter-institutional research opportunities. I wish you all the fruitful and productive discussion. Last but not least, I would like to sincere thanks to all of you for being able to join this virtual conference. During the pandemic COVID-19, please stay healthy and happy during the long pandemic. Again, thank you very much and enjoy the conference.
And thank you, Dr. Agus, for that opening speech. Ladies and gentlemen, all participants of the International Seminar on Metallurgy and Materials 2020, I would like to remind you to fill in the attendance list provided by the committee for the plenary session day 1. This day 1, we have 3 plenary sessions that already provided in the presenter guidelines that you have probably already read. And before beginning all the sessions, make sure you fill in the attendance list. And another reminder for all participants to activate all your cameras for the next photo session that will be taken around plenary session keynote 3. So make sure you activate all your cameras. And for the schedule on our seminar for today, as written on the guidelines, will be started with plenary session keynote 1, Professor Takeshi Kawai. So, and please prepare for the presenters and all participants. And thank you. I think for today's opening, we will start it shortly on the plenary session. Ladies and gentlemen, all participants, enjoy your seminar. Thank you.
Okay, thank you very much, the MC. So for this morning session, for the day 1 of our conference, I will be the moderator for our plenary session. So this morning we will have 4 great speakers. The speaker number 1 is Professor Takeshi Kawai, and then Professor Andika. The third one is Dr. Bambang Prihandoko, and the last but not least is Dr. Fatwa Firdaus. Okay. Okay, before the speaker begin, I would like to say hello again to all of you. Honorable Deputy of Engineering Science of LIPI, Dr. Agus Haryono, the Director of RCCM LIPI, Professor Nurul Taufikur Rahman, all the guests of ISMM or the representative, the distinguished keynote speakers, and all respected participants. I would like to say welcome to our ISMM 2020 or the 4th ISMM. Okay, before we go to our first keynote speaker, Professor Takeshi Kawai, I would like to read his his biodata. Okay, Professor Takeshi Kawai, his affiliation now is from School of Electrical and Computer Engineering, College of Science and Engineering, Kanazawa University. And Professor Kawai got his doctoral from 2003 from Tohoku University. His professional career starting as the postdoctoral researcher since 2003, and he already joined several postdoctoral researcher from Tohoku, and then joined again to NIMS, National Institute of Material Science, and then continue as the research associate at College of Science and Engineering at Kanazawa University, and then become lecturer since 2009, and now as the associate professor at Kanazawa University. Okay, without further ado, I would like to invite Professor Kawai. Professor Kawai, please, you can share your PPT now.
Thank you, Professor Denny. Now I will share my presentation slide.
Okay, maybe I'm sorry. I would like to say the time is about 40 minutes. Okay.
Yeah. Okay. Thank you. I understand.
Okay, you can share now, Professor Kawai. So we will have the discussion after 2 keynote speaker deliver their speech. Yes, please. Now it's okay. The slide is already in the full mode.
Hey, thank you. Maybe my presentation file is okay.
Hello, Professor Kawai. Is it okay?
Hi. But now, can I start my presentation now?
Yes, yes,
Oh,
you
really?
can share your presentation now. You can start now.
Already?
Yeah.
Yeah, I'm sorry.
Yeah.
I forget my presentation time. Yeah, I'm sorry, dear.
Maybe the time is earlier than our schedule.
Yeah. Okay.
Yes.
Yeah. Thank you, Professor Denny, for my introduction. And also, before my presentation, I would like to greatly thanks for all of the professors of this conference to invite me to that hot international conference. Very thank you. ありがとうございます。And this is today's my presentation title. Yeah, and this is the outline of my presentation. Firstly, I would like to explain the background, introduction, and the background of my research. This research, and I have the two topics. One of them is the fabrication of the ferroelectric gate diamond field effect transistor, and also the possibility of its pseudo-anomaly of operation. Yeah, let's start. Yeah, as you know, the diamond is the king of jewel. Yeah, and also the maybe the you know the diamond is the candidate next generation power semiconductor material due to its high electric breakdown field and high thermal conductivity and high carrier mobility. This table is comparison with those typical property of diamond with those of the other semiconductor material. As you can see, the diamond has a high thermal conductivity value and carrier mobility and breakdown field. So these excellent property is by considering those excellent electrical property, diamond is a promising candidate for next generation of power device application post silicon carbide or gallium nitride. And also about the diamond semiconductor, there are two kinds of the channel structure. One of them is the hydrogen terminated conductive surface conductive layer. So this surface conductive layer has a high hole density p-type semiconductor material, semiconductor working, and its low density of surface state. So it means it is very easy to create the good, smooth the pure semiconductive layer. But however, there's the serious problem. It is really sensitive for high temperature or plasma process. So it means it is really weak for active species. So about this problem, Professor Liu, I'm sorry, Dr. Liu of NIMS, they tried to create deposit, to create a gate structure by depositing the hafnium dioxide using sputtering method. But they conclude that it is really difficult to deposit such gate insulator by using the conventional plasma deposition process. And also they try to solve this problem by using the atomic layer deposition at room temperature deposition method. So they succeed to create the buffer layer of ALD deposit hafnium dioxide on the hydrogen terminated diamond semiconductor layer. So it means we must suppress the process damage for creating the device, semiconductor device structure on hydrogen terminated diamond. And also, this is one of the ultimate demonstration by Dr. Yamaguchi from NIMS. They tried to transfer the hexagonal boron nitride, two-dimensional hexagonal to boron nitride as a gate insulator on the hydrogen terminated diamond. And also they succeed to create the those field effect transistor structure. And also they investigate its carrier mobility. And as you can see, in case of their ultimate structure, they can obtain the highest carrier mobility compared with that of the other created hydrogen terminated field effect transistor. So it means by improving the device process, especially the gate insulator fabrication of the gate insulator process, hydrogen terminated diamond can be probably winner for high frequency or high power field effect transistor application, we believe. So nextly, I would like to explain what is the ferroelectric gate insulator, gate insulator field effect transistor. About the another semiconductor diamond channel, it is the bulk channel, bulk diamond channel. But in that channel, there's serious problem. So it's deep, really deep dopant level. For example, the phosphorus 0.6 electron volt or the 0.37 electron volt. This is really difficult to activate the carriers at room temperature. Yeah. So in order to solve this serious problem, we consider the ferroelectric gate structure might be suitable. Yeah, because this is the one of the demonstration of the ferroelectric gate structure by Professor Tokumitsu of the JAIS. They create the ferroelectric gate structure on the some oxide, conductive oxide channel, and also they try to activate the huge amount of carriers for conductive oxide semiconductor. And they conclude it is possible to modulate the huge amount of the carriers by using the ferroelectric gate insulator. So we consider by using this gate structure, maybe it is possible to activate the huge carriers for the bulk diamond channel at room temperature, we consider. So to investigate this possibility, as a first step, we use the ferroelectric organic ferroelectric material, VDF TRFE, as a gate insulator. So this material is organic ferroelectrics. So, and also to deposit this one, we don't need the high temperature. Around the 100 degrees C is enough. And also this is most important parameter fact. This VDF TRFE material has a large band gap than that of the diamond. So it means that we can use this ferroelectric material as a gate insulator for diamond. And also by using the ferroelectricity, we would like to we hope the high current on-off ratio for diamond channel, and also maybe we can operate the pseudo normally off operation for diamond field effect transistor. So this is our past demonstration. As a first step, we create those simple field effect transistor structure on diamond by using the VDF TRFE gate insulator. And this is the basic electrical property, drain current versus drain voltage property. As you can see there, we succeed to create the field effect transistor with ferroelectric gate insulator on the diamond semiconductor like this. And also especially we succeed to modulate the drain current by using the remnant polarization of ferroelectric VDF TRFE gate. It means that without direct gate biasing, we can modulate its drain current. And also, this is capacitance versus gate voltage property. This typical property indicates in our prepared gate ferroelectric gate structure, there is no interfacial layer. So it means that we succeed to obtain the ideal metal ferroelectric semiconductor structure. Yeah. And also, this is serious problem. Although we can modulate its drain current by using the remnant polarization like this. However, its deflected current level is still 10 to -2 power milliampere per millimeter. We consider this is not really deflected states. And also this is drain current versus DC gate voltage property. As you can see here is really deflected current level, but there without gate biasing, we can not deflect, still deflected its current level. So it means not normally, normally of operation state. Yeah. So in this time, in order to solve this problem, we would like to we have tried to improve this property for our structure. Firstly, we must consider why we cannot obtain the normally of pseudo normally of operation for our device structure. Its answer is really simple. Carrier density of surface conductive layer is still higher than that of the gate remnant polarization value. Yeah, so it means that we cannot modulate the all of carriers of surface conductive layer by using the remnant polarization. Yeah, so it means that should we need should we search the other ferroelectrics with huge remnant polarization value or not? The answer is no, because it is really difficult to find out the other ferroelectrics with large bandgap. This is most important parameter. Yeah. So with considering these current situation, we think that it is really difficult. Maybe it might be impossible to solve this problem. But there are the another approach for normally of operation of the surface conductive diamond layer. Professor Kawarada, the Waseda University, they recently they support the other process approach. It is the partially oxygen terminate structure by using the some nitrogen ion implantation technique. And also the by using these process technology, they obtain the such normally of operation like this. This is the IDS versus gate voltage property. As you can see, they can operate the normally of action by using the ion partially ion implanted device structure. So we consider by using this process technology, maybe we can create the pseudo normally of operation for our ferroelectric gate diamond FET. So in our study, we use the UV ultraviolet lamp irradiation for hydrogen terminate diamond structure. So by irradiating the ultraviolet lamp, we can create the active ozone species, and we can send those species on the hydrogen terminate diamond structure, and also the we can obtain the partially oxygen terminate structure. So by using the this process technology, firstly we check the can we control its carrier density with locally controlling. This is experimental procedure. this is a rough image of our device structure. Firstly, we create the surface hydrogen terminated surface conductive diamond channel like this. And also the for this prepared channel structure, we try to create the thin, narrow, partially oxidation area by using the ultraviolet irradiation. This is the basic experimental result. This data is ultraviolet irradiation time versus current density of the hydrogen terminated structure. As you can see there, by increasing the ultraviolet irradiation time, we can control its current density from 10 to 10 milliampere per millimeter to 10 to minus 8 power milliampere per millimeter order. Yeah, and we conclude its current density can be controlled by changing the ultraviolet irradiation. And also the this is the Kelvin Horse microscope image of our prepared channel structure. As you can see here, we can control its carrier density on the in-plane area. Here is a hydrogen terminate. Here is a completely oxygen terminate. And also this brown area is partially oxygen terminate area. So, and by using this such specialized channel structure, we create the ferroelectric gate FET structure. This is the basic basic electrical property, drain current versus drain voltage property. As you can see here, we can this prepared device can work without the serious degradation, such as the degradation of the current density value. And also the this is the IDS versus gate voltage property. As you can see here, with ultraviolet irradiation, we can shift the its hysteresis property like this. And also the could you see the around here? So it might be possible to operate the normally off operation for our devices. And also the this is the drain current versus gate voltage property for various ultraviolet irradiated device structure. As you can see there, with increasing the ultraviolet irradiation time, its curve, those curves are shifted to negative bias region. And could you see there this accumulate region by irradiating the ultraviolet irradiation. Due to the ultraviolet irradiation, there is no serious degradation of the accumulated current density, as you can see here. And also the now here now we roughly decide this lower current level is roughly deflected state for each device structure. And also we roughly decide here is a threshold voltage or a typical voltage. And also this is the radiation time versus such typical threshold voltage value. As you can see, with increasing the ultraviolet radiation time, we can shift its deflect threshold voltage. So it means that by irradiate by the ultraviolet with around the 20 minutes, maybe we can obtain the pseudo normally of situation. So based on the past basic experiment, we create the optimized device structure. This is these data, the conventional result. Firstly, in this result, we can obtain the good device operation without the serious degradation. And also, this is a drain current versus a gate voltage curve. And as you can see there, by using the ultraviolet irradiation, we can obtain the clear on state and off state without the DC gate bias. We consider this is one of the results for the possibility of the pseudo normally of operation we consider. So in order to investigate its detailed electrical property, to investigate its possibility of the pseudo normally of operation, we try to measure those typical measurements. I'd like to explain this measurement method. Firstly, we ground the source and the drain electrode were grounded. And also the gate voltage was applied to the gate structure. And to generate or write the remnant polarization value in the gate insulator. And also after that, we opened gate terminal and measure its current level of the created channel structure. This is the first result. This is the drain current for accumulated channel without DC bias and deflected channel without DC bias. So as you can see here, we can obtain the higher current on-off ratio over the 10 to 7 power without DC gate biasing. And also we check its retention property. This x-axis is the retention time. As you can see there, we by using our structure, we can keep the off state until the 12 hour by using the remnant polarization. And also this is the other specimen result. By improving its both gate and channel structure. Until now, we can keep its off state over 60 hours. So maybe my conclusion is maybe this is the pseudo normally of operation for diamond field effect transistor we consider. But in near future we must investigate the other parameters. This is first success. So we must investigate the other parameters such as the breakdown property and the off state. Yeah. So finally, I will conclude my presentation. In this time, we have prepared the diamond ferroelectric gate field effect transistor with improved partially oxygen terminated channel structure and investigate its electrical property. One of our result, the current density of the hydrogen terminated diamond surface conductive layer can be controlled by using the ultraviolet irradiation time. And also the diamond ferroelectric gate FET with partially oxygen terminated structure can indicate the clear device property without the serious degradation for device property. And also the off state, deflected state due to the remnant polarization. It means that without direct DC gate biasing can be held over the 60 hours now. Yeah, this is that's all. Finally, many thanks for your attention. Thank you. Yeah.
Thank you very much, Professor Kawai. You are very on time. Wow. Okay, it's very great sharing session. Professor Kawai already shared to us about the age-terminated diamond field effect transistor with ferroelectric or FET, and many things that he already explored, many novelty that already shared with us, and I think that novelty will have the revolution for the electronic or the electrical material. Okay, to all participants, please, if you have any question, you can write down your question to the chat room, and then for the Q&A we will have after the second keynote speaker deliver his speech. But in the meantime, you can write down your question into the chat room. Okay. Thank you, Professor Kawai. Please wait a moment. After the second speaker,
okay.
We will have the Q&A session. Okay.
Thank you.
Okay. Thank you for your presentation. Okay.
Yeah.
We will continue to our second presenter.
Yes.
Professor Andika. I would like to say hello to Prof. Andika. Okay. Hello, Prof. Andika. Can you hear me?
Yes, I can hear you.
Okay, Prof. Andika, you can share your PPT now, your slide now.
Okay. Wait a moment. Okay. So.
Okay, before Professor Andika deliver his presentation, I would like to brief his bio. his curriculum vitae. Full name, Professor Dr. Ing Andika Widya Pramono, MSc. He is a full professor since last year, Prof, if I'm not wrong. And then, yeah, he's, wait a moment. He has involved in many workshops, both the national and the international workshop regarding the managerial workshop, including the managerial workshop as well. For the overseas workshop, he already joined with the LIPI JSPS research training program, and then bio nano composite, and many other related with material research training on micro texture analysis of S-down NB-tin intermetallic. Also the Erasmus Mobility Program in the 2018. And then for the managerial history, for the last, at the 2010 to 29, Professor Andika is the director of the Research Center for Metallurgy and Materials. And he also active in the organizational, like the Himpanindo, Indonesian Research Union, and then the Society of Biomaterial of Indonesia, and also the Material Research Society. And he also is the alumni of Ikatan Alumni, the Habibi program, or IB. Okay, Professor Andika, you can deliver your presentation. So the time is yours. It's about 40 minutes. Please.
Thank you very much, Dr. Denny Siti Hairudini. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good evening all.
Waalaikumsalam.
Yes. First of all, I hope my voice is clear enough for you, because I'm using two devices, smartphone, PowerPoint, and I use my smartphone to come out with my voice. So okay, it is very very happy for me, to be able to share some information regarding the application of superconductors in the field of energy harvesting. I assume I have the same period of time as the previous professor, previous keynote speaker. That's 30 minutes, right? 30 minutes of presentation. I don't know, but most of you already know about the definition or the meaning of the energy harvesting. So I think I just maybe just put some more emphasis on it, because could be some of you think that energy harvesting is like we are talking again about what's that, solar energy, and then the water energy, the ocean wave energy, but actually it's not like that. In case some of you think energy harvesting is something like that. So the energy harvesting is actually something different, and we will discuss about it today. And I will begin with the definition of the knowledge of the superconductor. This is my outline, my presentation outline, the introduction, and then the wearable electronics, and then wireless sensor network, conclusion, and then the near future advance. I begin with the introduction. So, as we know that in Professor Mans discovered the great behavior, but when it is superconducting material, I'm sorry, it seems that my maybe it's because of okay, there's some trouble in connection in my laptop, in my presentation, not in my voice. Then at a certain point of temperature, suddenly drops. As you see, the green one, it suddenly drops. So there is a so-called the critical temperature to define or to make a borderline between the normal condition and the superconducting condition. And Mr. Heike Kamerling-Ons tried that for the first time for the mercury. So his discovery was actually in the mercury. Okay, wait. So I hope, I don't know what happened, but okay, I continue. So this is the timeline of many attempts, hundreds attempts since the beginning of the 20th century regarding the research and development in superconducting material. Okay, so I don't know, is this a movie or my presentation? I don't know, but I try to have a control of my laptop, but it doesn't work. So I just continue. Okay. Yeah. Okay. As you see, this is the timeline of the superconductor, and you see that in the borderline of the liquid nitrogen, this is a very significant border that delineates the difference between the low temperature superconductors and high temperature superconductor. There is another definition of the low temperature superconductor and high temperature superconductor. There's what usually people think is by the temperature of the liquid nitrogen that evaporates into gas. So as you see that so far the low temperature superconductor still more than the high temperature superconductor. So as you see in the beginning, 1900, you see there is a mercury, there is a lead, okay, and then there's a niobium. And not until 1950s, when the researcher from the, I think the University of Chicago discovered the magnetic horseshoe in the form in the shape of the superconductor that had applicative around 1950 or 1960. There was a discovery of niobium tin and then niobium germanium. Niobium tin is the very first or one of the first technical superconductors that can be implemented. The definition of the technical superconductor is that it can be or it could be implemented into wires and cable. Mercury, lead, the first discovered superconductor, was not technical superconductor. And then as you see, all the research and development attempts around in the period of 1985 to 1990, in the late 1980s, the beginning of 1990, there's a cuprate superconductor. This cuprate superconductor can use the liquid nitrogen as the cooling medium or the cryogenic medium. As you see, the first one that reached for the cuprate is the barium copper oxide with the addition of deuterium. And the TC, this is as you see, this is about 75, 80 Kelvin, as you see in the diagram. And then, but not until 2005, in the period of 2005 and 2010, then the iron-based superconductor with the addition of arsenic and strontium reach the temperature of the evaporation of the liquid nitrogen, as you see in the period 2005 until 2010. After that, people start dealing with the high temperature superconductor. There is one interesting point about the magnesium diboride. As you see, from the year 2000 until 2005, there was a discovery of magnesium diboride by the Japanese professor. And this is actually a very good low temperature superconductor so far. And magnesium diboride is actually still in the investigation, but the tendency is to increase the performance to be applied for the high current, high voltage application for the power line and the other high voltage or high current electrical component. So okay, now in the high temperature superconductor, the latest attempt empirically, not theoretically, empirically, has been the discovery of the lanthanum decahydride, LaH10. And this lanthanum decahydride has the TC of the minus, only minus 23 centigrade. So it's yeah, it can be functional in the very normal cooling device. But theoretically, through the density functional theory, the higher TC is predicted to be happening soon enough, hopefully, in the yttrium decahydride, YH10. So so that's the timeline of the superconductor. I don't know. Am I getting help in moving forward or backward in this PowerPoint presentation? Because I cannot. Okay. As you see. Okay, next. Okay. So the high temperature superconductor okay. try to mute it. Okay. Okay. So the room or near room temperature superconductor that is happening in the hydride, and then still in the experimental, that is use and fill. So this is a very micro size implementation. So that is this superconductor. As you see, the lanthanum decahydride is pressed a very high pressure by diamond anvil in the micro size, and then with the hydrogen environment, when you do that and when you measure the current, then you will find that the diagram of TC will be formed in the lanthanum decahydride. So this is by high loading of diamond anvil. Okay, next. If I'm getting help, then next. Okay. So this is the lanthanum decahydride crystal structure. Okay, mainly it's actually cubic. Initially, it was discovered having the cubic structure, but then the attempts of the research and it has various upon various pressure, as you see on the right side of the slide in front of you. So, so let's say if we can, presumably, when we can make this lanthanum process that's scalable, then when you sinter it, then it has the cubic structure. So it is synthesized at 730 centigrade. Okay, next. Okay. Now, what you see in front of you is the TC prediction. As I said before, that the yttrium decahydride, not lanthanum decahydride, still theoretically predicted using the density functional theory. But the theoretical approach has been such that it can form this diagram, the values of TC as a function of various pressure. This is theoretically, not empirically, through the density functional theory. So it is very, very, as you see, very interesting, the TC of this yttrium decahydride. Very, very interesting, because as you see, let's say 300 Kelvin, you subtract it by 273, then we are dealing with the room temperature application of the yttrium decahydride. Okay, next. Okay, I'm good. Okay, so lanthanum decahydride and yttrium decahydride, or lanthanum, or okay, lanthanum and yttrium come from the red earth element. Okay, this is the country that domination of the red earth element, and what I circle there with the yellow circle is the yttrium and lanthanum. Of course, since superconductivity in yttrium decahydride and lanthanum decahydride is not popular, so the application still written as spark plugs, cancer treatment, camera lenses for the lanthanum, and the battery electrode. Okay, next. I'm sorry if I realized that I'm getting help in the presentation. I thought I'm doing myself. And if I mention about rare earth element in Indonesia, then the rare earth element very abundant in this, at least these two minerals, monazite and the cenotype. And these two minerals are abundantly available in the Bangka Belitung Island. Lanthanum comes from the monazite that has been by PT Tima has been now available in the form of lanthanum hydroxide. Yttrium comes from xenotime and available in the form of phosphate. So actually, it's very, very interesting if we can make use of this lanthanum hydroxide and yttrium phosphate. Okay, next. Okay, if we talk about the main application of superconductivity, then this is a very, very popular one. And I think some, or let's say most of you already know that this is not the application without price. It is very, very commercial application. For example, superconducting magnet. And then on the right side, you see this is MRI, magnetic resonance imaging. That's already available in many, many hospitals throughout the world. And then some application in the magnetic levitation train, maglev. And then there is also some prototyping and scaling up of the superconducting transformer. Okay, next. Yes, next, please. Now, how about in energy harvesting? So energy harvesting is actually, we make use the existing condition that is realized or unrealized producing energy. But usually energy harvesting is not as a resulting, it's not a big energy, but a very small or medium scale. Okay, next. The energy harvesting, by definition, refers to any attempt to acquire, derive. So you get it, you derive it, you develop it, and store it from external sources. Could be a solar power, wind energy, thermal energy, and etc. Is many, actually many. Okay, into autonomous devices. Autonomous devices. Energy harvesting is also known as the power harvesting, energy scavenging, or ambient power. And with that, what I said, it provides a very small amount of power for low energy electronics. That's the definition of this energy harvesting. Next. So the objective of this our discussion is what happened with the energy harvesting through the superconducting material for the wearable electronic devices and wireless sensor network. Next. Yes, please, next. Okay. This is the timeline of the Internet of Things. This is the Internet of Things that's already began in 1969 in its development. It's very, very potential to use the energy harvesting. Okay, next. Okay, now we talk about the wearable electronics. Next, please. Okay. One of very important attempts is the use of the gallium indium tin nanodroplets. This gallium indium tin material is a superconducting material. So what these people do, this is from the three-party in Australia and China. They developed this gallium indium tin nanodroplets by using this method, the sonification from the bulk liquid metal. Okay, and then they form this nano size or near nano size nanodroplet. And then this nanodroplet of gallium indium tin is or has been lithographed into flexible electrode or circuit. As you see in the photos in front of you, that it can be lithographed or it can be painted into this electronic circuit. And as you see, the application is in the small size, and it could be useful for the wearable electronic. Okay, next. Yeah. And then the second one is the application or the implementation or the combination of carbon black and graphene for this composite for the application for the flexible supercapacitor. Graphene, actually, if you combine two layers of graphene with making the degree of 1.1 degree, then it can act as the superconducting material. So this is the combination of graphene oxide and then carbon black, and then reduce, and then they make into the composite and then apply that for the supercapacitor. Okay, next. Now this is the property of the supercapacitor that using the carbon black and graphene at a very, very optimum. Okay, based on this paper, this is a very, very optimum condition can be or could be attained by this graphene and carbon black. Next. Okay, the third one is a waveable asymmetric carbon nanotube, which is doped or infused by manganese oxide particles and reduced graphene oxide. And this is application for the electronic textile. And for the application or implementation is in the wearable electronics. Okay, next. Yes, next, please. Okay, so this is the property of this electronic textile. Okay, next. Now I'll talk about the wireless sensor network. Next, please. So when I talk about the wireless sensor network, it is very good to begin with the so-called this Josephson junction. Maybe I think some of you know about this Josephson junction. That is the arrangement or the order of this superconductor, insulator, and superconductor. This Josephson junction is this Mr. Josephson found it and or discovered it, and he measured that this Cooper pair as the basic fundamental of this superconductivity can move very easily through the tunneling effect in the insulator part. Josephson effect is the supercurrent that flow indefinitely long without any voltage applied. That's the significance of it. And in the decade of 1990s, many attempts were conducted to fabricate high-performance Josephson junction based on never with the low temperature superconductor, but directly with the high temperature superconductor. Next, please. The development based on Josephson junction, the next one is the so-called SQUID, the superconducting quantum interference devices. As you see in the picture in front of you, this SQUID develop or generate the magnetic field. As you see, there is also a part of it. This is that has the Josephson junction, and this device may be configured as a magnetometer to detect incredibly small magnetic field, small enough to measure the magnetic field in the living organism. Okay, next. Okay. In 1990s, there was a SQUID receiver, which was developed based on the diagram in front of you. There is a SQUID magnetometer inside the liquid nitrogen. As you see, this is high temperature conductor. There's a probe, and then connected to all the system that use it or amplify. Okay, next. Yes, next please. So this is the application. As you see, the box on the left side with the dash line is the squid hut, and then it acts as a sensor, and then it connected to the control room, and then nowadays it connected also to the network for the remote sensing or remote detection. This is the squid geomagnetic signal analysis and modeling based on Schumann resonance in the Earth ionosphere cavity. This is the application in the geology. Okay, next. So the third application is the wireless sensor network for monitoring structural health. It is bridges, building, human, automobile, machine, even the aircraft. So this is using the wireless sensor based on the superconducting material. So this is what I call this Internet of Things now getting into impact in this situation. Next. Yes, please. So the maintenance-free energy for this sensor comes from the energy of vibration collected by levitation-based energy disperser system, the sensor. So when we talk about levitation, it can come from the superconducting materials, Meissner effect, DC electromagnets, eddy current, permanent magnet, and diamagnetic. What's very popular is using the superconducting material and the electromagnetic system. Okay, next. So this is the what as mentioned before, the wireless sensor based on the magnetic levitation. As you see, there is a magnet, there is a copper coil. Okay, this is the basic principle of it, and there's another magnet in the center of it. So there's a challenge when you use the copper coil. That is when you have to connect it with the MEMS, micro electromechanical system, and the electrical resistivity of the copper. Then the solution is the use of low resistance conducting wire or even superconducting wire. When we use the superconducting wire, then there's a double function of diamagnetic levitation as well as zero resistant electromagnetic transduction. Okay, next. Okay, the conclusion of it, please, next. So superconductors were empirically verified to be suitable for the application of energy harvesting in the form of wearable electronics and IoT-equipped wireless sensor network, or WSN. And then the superconducting material may provide alternative solution for the energy harvesting of WSN by acting as double diamagnetic levitation and zero resistant electromagnetic transduction. Next. The future attempt. So actually, yes, please, next. The future attempts is actually going back to this timeline. What will happen? What will happen? Now we should focus ourselves to the high temperature superconductor, especially the lanthanum decahedrite that's already empirically discovered, and then continuing on this cuprate superconductors, and then empirically proven the deuterium decahedrite that is already invented theoretically by density functional theory. I think that is from me. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof. Andika, for your delivering your presentation about the superconductor, about energy harvesting material based on superconductor. Okay, we already have two speakers deliver their material, and now is for the discussion Q&A session. Please, if there is any question, you can put in the chat, or if possible, you also can just directly, and maybe I ask to the co-host to unmute or and in the video mode. Please, anyone, if you have any question, just address to who? To Professor Andika or Professor Kawai, like that, please. Okay. Meanwhile, Professor Kawai, can you hear me?
Yes.
Okay.
Yeah.
Okay. Meanwhile, we waiting the question from the floor, from the participant. Okay, I have some little question for you.
Already?
I'm curious, based on the technique, the method that you develop in. Yeah, I would like to asking about the method, about the technique for the thin film. Yeah, for the make the layer, the thin film in your laboratory. If possible.
Yeah.
Because from your slide you show about the thin film deposition. By your special technique, I think that you mentioned about low temperature. Yeah, and then the film is deposited on the diamond FE ferroelectric FET.
Yes.
Field effect transistor, and actually for the FET, for the FET application, so what is the range of the thin film and what is the proper thinness of the film itself?
Firstly, I will share my presentation file, and about the film fabrication, we use the conventional spin coating method. This is a very simple one, and
spin coating.
To create this organic ferroelectric thin film, we can deposit this one by using the spin coating and with roughly low temperature annealing, around the 100 degrees C. It's okay. And also,
so the thickness is in the nanometer or the submicron?
Maybe its film thickness is around under 100 nanometer. Because its band gap, VDF band gap of the VDF TRF thin film is really high. So it means it's really tough insulator. It can work as a tough insulator. So it means we don't need the huge film thickness for gate insulator working, I think.
Yeah. Unfortunately, in your slide, you didn't show the SEM figure. Actually, that's interesting.
Because its film thickness is very thin. Maybe there's no meaning to check the SEM observation. However, to consider the device operating, we must check its surface roughness of gate insulator, and to check the we measure the AFM measurement at the same time of the KFM measurement. As you can see, this is three-dimensional image, but I'm sorry, there's no thickness information, but its film roughness, surface roughness is under the 1 nanometer. So it means our deposited VDF TFE thin film is maybe the angstrom level roughness, I think. It means it is really smooth. And also to create such smooth organic thin film, we don't need the the specialized technique for our spin continuum.
Okay.
Yeah. Because this VDF TRFE is really easy treatment material, I think. Yeah. If you have any interesting, could you ask us, or maybe you can try to use this material for various application, device application, I think.
Oh, very interesting, Prof.
Yeah.
Yeah. If you say that the technique is not so difficult, not so advanced, yeah, I think it's scalable, right? For the industrial scalable when you have the proper performance.
Yeah, thank you.
And yeah, and you want to make scaling up, yeah.
Yeah.
Congratulations, very, very good performance. Also, as I say it from you, as I see from your PPT. Can I have another question, Prof? Hello, Prof. Kawai. Hello. Hello, Professor Kawai.
Hi.
Okay.
Yeah.
I still have one another question.
Yeah.
I see from your list of your CV that you also developed the perovskite oxide material, right?
Yes.
Yeah, like strontium, ruthenium oxide, bismuth-based ferro-oxide. Yeah, I'm
Yeah.
very interesting. Yeah, for that perovskite oxide material.
Yeah.
What kind of the application for the perovskite oxide that you develop in your laboratory? Only for capacitor or any other maybe for PV photovoltaic also?
Yeah. Of course, we investigate the other perovskite materials, not only the ferroelectric material, but also the high-TC superconductor. And in near future, I would like to, I already explained these perovskite ferroelectric material can modulate the huge amount of the carrier compared with other conventional gate insulator. So, and also, but the serious problem is its band gap is still lower. So, in the future, we would like to find out some candidate ferroelectric perovskite ferroelectric material with both large band gap and huge remnant polarization value. And by finding out those material, we can maybe we can combine with our ferroelectric gate field effect transistor system, I think. And also the other different direction. I have now one idea by combining with the ferroelectric gate insulator and high-TC superconductor channel structure. Yeah, and maybe Professor Andika really know the high-TC superconductor has a huge amount of the carrier level, and also it is impossible to modulate such huge number of the carrier such as the superconductor. But I think by using the ferroelectric material with huge polarization value, maybe we can we might be able to realize such superconducting ferroelectric gate insulator transistor to modulate the really huge amount of the carrier. And also maybe we can apply such devices for future application for the really high power application, we believe. Okay.
Okay. Yeah, Professor Kawai, I think I will go back again to you. I need to go to Professor Andika first. Professor
Yes.
Andika, can you hear me?
Yes, yes, I
Yeah.
can hear you.
Okay, we have the question from Dr. Hendrik. So why graphene is not shown in the timeline of your superconductor? The graphene might be a superconductor when stacking between layers. Is it right? Maybe you can.
Okay, thank you
Please.
very much, Dr. Denny, and thank you very much for Mr. Hendrik for a very good question. My answer is that it should be there. Yeah, this graphene should be there in this timeline. The reason it is not there is maybe it's because the discovery of the graphene as a superconductor when you stack it to layer with the magic angle of 1.1 is just recently. My answer is it should be there. It should be there, even though that's not the high temperature superconductor, but actually it's a very, very good discourse just recently. And my answer is it should be in that timeline.
Okay, so that's our homework, Prof. Andika, to make it, to put it in the timeline.
Yes.
Yeah. uh, okay, is there okay? Maybe the next question is from me. This is just the very basic. I think just want to confirm. So Prof. Andika, so what is the best TC of the superconductor material now in the commercial level? Previously, you mentioned about the room temperatures superconductor that you already developed, right?
Yeah, right.
Yeah, maybe
So
you can, yeah, please.
yes, okay. The high temperature superconductor that has a very high temperature, okay, not low temperature. The high temperature superconductor that have been intensively investigated is the cupred. The R&D attempt have already reached how to increase not only the TC but also the GC, the current density. But as you saw in my diagram of timeline of superconductor, empirically, the highest superconductor so far is discovered in the lanthanum decahydride. But I mentioned that, I showed that before, that it's in a very micro scale size. High diamond anvil in the hydrogen environment, very high loading. It is empirically proven, discovered, minus 23 centigrade with 150 gigapascal. But it's not yet commercial. This is still the invention of the TC and around that. I think it should be the next challenge is how to make it, this is higher TC, and then implementable. The process, the synthesizing method should be scalable. The next candidate, as theoretically proven, is the yttrium decahydride. That's a room temperature, but still theoretically by density functional theory. And our challenge in Indonesia is that we have lanthanum hydroxide from monazite. It's commercially available from PT Timah. And then we have yttrium phosphate. So I think this is for us a very, very challenging situation. These two, this lanthanum decahydride and yttrium decahydride.
Yeah. Yes, I agree. I'm very agree with you, Prof. That two material, lanthanum, yttrium, also usually applied for any other functional material. For instance, for the fuel cell, solid oxide fuel cell, also we using that material. Maybe I have the following question, Prof. Andika. Is it okay? Okay. Meanwhile, we have the source of the mining, right? From that material that you mentioned before. Maybe you have the vision for the next future when such of that material we use from the waste or the recycling existing one from the electronic material waste, or we can use, for instance, by other sustainable material. What do you comment about it? Okay, Prof. Andika?
Yes.
Okay,
Uh,
please.
okay, can you repeat again your question because it's some technical
Okay.
communication? Okay, I'm sorry.
Okay.
Okay, can you?
Okay. So the two the metal that you mentioned before, like lanthanum and yttrium, that you use for our local superconductor, I very agree with you because we have that resource, the mining, the material resource. So,
Yes.
for instance, when we want to use another alternative one, for instance, from the recycling material that we mining from the existing electronic material, is it also possible to apply it, or it should be in the like the lanthanum nitrate, lanthanum phosphate form, or how, in order to make the proper superconductor?
Okay, thank you very much for the question. So actually, is it very possible if you use the secondary resource from the waste, electronic waste? It's very, very possible. The question is, the challenge is, if you can extract that, then that material, which is or which are superconducting, it's a high temperature superconductor or low temperature superconductor. So that's the basic question first. If you what we find, or if we can extract from the secondary resource or waste is the low temperature superconductor, then actually it is applicable, but it's very with the very low temperature. You have to use either helium or hydrogen. And if you talk about the low temperature superconductor, the challenge is how easy it is to be implemented in the normal daily life. The most popular, the most accepted application of the low temperature superconductor is so far is the MRI. And then there's one in the Research Center for Chemistry, there's an NMR. MRI and MR in the health and for the research and development. So actually it's no problem. It's very potential if you can extract that from the electronic waste. The question is, if we do that, then what type of superconductor material? It's very good if we can find the high temperature superconductor in the group of cuprate, barium cuprate, with the addition of yttrium and others, lanthanum. So you can use the nitrogen. So actually, it's just like that. So the question is whether you find it is a low temperature or high temperature. I personally haven't not known yet if we can find lanthanum or yttrium from the secondary resource. I haven't marked that yet in my mind. I still think about it from the primary resource, the monazite and the cenotype. That's okay.
Okay, thank you. Very insightful, Prof. I have to go back again to Professor Kawai. Later, I will go back to you again.
Yeah.
Okay, Professor Kawai, we have one question here from the floor from Ahmad Ridwan Tresna.
Yeah.
Prof. Kawai, he gave his question. Sorry if my question is not relevant for your presentation. I'm wondering the isotope effect on diamond. We substitute by C12 or by C13. Substitute C12 by C13. So can we get a change in the band structure if diamond? And can we make a better structure based on isotopic doping?
Yeah. I already answered that question by chat. I think it is not easy.
By chat.
To modulate its band structure by using the irradiation, isotope irradiation, because as you know, the diamond, its chemical bond is really tough. And also, so based on such tough chemical bond of diamond, we can apply those material or the space application. Yeah. For example, the space emitter system in the space. And also, based on those material property, I think it is not easy to modulate them. But in the case of the doping level, maybe we might be able to modulate its band structure by changing the doping level, such as it is the famous specialized doping technique, the delta doping, homoepitaxial through the homoepitaxial grown, I think. Maybe.
Okay. Yeah, because Dr. Nugraha is usually he exploring on the theoretical and computational. Maybe he always have the vision, the future vision. He's very good on it. Maybe he interesting on to enhance your your research. Okay, maybe later I'll go back again to you, Professor Kawai.
Yeah.
In the meantime, I have another question for Professor Andika. Again, this is from Mr. Hendrik. So as we have seen the picture of magnet levitation in your slide by using the spring, so what determine the distance between the dust of two? Is there a way to control the distance? So if I want to make it separate several meters between the dust to spring, how could that be done? Prof. Andika?
Okay, thank you very much,
Hello,
Denny.
Prof.
And
Andika, can you hear me?
yes, yeah, I can hear you. Yes, I can hear you. Yes, thank you very much for the question and also for Mr. Hendrik. As I mentioned, I already answered that in the chat. That it depends on the magnetic levitation, because yes, the Meissner effect as the fundamental of the magnetic levitation is depend on first the magnetic flux that cannot go through the superconducting material when you are below TC. So it means the power to levitate it depends on the magnetic flux. And you can, in some paper, in the Coprats and also in the magnesium diboride, they increase that by using the compositional design. So actually, it actually improved the magnetic flux property. But the challenge is that the fundamental challenge in the superconductivity is that this triangular shape diagram of DC, GC, and TC, if you increase GC, can sacrifice the TC. But actually, it is possible if you can widen or broaden this triangular shape of DC, GC, and TC. And compositional design, doping, and heat treatment may do that. I
see. Okay, Prof. Andika, can I mention about the oral professor research oral presentation book in here? Because when I searching in the Google, it's already in the link open for everyone, right?
Yes. My oration, professor.
Yeah,
research.
oration. Oration.
Yes.
Yeah. I just want to make just announcement or promotion, if possible. If anyone who want interesting, you can search and download it. It's free. You just can directly put Professor Andika name. Okay, it's about the superconductor. Yeah, especially for the rookie like me about the superconductor, like what? It's very interesting and it's very useful for me. Okay, Prof. Andika, we have another question from Dr. Nono. Oh, this is very interesting question. So, do you have any idea how to make the technology of hoverboard such in the movie?
Okay. Okay. I think if I cannot go too far from the superconductivity, then my specific answer for this specific question is that use the high temperature superconductor. It is very possible to do that if we can have the room temperature superconductor. Then there is no hush regarding the cryogenic cooling. So that's why the goal for this lanthanum and yttrium decahydride, it's very, very promising. We can do this technology if we can, let's say, I say that eliminate cryogenic cooling system that's very, very complex and not practical. So first, in the aspect from the point of view of superconductivity, to answer that, then use the high temperature superconductor, especially the room temperature one. Then from that, we can move on. You can imagine that if this is happen in the room temperature, this effect and this meditating development, and then the first one is how to attain the room temperature superconductor with the scalable synthesizing process technique. Not the use of the diamond anvil is so very small, micro scale. It is not implementable.
Okay. Okay. Meanwhile, we waiting another question from the floor, from the participant. I have another question for you, Prof. Andika. Is it possible the superconductivity of the material is changed by the form of the material? For instance, we have the similar composition of the material. We develop the wire, the plate, and maybe another bulk form. Is it different with the different of form of the material to their superconductivity?
Yes, you mean in the form of your question in the form of wire or in the kind of material, the variation of material? Sorry, I didn't
the shape, the shape of the
okay,
material.
Yeah. Okay, okay, yes. So actually, if we talk about the shape, if let's say wire, and then wire, we talk about the coil, or we talk about the bulk material. So there's of course, there's a characteristic. There's a characteristic. It's not the same, but the fundamental property of this, I mean, the superconducting wire, have to be careful regarding. Actually, even though we already have the MRI using the superconducting magnet and coil, there is an effect of straining. When you coiling the wire, there is a strain that. But if you use the bulk material, then the question is how in the aspect of how we manufacture that. When the scale or the size of it is already significantly big enough. I mean, the superconducting material is actually most of them is very brittle, and then especially when we talk about the high temperature superconductor, then it's very challenging when we shape it into the bulk material, either this straight or bend. That's actually the question in the manufacturing aspect of that. Even though it's still possible, what is still normal is using the wire and then coil.
Wire and
so
coil. So that's the most feasible one, using wire form.
Right. That is the most until now the dominant of this superconducting shape. I mean, the superconducting commodity or superconductor commodity in the aspect of the shape. Still dominant is in the wire, or ribbon, wire or ribbon.
Okay. Prof. Andika, would you please re-describe about the harvesting concept based on the superconductor material? I still not clear enough before. Excuse me, if you please.
Okay. the energy harvesting of this based on this superconducting material. So actually, the energy harvesting that people talk about globally is something that happen in the daily life without people too much realizing it. Okay.
Yeah.
Of course, energy harvesting can be from solar energy, yes, wind energy, yes, but also like when we talk about the vibrational energy, sound energy, and then kinetic energy based on the small scale activity. So the difference of this energy that is developed and then applied for the autonomous device. When you apply that, of course, you can use copper wire.
Correct.
A circuit that is very conventional. The idea of this application of superconducting material in energy harvesting is to replace or to substitute this copper or the conventional material that acts as the conductor to become superconductor, so that the energy efficiency is getting higher. Now, in my presentation, one of the very good example is when you the gallium indium tin, when you make it into nano droplets by the sonification, and then you use the technology of lithography and make it to the circuit, something like that. That literature that I observed and I read, these three-party people that developed this gallium indium tin, they mentioned that they also already developed the prototype of this wearable electronic based on this gallium indium tin, even though I didn't see the prototype of it, but they mentioned, they claim that they developed also the wearable electronic. I believe it is prototype, that's not yet commercial, based on the lithograph gallium indium tin. So this is how to increase the energy efficiency based on the conducting property. So when you use superconducting material, it means R is 0. It means higher.
Correct.
So that's the position of the superconducting material in the energy harvesting system.
Okay. Now it's clear, more clear than before. Thank you, Prof. Andika, for your insightful replay answer. Okay, maybe I'll go back to Professor Kawai. Are you still there, Prof?
Yes.
Hello?
Yeah.
Okay, maybe this is out of topic from your slide, but I just curious about the perovskite application, the perovskite oxide of your material, like the bismuth ferrite oxide, for instance, for the PV application. Are you also interested, or are you also concerned on the solar energy application of your perovskite oxide?
I know there are many researchers who try to create a specialized solar cell using the fundamental ferroelectricity. I know the one of the some person, one of the, my friend also try to create such new solar cell system, but I think that it is not easy to apply those systems for real application, because as you know, the ferroelectric material is roughly work as a insulator. So it means by using the ferroelectric remnant polarization, maybe we can create the some carrier and by photo irradiation, but it is really difficult to pick up those created carrier through the insulator like ferroelectrics. I think, yeah. Of course, yeah, it is the scientific interesting approach, but with considering the real application, maybe it might be really difficult, I think.
Yeah. Okay.
Yeah.
Thank you very much, Prof. Kawai and Prof. Andika for the insightful explanation. Oh, we have still one question for Prof. Andika. Okay. For Prof. Andika, this is the question from Dr. Agung. So do you have the calculation about the efficiency of energy harvesting by using superconductor compared to the conventional materials? For instance, from vibration energy, how many percent the efficiency using the superconductor? Please.
Okay. Okay. Thank you very much, Denny, and thank you very much, Mr. Agung. That's a very good question. If you ask me about the efficiency in the quantitative way, I haven't had the answer about it. Okay, but qualitatively, it should be very logical that the energy efficiency increase. Now, the question is, when we talk about the energy harvesting in this method, it's actually not no longer about the for example, solar cell and a megawatt water energy and a megawatt. That's in a very small scale. In a very small scale. That's what people agree on the definition by energy harvesting in more common way. Now, of course, then if we can use the superconducting material, okay, which has a zero electrical resistivity without getting any complication or any trouble with the cooling system, then it should be very it has significant effect. I haven't had known yet about the quantitative value in statistical way, not as a by example, in statistical way when we use the superconducting material for small scale energy harvesting. What is the energy efficiency? But I believe based on the logical logical aspect or logical property of this superconducting, it will increase the energy efficiency. But I haven't had any known number, a statistical number regarding what the efficiency, the very common way that can be increased, the delta efficiency that can be yielded by using this superconducting material for the energy harvesting, especially in the wearable electronics as well as the wireless sensor network. But it should be better. It should be better. Okay.
Thank you very much, Prof. Andika. I think we have to finish this first session from the plenary session. So please, I would like to invite all the participants to turn on your video. We would like to take a picture together. Please, everyone, just turn on. And maybe the operator, the co-host will take a picture for us. Professor Kawai, can you open your video?
Okay, ready?
Oh, ready, yeah, okay. Okay.
Kang Denny?
Okay, Panono, please. Yes.
Okay. Please, if anybody, the photo is not showing, I think the background is not compatible, or maybe you have to turn off your green screen. If you click the green screen, maybe sometime your face will cover by the background. I think like. Okay.
Okay, maybe Pak Nono, you can give us the mark. Okay, is it finished, Pak Nono?
One more.
One more. Okay, okay. Dr. Nugraha,
There are
please.
2 slides. So now I'm going to take the second slide.
Okay. Give your best
3,
smile.
2, 1. Okay, finish. Thank you.
Finish. Okay. Thank you very much, Dr. Professor Kawai and Professor Andika, for your insightful presentation. So we have to finish this session, and we will go back again at the 10:40. Maybe we take the break time for about 10 minutes, I think. Yes. About 10:40, we will continue with our next plenary speakers, to Dr. Bambang and Dr. Fatwa Firdaus. Okay. I think I return back to the MC. Please, Dr. Wita. Is there any Dr. Wita now? Okay. So if no, maybe we just closing for this first session. Thank you. I would like to say thank you again. Thank you very much for Professor Andika and Professor Takeshi, and to all the participants. And we will go back again at the 10:40. We will have the break time about 10 minutes. Thank you very much.
Segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia. Infrastruktur riset strategik dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian, dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti, dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah Kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, LIPI juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan.
Okay, welcome back again to our ISM 2020 seminar. I would like to welcome to Dr. Fatwa. Dr. Fatwa, are you ready to join with us?
Yes, I'm here.
Okay, nice to hear you. Maybe in the German now it's very early morning, right?
Yeah, it's 15 minutes to 5 now. Yeah.
Wow, it's subuh time in Indonesia. Subuh. Okay, we are very sorry to disturbing your time, your very early morning time.
No, I'm happy to do it. Thank you very much for the opportunity. Yeah.
Oh, yeah. It's also the honor for us actually that you are accepting our invitation. Okay, Dr. Fatwa, and we also already hear Dr. Bambang. Hello, Dr. Bambang, can you hear me?
Yeah. Yeah, okay.
Okay. Okay, wait a moment, because
my voice is okay.
Okay, no problem. It's clear. Very clear enough. Yes, it's clear. Okay, for this second session, we have two plenary keynote. For the first time is Dr. Bambang Prihandoko, and then the second one is Dr. Fatwa Firdaus. Okay, Dr. Bambang will deliver his speech about the current research and development on battery, and Dr. Fatwa will share to us about the photocatalytic and water splitting advanced materials status. Okay, without further ado, I would like to starting for the first speaker, Dr. Bambang, but I would like to share his bio, his biodata. His full name is Dr. Insinyur Bambang Prihandoko, MT, and Dr. Bambang finished his study from the TU Delft in the Netherlands, in the Holland, and then he continued again. So he got to master from the TU Delft and then from the Universitas of Indonesia, the metallurgical and material engineering, and also his doctoral from the University of Indonesia. And Dr. Bambang have a very tremendous research experience regarding the battery or the fuel cells application for the energy application material since 1999, since the early 2000, the solid electrolyte application until currently, until now. Now is Dr. Bambang many research about the lithium ion battery, and I think for the Indonesian researcher about the battery, Dr. Bambang is already very well known. He has many publications, both national and international. And then I would like to, yeah, and also the grant research acceptance that already got by Dr. Bambang. Now he also as the head of the consortium battery, research battery for the lithium, and then as the committee, the head of committee for the SNI nanotechnology since 2011, and also for the SNI, other SNI standard since, yeah, for the mobile, the electrical vehicle since 2016 until now. So as the Masyarakat Ilmuwan and Teknologi Indonesia, the member of the MITI, and also the member of the Matrix, Masyarakat Transportasi Tenaga Listrik, also METI, Masyarakat Energi Terbarukan Indonesia, and also as the member of the Listrik Indonesia. Okay, maybe the co-host, please share the PPT of the Dr. Bambang. Yeah. Okay. Dr. Bambang, the time is yours. It's about 40 minutes. Yeah, you can share your presentation, please.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. And good morning or good afternoon. Ladies and gentlemen, I want to present about the lithium battery as key of energy era. This is the new development of new grid of a lithium battery to make a new energy revolution. And next presentation. Yeah, I am in R&D on lithium battery in the LIPI, or Indonesia Science of. Yeah, the R&D lithium battery in LIPI was become center of excellence for electrochemical energy material. I am a member of IMLB, International Thing on Lithium Battery, and member of HES, Electrochemical Society, and MRSS Material Research Society, and now member of PRN Lithium Battery, National Research Priority on Lithium Battery. This is my workshop, lithium battery on the Pacific, and this is the equipment for to make active material and electrode sheet. Yeah, next. My outline of my presentation is about the first is energy revolution, and second is battery, and the third is lithium metal phosphate, and the last is conclusion. And I want this now about energy revolution in the industrial revolution. This because become industrial revolution need energy, more energy to make a production, mass production, and this it is described the important innovation to meet the industrial revolution and energy revolution. This is the because become an industrial revolution and about the energy revolution. And we can see that's the graphic is between the conventional energy to unconventional energy, like fossil energy. It is very, very high development. And then next, yeah. The energy revolution is driven by scientific and technological progress. Yeah, this is the first is the progress on the petroleum scientific and technological revolution. The push the transition from conventional to conventional oil and gas, but it's now the limited in the limited years. And the second energy revolution is to battery energy storage. Yeah. And then there is begin this year to in the golden age of new energy. Yeah. Next. And this is the from the China from Chinese national oil and gas company, and they make a paper and publication, and so talk about the new energy revolution may come earlier than expected, especially to reduce power generation with the new energy and breakthrough in battery energy storage technology, which strongly promote the coming of new energy era. But there is they have a requirement for the new energy era for the technology of battery is if they can be used for mass production of battery, it can be charged quickly and have a long service and good durable. The new energy era will come sooner. This become earlier in this. This is the requirement. Is the first is mass production, and the second is charged quickly, and the third is a long service and good durability. I want explanation about this requirement for technology battery in the next presentation. Yeah, next.
Next slide.
Next slide. Yeah. Yeah, about the energy revolution, many government in the world make a policy goals about the new energy and the new vehicle. This is electric vehicle. The first is from Norway. Norway, we won the 2025, and Netherlands is the same, and the last is France and UK, Great Britain. He won 2040. I want to stop the conventional electric, the conventional vehicle. This is the policy goals. And next slide. And the energy revolution give the Indonesia is to company Indonesia the must be changing to new energy era. The first is Pertamina. Pertamina is a company of oil refinery, yeah. And the second is an electric company with the power generation from coal. Yeah. They must change to a new energy era, and they begin develop of lithium battery in industry. Yeah. And the other I guess electric vehicle, Indonesia electric vehicle is begin to develop, and now is more than 10 company. And the other is the electrical system. Yeah, next presentation. I want to explain about the requirement. The requirement. The first is lithium battery can to be mass production. Yeah. But the production of lithium battery need more chemical material and more component, like this in the video. Yeah. Is from aluminum, graphite, copper, terus, and then manganese, cobalt, nickel, lithium, and other, and plastic. And the other end, it's to get serious about the recycling lithium-ion battery. This is time to get serious about recycling lithium-ion battery. And we can get the copper, we can get the inert material, we can get the aluminum and the other material. And who is Indonesia about this? Next, let's slide. Indonesia has this mineral for raw material of a lithium battery and begin to extract. We done the R&D about the mineral extraction by hydrometallurgy. Is from raw, from ore of a mining material to extract by hydrometallurgy, and we make the chemical material like the nickel hydroxide, cobalt oxide, magnesium oxide, lithium carbonate, graphite, phosphoric acid, lithium oxide, hematite, sodium bicarbonate, and so. It is the chemical material we make as a raw material for lithium battery, and therefore Indonesia have a ability to be mass production of a lithium battery, and if the great chance to be mass production in Indonesia. Next slide. The second is lithium battery can be charged quickly. Charging capability has therefore become one of the key future targeted by battery and electric vehicle industries. But the factor for the fast charging consideration is more. then we focus it about the atomic scale and nano to micro scale, and then become the fast charging battery of lithium titanium battery or LTO cells. And then this the lithium titanium battery, a great performance in low material and low temperature and super long cycle life. But it's not enough by self on battery pack, and he won't help by the control of battery management control. And the next, yeah, we developed the lithium titanate in my work. I modified the lithium titanate to sodium lithium to decrease working voltage, and it is the success. We have now sodium lithium zirconia titanate in the 1.220x volt. It is more lower than LTO. LTO is 1.55 volt. Next slide. And the third requirement, lithium battery can have a long service of long lifetime and good durability. Durability is like the safety. It is a comparable figure about the more battery. It is in this slide, and we can see the NMC. If only the specific energy is very, very good. And in the comparable with the lithium iron phosphate, the is more lower in the specific energy. But the other is good. Specific power is good, safety good, lifespan is good. And LTO, lithium titanium battery, we have only lifespan, performance, and safety is good. Okay. Next. But the lithium battery can help the development of a battery management system, or BMS. This BMS is any electric system that manages the rechargeable battery, such as protecting the battery from operating outside. It's a safe operating area. This is the function of a management system in the battery. It is about the temperature or the state of charge of the current and other. And then BMS can help the lithium battery more long time and good durability. And next presentation, next slide. This is the function of a battery management system. Estimate the SOC, estimating state of charge, estimating state of health, monitoring cell current voltage and temperature, controlling the battery charging profile, and the other, and the BMS. Therefore, BMS can give lithium battery more on lifetime and more on durability and more on safety. Next slide. And the other requirement now is a lithium battery must have high voltage battery. The application of a lithium battery in the form of a battery pack with high voltage and high capacity, this require high voltage lithium battery. This high voltage operation need high voltage lithium battery. And the current development of a lithium battery, we can see this NMC is very, very good. NMC is nickel metal cobalt oxide. And we develop about the lithium manganese iron phosphate like this in the green line as we comparable with the lithium nickel metal oxide. This the specific capacity is same, but the adding of a cobalt, they make NMC more greater specific capacity, and we can see this more 50 more than the first, and the that is lithium rich nickel metal cobalt is more than 100 is the begin from lithium nickel metal oxide, and it's around 280 milliampere hour per gram. And we want the development of lithium and iron phosphate to new lithium manganese phosphate by adding of the cobalt. We want the response of the material is the same as lithium, nickel, mangan, cobalt, maybe more. Next slide. I was interested to develop lithium metal phosphates because lithium metal phosphate is more safety. This phosphate is the base of a network structure, and so it is more safety to protect of oxygen. Therefore, is lithium iron phosphate is good safety than the lithium nickel manganese oxide. And lithium can all more and deep cycle can all the lithium can all move in the lithium metal phosphate, and deep cycle can be close to 100%. So it's a lithium. So its lifetime is more longer. Metal variation in the lithium metal phosphate can profit an higher working voltage variant, and lithium battery become high voltage battery. This is the example. Lithium iron phosphate have 3.5 volts. Lithium manganese phosphate have 4.1 volt, and lithium nickel phosphate can have 5 volt. Therefore, the development of a high voltage battery is very good in the lithium metal phosphate. And we use the lithium manganese phosphate as a base. We use lithium manganese metal 1 phosphate was chosen as the base of the development of a lithium red and lithium white battery, or merah putih lithium battery. We have a product as lithium merah putih lithium battery. Next slide. And we have planned to produce the lithium red and white battery. This merah putih lithium battery in Indonesia. Lithium red battery as lithium titanate battery. This is a fast charging battery. The composition is anode is sodium lithium zirconia titanate, electrolyte by lithium PF6, and cathode is by lithium manganese phosphate. And lithium white battery, this is lithium battery as a lithium ion battery. The composition is anode graphite, electrolyte 6, and cathode is same as lithium battery red. Next slide. Therefore, we focus to make an industry of merah putih lithium battery. The value chain is like this, and we produce from ore of mining to chemical material and become active material. This can be cathode in anode and electrolyte, and we make a fabric produce to electrode sheet, and then we make a manufacturing for assembling cell and then battery pack. And then this is my work in the national priority of research for lithium battery. Okay. This may be my presentation. Next slide. The conclusion is lithium battery developed by the nanoscale technology will be able to meet the challenge or requirement as a new energy in the future. The second conclusion is development of lithium metal phosphate batteries can be expected to increase Indonesian role in the world market of lithium battery. I think this my presentation is next slide. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Bambang, for your presentation. I think you should hold on for a moment. We will have the discussion Q&A after the next presenter, Dr. Fatwa, deliver these materials. Okay, Dr. Fatwa, you're ready now? You can share your PPT now, okay?
Yes, let me try.
Okay, but before Dr. Fatwa deliver his speech, I would like to read his bio, his CV. His full name is Fatwa Firdaus Abdi. We are very lucky got his as 1 hour plenary keynote speaker because his wow, the education is very excellent. He got his Bachelor of Engineering from the Nanyang Technology University, Singapore, and then he got the 2 master degree, Master of Science from the NUS and Master of Engineering from the MIT, and then he got his PhD cum laude from the Delft University of Technology, same university like Dr. Bamba. And his current position as the Deputy Director of Institute Solar Fuel at the Helmholtz Zentrum Berlin in German, and then group leader previously as a group leader and senior scientist at the same institution. His publication for sure more than 6.
Hello. Hello, am I still connected? Oh, yes, okay. So it's probably Dr. Denny is the one having problem.
Oh, sorry. Before I'm still mute. Okay. I'm sorry for the connection of mine, Dr. Fatwa.
No, that's okay.
Okay,
I was
without
just
further ado,
I thought I was.
okay.
Can
Now
I start
the
then?
time is yours. You can deliver.
Okay.
Yeah, you can start now. Your
Okay.
time is about 40 minutes. Okay, please.
Okay. Yeah. Hi. Thank you very much, Dr. Denny, and also for the organizers for inviting me and also providing the opportunity to deliver this presentation to share a little bit about our work. As introduced, I'm working on solar water splitting and Institute for Solar Fuels in general, but I've been working mostly on solar water splitting. And today I'll share a little bit of a story along the value chain from the materials development point of view. Also at the very end later, just about 5 minutes, I'll share a little bit our activity in transforming these materials that we develop into a large area device, a larger area at least outside of the laboratory scale. All right, so I'll start with a little bit of introduction on where I work, because I don't think that everyone is familiar with SZB. So the name is Helmholtz Zentrum Berlin for Materials and Energy. So it's one of the research center under Helmholtz Association. So in Germany, the national labs like LIPI is divided into 4 different associations. 3 of them are relatively big. Those are the Max Planck associations. Those are the Fraunhofer as well as Helmholtz Association. So, and under Helmholtz Association, there are 19 different research centers. So maybe one of the ones that there's more well known is the Deutsche Synchrotron. So that's DESI. So that's a German synchrotron. It's also under Helmholtz, or the German Aerospace Agency, the DLR. That's also under the Helmholtz Association. We are one of the mid-sized research center, and in Berlin, we're focusing on materials and energy, as the name suggests. And in Berlin, we are located in 2 different places. One is located in Wannsee, so that's a little bit let me see, can I show my pointer? There you go. So the Wannsee is in the southwest of Berlin. So if you know, Berlin is already almost out of Berlin, this area, a little bit green. So this is close to Potsdam, the next city. And there we have, we used to have a nuclear research reactor, but in last December, it was already shut down. So now it's being decommissioned. And we have a lot of other institutes doing compound semiconductor photovoltaics, electrochemical energy storage or battery, like the previous speaker has shown, soft matter, magnetic material, and the institute where I'm working, which is solar fuels. And the second location is Adlershof. So that's really, I think it's about 30 kilometers or close to 40 kilometers from Wannsee. So that's really the other side of Berlin, southeast. And that's where we have our synchrotron. So this is a smaller synchrotron than the German synchrotron at Hamburg, but this is still very useful and it for a lot of materials research that we're doing. So it's called BESSY or Berlin synchrotron. Yeah, was I muted? Maybe I was muted. So we have the Berlin synchrotron, and on top of that, we have the also other research activities on photovoltaics, and also the PV Competence Center that's located in Adlershof. Yeah, so I'll begin by motivating a little bit why we're interested in renewable energy, right? So the previous speaker has already introduced the topic, but I'll restate very briefly, or maybe in order to move towards the water splitting. So the whole goal is actually fossil fuels, right? But in all honesty, so the main problem with using it right now is really the environmental consequences that comes with using fossil fuels. And there's this relatively recent paper that came out in Science about like 4 years ago now that actually listed that in order for us to limit global warming to less than 2 degrees, we need to actually decrease the atmospheric CO2 level by negative 10 gigaton carbon dioxide per year by around 2050. That is actually a pretty big and ambitious target. The question is, how can we actually do that as a whole, right, as the world? Now, I write a very simple equation here. To the amount of population, so how many people are living in a certain land or in the world, right? Multiply by the GDP, the gross domestic product per population, multiply by the amount of carbon dioxide that is emitted per GDP, right? So if you see that it's very simple, the populations gets across here, GDP is also cross, and you get CO2 equals to CO2, right? So that's really simple. So in order for us to decrease the total amount of CO2, one of these terms needs to be decreased. The problem is with population, you know, that it's ever increasing, right? So it's really hard to imagine that we decrease the amount of population in the world, right? And as is the case for the GDP per population, right? So GDP per capita, all countries would like to get better. So especially before the pandemic, right? I mean, throughout the pandemic, we see a decrease of GDP, but I think we hope that we will get out of this pandemic situation. And again, we'll be back as normal. Every country will want to be more prosperous, which means that the GDP per capita of almost all countries will actually increase. So our only hope is actually in decreasing the CO2 per GDP. If we want to decrease total CO2, we need to decrease the CO2 per GDP. Can we actually do that? Well, the data tells us that it has not been shown. So this data that has been collected here is showing the CO2 emissions as a function of GDP for various countries in the world back in 2016. What you can actually really see here is that the amount of CO2 emitted is really proportional to the GDP that country has, right? So historical data doesn't really support our goal of reducing this. For example, Indonesia is there, right? And somewhere in the middle here. And of course, we want to increase the GDP per capita. And if we actually go along this plot here, unfortunately, it will be accompanied with increased CO2 emission. As another correlation that is shown over here is this is still the CO2 emission on the y-axis, but it's against Human Development Index. So Indonesia is somewhere here, right? And if we want to, of course, we want to increase our Human Development Index. And if we do that, according to this plot, we also will increase the emissions per capita. So now, this is historical data or like the data that we have right now. Can we actually break this relationship? So instead of Indonesia, for example, moving upwards in this plot, can we actually move horizontal instead, right? Being more prosperous, increase our GDP without increasing the CO2 emission. Now let's break down the factor that is going inside the CO2 per GDP even further. So we can actually correlate it with the amount of energy consumption per GDP multiplied by the amount of CO2 per energy that we consume. So the first term, we can actually decrease by more efficient use of energy. So basically replacing your bulbs with a higher efficient LED bulb, for example, or other improving the energy efficiency of your engine and whatnot. That can be done with for the first part. But for the second part, we can actually achieve this decrease by transforming to low or even zero carbon energy source. And this is actually the main motivation why we are actually working, looking for alternative renewable energy. So we would like to replace the energy, the fossil fuels that we have right now with something that doesn't emit carbon, so that we don't need to move upwards in this plot over here. All right, so with that introduction, I'll come to show you or share with you 3 facts that I think it's a fact for a search of renewable alternatives. So I don't know if this is a real fact or alternative facts. I think we can argue about that. But I hope I can convince you in the end that some of this is actually pretty true. First of all, I think we know that the sunlight among the various sources of energy that is available to us is the most abundant source of energy. So we have about 120,000 terawatts that is incident on Earth. And 36,000 of it, terawatt of it, is actually incident on the land area of the Earth. Such that, so that's so enormous, such that if we actually just take 0.8% of the surface of the land in the world and cover it with 10% efficient solar device, which is already, the commercial devices are already way ahead of this efficiency, we can actually achieve 30 terawatts, which is the total energy consumption predicted in the year of 2050. To give a feeling about how large or how small that 0.8% is, you can see that if the whole map of the world is here, we just need to cover one small part of South Africa. And in the case of Indonesia, to give a little bit more perspective, Indonesia energy use is 250 gigawatts in 2018. And therefore, we actually need about 20,000 kilometers square of area for that. And just as a comparison, East Kalimantan province alone is way larger than that. And even Central Java is larger than that. So of course, it doesn't need to be concentrated, but if we actually spread it out for different area, we can actually cover 20,000 kilometers squares pretty relatively easy. We do have the land area for that. The problem with solar energy or sunlight is the intermittency. So the availability period of solar energy doesn't coincide with the peak period of energy demand. So of course we have the daily cycle. So sunlight is most available during the midday, the middle of the day, the noon, right? But unfortunately energy demand doesn't work like that. So we need more energy in the morning, in the early morning, and also late, early evenings, for example. And it doesn't really match with the availability of sunlight, right? Also, we have seasonal cycles, especially in the northern and southern hemisphere, where we have winter and summer, and we actually do need more energy in the winter, but the availability of sunlight is actually less over there, much more in the summer. And of course, we have weather fluctuation too. So you want to be able to have an energy source or that is more reliable than that. That brings us to the second fact. If we actually take a look at different types of or ways of storing energy, as shown over here in the simplified plot, we can actually see that the y-axis here is the energy density, and the x-axis here is a power density. This is logarithmic, mind you. So the chemical fuels such as gasoline, why we like it so much, because it has a really high energy density as well as a high power density. Batteries and supercapacitors are good alternative, but their energy and power densities are nowhere near what we can achieve with chemical fuels. And why is that the case? That's really because we are actually storing energy in chemical fuels in the densest form possible, which is chemical bond. So it's bond between atoms. That's how we store the energy. So that's sort of the fact. Batteries, it doesn't mean that batteries and supercapacitors do not have applications, of course, right? But I think this shows that if we actually need to work on all of them, and some applications you cannot actually fulfill everything with just batteries or supercapacitors. The final fact, or more of a situation, so this is an empirical situations that we are facing right now. Unfortunately, electricity is still inaccessible in many locations. So this is related on how we are using energy. We actually do not consume most of our energy in the form of electricity. We only use about 17% in the form of electricity, and 83% of our energy use is in the form of fuels. What does it mean? It means we do have large infrastructure for fuels, but actually not so much for electricity. So now if we combine these three facts together, I think it's not so difficult for us to see or try to conclude that one of the most probably interesting or attractive way of alternative energy is if we actually store or try to make fuels from sunlight. So if we can do that, then we can actually use the abundant source of energy, which is sunlight, that's potentially able to fulfill the whole world's energy demand, and at the same time overcome the intermittency of sunlight. But can we actually do that? Of course, the answer is yes, and that's what plants have been doing in the process that we all know very well called photosynthesis. So plants take carbon dioxide and water and use sunlight to transform them into sugar here, the glucose, some kind of sugar, and release oxygen. Now, it turns out that although this reaction can be driven by sunlight, this is not the simplest reaction. So it's also, this consists of multiple how do you call it? Like you can break it down to several reactions, and the formations of glucose itself is actually happened in the dark in the plant itself. The simplest reaction that you can do with sunlight is water splitting, or one of the simplest is water splitting, where you take water molecules and you break it down into hydrogen and oxygen. And then when you have hydrogen, you can actually use it directly as fuels in fuel cells, for example. Toyota Mirai or different car manufacturers have actually already producing this and releasing it commercially. Also power generation. Siemens also have already working on this. Or you can actually use hydrogen in order to combine it with different types of reaction in order to make whatever it is that we're already making right now. For example, if we put it in a Haber-Bosch reaction, combine it with nitrogen, we can actually make ammonia. And this is something that we're already doing right now. But the hydrogen, unfortunately, comes from unclean or non-green sources. And ammonia is very important because it's a prerequisite or the precursor for fertilizer, which is important in order for our food, right? So to feed us, actually, basically. And another alternative is actually to combine it with carbon monoxide or carbon dioxide in a Fischer-Tropsch reactor, where we can then make any hydrocarbons that we want: methanol, diesel, plastics, paraffin, naphtha, whatever. This process has actually already been done in a large scale in many petroleum or refineries, right? So basic ingredient over here is that how can we actually split water into hydrogen and oxygen? And one of the easiest or the simplest way, no, I wouldn't say the easiest, the simplest way of doing that is in a photoelectrochemical cell. The process is as follows. So we take semiconductor, the simplest configuration is shown over here, where we take semiconductor and in this case metal counter electrode here connected with wire, and we dip it into an electrolyte. And a semiconductor, as you know, it has this valence band and conduction band, where we can actually carry, where we have a full of electron below valence band and empty of electron above valence band, separated by a band gap, right? And for semiconductor, the distance between this conduction band and valence band is within the energy of sunlight. So upon illumination of sunlight, you can actually excite electron from the valence band to the conduction band. You create electrons in the conduction band and holes in the valence band. Now, in the case that I'm showing over here, this is a photoanode. So we are doing oxidation on the semiconductor. And we do have an internal electric field inside the photoanode. I omit the drawing here to make it simpler. That actually shifts the electron to the back contact and the holes to the surface over here. And once the holes here arrive at the surface, it then can oxidize water to form oxygen, whereas electrons goes to the other side and reduce proton to form hydrogen. So the overall reaction can be shown over here. So the half reaction is we have the proton reduction to hydrogen and the water oxidation to oxygen, but the overall reaction is just what I showed you in the previous slide. Water split it into 2 molecules of hydrogen and 1 molecule of oxygen. As you can imagine from this scheme of how it works, one of the most important component is the semiconductor materials, right? So this has been the holy grail of this photocatalysis field, is actually trying to find the materials that actually fulfill all the necessary requirements for photocatalytic water splitting or photoelectrochemical water splitting. The requirements is as follows. So we need to have good visible light absorption, of course, because sunlight
Halo, Dr. Fatwa.
Hello, I'm sorry. I'm back. I'm sorry. I don't know why it's get disconnected.
Okay.
I'll try to share my screen again.
Okay, please.
Can you see it? Yes?
Yes.
Okay, I'm
Yes.
sorry. Okay,
Yes,
I'll continue.
mode.
Yeah, so
Yeah, please.
So the requirements, first of all, is good visible light absorption. That's because in sunlight, if you take the solar spectrum, the large part of it is actually visible light. So we need to have high amount of absorption over there. Second, we also need to have a suitable band edge positions, meaning that the conduction band and valence band needs to be positioned well relative to hydrogen and oxygen evolution potential. And that's because the electrons and holes needs to have enough energy in order to reduce or oxidize water. We also need to have efficient catalysis and efficient carrier transport within the semiconductor. We need to have high stability. We want to dip the semiconductor in water, right? And we also need to have the materials that are cheap. Now in our institute, we're interested at complex metal oxide semiconductors as a material class. And why is it the case? The reason is we like to take advantage of its relatively high stability as compared to 3-5 semiconductors, for example, or as well as the low cost, right? So it is not a very good semiconductors in a way that it doesn't have efficient carrier transport. Sometimes the band edge positions are not too suitable, but we'd like to try to understand it and modify it while taking advantage of these two pluses that the complex metal oxides have. I'll share a particular success story on a one material called bismuth vanadate, or BiVO4. This is a material that I've been working on since my PhD in Delft. So we've been so it's actually around in our daily life more than we know it as a yellow pigment in paint or printing ink, and it's also photocatalytically active. So we already know this for more than 20 years. Monoclinic scheelite is the photoactive phase, and it's an n-type semiconductor with a band gap of 2.4 electron volts, meaning that it absorbs sunlight up to 520 nanometer, which is why the color is yellow. In our group, we deposit it very simply using spray deposition or a spray pyrolysis, where we prepare a precursor consisting bismuth and vanadium precursor, fit it into this nozzle, and then spray it onto a substrate that is located on a hot plate. For example, this is glass substrates, right? And as you can see from the micrograph over here, this film here is the 100 nanometer layer of bismuth vanadate, and the yellow color here is really the bismuth vanadate layer. And
Oh, halo, Dr. Fatwa.
yeah, hello.
Yeah, now it's okay. Okay, please continue, Dr. Fatwa. Hello.
Hello. Yeah.
Yep.
Yeah. So I really
Very good.
don't know. For some reason, Zoom keep kicking me out, and then I'll try coming back in. I'm really sorry for this.
Okay. It's okay. Sometimes happen.
Okay, so
Okay, please continue.
I try to continue here. So our approach is that we try to identify what's limiting the materials.
Halo, Dr. Fatwa. We're still waiting for Dr. Fatwa. Maybe he had some internet connection loss. Hello, Dr. Fatwa. You still
Yes.
mute? Yeah. Okay. Maybe your video to lowering the bandwidth. I think I just share your presentation.
Okay, I'll try to do that, right? I'll try to stop my video and then I'll just share my presentation. Okay. Do you see it now? Yes? I'm assuming so, right? Okay, so we try to identify what's limiting the...
Sorry, the PPT not yet shared.
Oh.
Okay. Okay, now it's okay.
Yeah. So we try to identify what's limiting the performance in our bismuth vanadate, right? So the way that we do it is we try to identify which of the processes that happen inside the material that is limiting. So we can divide it into absorption, so light absorption here, and then carrier separation, so how the electrons and holes are separated, and finally the catalysis that happens at the surface. The first thing that we found out is that these water oxidation kinetics are slow, and that can be actually the slow process prevents our photocurrent for having too high. And the solutions to that, as a way to solve that, we deposit cobalt phosphate catalyst. As you can see on the right-hand side, we have the photocurrent as a function of potential. Without the catalyst, we have this black curve. And as soon as we put this cobalt phosphate catalyst, we increase the photocurrents quite significantly. The next problem that we found is a poor carrier transport, meaning that the conductivity is not very good. So we try to dope it with tungsten, for example. Tungsten replaces vanadium and introduce additional electron. Or we can also insert hydrogen. Hydrogen goes to the interstitial and insert electrons. So this solves the poor carrier transport issue. And once we solved that, we came into another problem, which is the poor charge carrier separation. And we addressed that by introducing dopant gradient. What we did in short is that we tried to introduce electric field inside the whole thickness of the film. And by doing that, we separate electron to go to one side and then holes to go to the other side. Other peoples have also tried nanostructuring. We actually do not work on this methodology in our labs so much, but this has also been proven very effective. So you try to decrease the amount of decrease the thickness of bismuth vanadate so that the carriers do not need to travel so far. But by nanostructuring, you ensure that the light absorption is still pretty high. And in terms of the progress of bismuth vanadate is summarized over here. So the number of photocurrents of the different groups that have been working on bismuth vanadate. And as you can see, in the last 10 years, we have really had a really significant increase of performance, right? So it's such that the highest photocurrent that we have right now is already very close to the theoretical limit. Even so, the oxide-based devices have also been demonstrated. For example, we've shown a device that shows 5% efficiency in collaborations between Delft and SZB. And we also collaborated with our colleagues in Korea, where we show a device of about 8% efficiency. And that's also, of course, not only us, other groups have also been working on oxide-based devices. Now I go back to this plot now, and the other message that I'd like to send is that since the photocurrent is already very close to the theoretical limit, the only possibility if we want to improve the performance more significantly is if we can actually go beyond this limit, right? Or in other words, can we actually shift this limit upwards so that we can go further than this 7.5 milliamps per square centimeter? And one way to do that is actually by decreasing the band gap of bismuth vanadate. And we can do that, for example, with sulfur incorporation. So bismuth vanadate, the valence band is composed of mainly oxygen 2p orbital. And if we replace that with sulfur 2p orbital, for example, that is energetically higher than the bismuth, than oxygen 2p, we can increase this valence band positions and decrease the band gap. And when we decrease the band gap, we can increase the absorption, the light absorption that we can part of the solar spectrum that we can absorb, and therefore increase the theoretical limit. So this is the work of Marlene, who was a PhD student in my group. She graduated last year, wherein she did introduce the bismuth vanadate under different partial pressure of sulfur. And as you can see from the photograph here, the film turns from yellow to light brown and then finally to dark brown. And if we look from the X-ray fluorescence and X-ray photoelectron spectroscopy results, we can see that the amount of sulfur, so this is the sulfur to vanadium atomic ratio, increases indeed when we increase the sulfur partial pressure. So this is also collaborations with group at NTU Singapore, Professor Lydia Wong, also Indonesian diaspora, maybe some of you know her, and also my colleague in Kaus who did the DFT calculation. So we, in the end, we shifted the band gap by about 0.3 eV, which then increases the theoretical maximum up to 12%, from 9% to 12%. We confirmed this band gap shift. As you can see here, the band gap moves from about 500 nanometer here to about 580 nanometer. Instead of sulfur, nitrogen has also been reported to be effective, but unfortunately for our particular bismuth vanadate, this has not been successful. Another method is actually to come up with, if we don't want to reduce the band gap of bismuth vanadate, is to come up with a novel complex metal oxide altogether. And one possibility is copper bismuth oxide. It has a band gap of 1.8 electron volts, so it's really good. And the properties are pretty comparable to bismuth vanadate, but the problem is stability. So the copper here, if we put it inside the solution and you do photo reduction of water in this case, it can get reduced to copper plus or even copper metal. Nevertheless, people have actually already been working on it. It's still in earlier development, so we have a couple of films that are shown over here, and the improvement have been quite significant, but we're still a long way to go to the theoretical limit. On this particular front, I also have an ongoing collaborations with Universitas Indonesia, where we try to look at this copper bismuth oxide and nanoparticles of bismuth for a CO2 reduction to formate. Another attractive material or novel complex metal oxide is tin tungstate. So it has a band gap of 1.9 electron volts. So this is also pretty good. And this is a work of Moritz, who graduated last year. He did his PhD, finished his PhD last year. So in this case, we deposit our alpha tin tungstate using pulse laser deposition. As you can see here, we use excimer laser to ablate the target and then deposit it on substrate. So this is under vacuum deposition. Why do we want to do that? Because we want to keep the tin here under 2+ oxidation state. Another problem with this material, though, is that the tin 2+ oxidizes to tin 4+ under photoelectrochemical conditions, which is what you see over here in the red. A bare alpha tin tungstate show a photocurrent at the beginning, but it decreases quite rapidly to almost 0. We can overcome this by depositing a protection layer, nickel oxides. And if you do that, we can actually extend the stability. So this is current as a function of time under sunlight illumination. The performance is relatively stable. And although the photocurrent is still pretty small, so less than 1 milliamps per square centimeter, but this is the record of this material. And we hope that we can actually improve this further. On the other side, the nickel oxide deposition is, on the one side, nickel oxide deposition is good to extend the stability, but at the same time, it actually decreases the photovoltage. As you can see here, this is the photovoltage as a function of nickel oxide layer thickness. And in order to understand this, we went to BESI, the synchrotron in Berlin, where we did hard X-ray photoemission spectroscopy. We want to understand the interface, what's happened at the interface here between alpha tin tungstate and nickel oxide, and we try to investigate it with X-ray with different photon energy. So this is the work of Patrick, who is a current PhD student in my group. So we look at the gist of the study is shown over here, where we'll look at the thin 3D orbital or the core levels as a function of the thickness of nickel oxide. And as you can see, the peak shifted to higher binding energy as we grow thicker tin oxide. It can be interpreted as follows. So we can actually see that if we go to higher binding energy, the tin 4+ contribution is actually increases. So what we see if we deposit thicker nickel oxide layer, we have higher contributions from tin 4+ instead of the tin 2+. And we work with our colleagues at KAUST again, and which shows that if you have tin 4+, you actually have a mid-band gap state, intra-band gap state, that can actually cause the limited photovoltaic. So we're still finalizing a publication on this, so hopefully this can be released pretty soon. All right, so I'm sorry for taking too much time, but I'll try to finish in the next 3 minutes. So we'd like to switch gear with this last few slides. So in the beginning, I'll talk more on the materials development, but here in the last few slides, I like to focus more on how we translate from the materials that we have to the device, right, to large area devices. So if you look at the situations in the field, is that lots of reports of devices actually have a very small active area, less than 1 centimeter. Only a little bit, only a handful of them all demonstrated active area that is larger than 1 centimeter square. So at SGB, we have this efforts where we try to increase the area from 1 centimeter to 50 to 200 to even meter square modules. So in our group, we participated initially with PECDEMO. So this is a European project where we take a look at the initial part of the scale up. But my colleague, Sonia Kalnan, for example, at PVCOB now coordinate another European project called PECSYS, who is looking at this meter square module. So I'm going to share to you just a little bit on this early scale up. So in PECDEMO, the problem that we have, we can already see within this early area increase. So for example, if we look at the materials that is photoelectrodes that is small, right, a lot smaller than 1 centimeter square, we can get efficiency of about 6% in this particular case. But as soon as we increase it to 50 square centimeter, we decrease the solar to hydrogen efficiency by a factor of 3. And we found out that this is not a material problem. So we spent so much time trying to improve the materials, but actually it turns out that this is due to improper electrochemical engineering. So how we design the device, the reactor itself, it actually matters a lot, and that it can decrease the efficiency by a factor of 3. So the efforts in my group, we try to use simulation, multi-physics simulations in order to identify the loss mechanism. So this study over here, for example, is a collaboration with EPFL in Switzerland, where we just model now the different losses, be it from the ohmic losses in the substrate, in the electrolyte, as well as pH gradient. So this is mass transport issue in the electrolyte as a function of scale. And as you can see, indeed, the voltage loss increases quite significantly as we increase the scale of the electrode. One example here is that the pH gradient. So the color map here is the pH of the solution. It starts at 7, but due to reaction, it goes to really alkaline solution close to the cathode. What we can do is that we can try to increase the flow rate, so at least the supply of the new electrolyte, in order to suppress this pH gradient. So this simulation is pretty useful in trying to decrease the amount of experiments, because you cannot actually do a lot of all the experiments that you want with designing different devices. So it's very useful in trying to do that. But the other important thing is to validate the simulation. So this we also do in our group. For example, this is a work by Kesuke, a postdoc in my lab, where we look at the pH measurement, pH and the electrolyte in situ using fluorescence technique. So in the video that you see right now, you see that as we start water splitting, we change the pH of the electrolyte to become more acidic. Blue means more acidic, and red means more alkaline. So we change the pH of the electrolyte throughout the bulk of the electrolyte when we do it in unbuffered electrolyte. Now, if we actually do it in a phosphate buffer, we see that we limit this change of pH only to a very small region close to the electrode, right? So this very useful visualizations is actually helping us in developing better simulations and try to validate the simulations, right? Another thing that we can actually detect as well is the oxygen concentration. So this is the simulation, and we compare it with our measurements, and we see that it qualitatively matches what we actually have from the simulation. Finally, we also have other experimental validation technique. We have this particle image velocimetry, where we can actually measure experimentally the velocity of the liquid electrolyte inside the system so that we can detect convection like this. We also can monitor bubbles using shadowgraphy. So we track it, we determine the sizes, distribution, and the velocities. And all of these are part of the reason why I'm sharing with you is this is part of this Helmholtz Energy Materials Foundry, specifically solar fuels devices facility, which is like our synchrotron is an open access or like an open user facility. So it's open for users from anywhere, basically. So if they have interesting problems that they would like to tackle with our tools, they can actually just contact us. Okay, I take already too much of your time, so I try to end here with a few take-home messages. First of all, solar energy, I hope we see that it's the way to go. We just need to store it, and solar fuels is one possibility. And we need to have a breakthrough in materials development if we want to push this photoelectrochemical water splitting further. And progress in bismuth vanadate has actually been a key example, but now we need to address this band gap issue by either decreasing the band gap with dopant incorporation, for example, like sulfur, or we develop other novel oxides. And finally, I showed you our initial efforts in scale up. It is challenging, but we believe it's important to develop feeling for this. And we cannot wait until the industry is actually being interested in it. So because no industry probably would be attracted by technology that is only demonstrated in very small laboratory scale. So unfortunately, we as a scientist also need to engage our activities as well in that type of efforts. And I showed you that in our group, we combine modeling and validation in order to determine the limitations in these devices. With that, I'd like to acknowledge my group members, the Institute for Solar Fuels, the collaborators, as well as the funding agency. And of course, thank you all for your very, very kind attention. I'm sorry again for the technical difficulties earlier.
Thank you very much, Dr. Fatwa, for your delivery. Very great presentation. Yeah, this is insightful for us, especially for me, because yeah, many inline interesting research with our group in here. Okay, Dr. Fatwa, please hold, and maybe I will give a chance to participant, to all the audience. Please, if you have any question, you can chat directly in our chat box, write down in the chat box, and then address it to who? To Dr. Bambang or Dr. Fatwa. Okay, meanwhile we waiting, I have many questions actually for both of you. Oh, okay, before we going to for Dr. Fatwa, I have one question from Prof. Anna Zulfia for Dr. Bambang first. Okay, Pak Bambang, this is the question from Prof. Anna. So my question addressed to Bapak Bambang, the presentation is interesting and informative. I have a question. You produce lithium-ion battery, namely merah putih, lithium-ion battery. So what is the performance of this battery, such as the specific capacity or energy density in a module? Is it possible for merah putih battery to assembly in electric vehicle? I think next year, the Indonesian government will build the lithium battery industry. What do you think about the mineral resource support in this factory? Pak Bambang, please, time is yours.
Okay. My battery specific capacity is around 160 milliampere hour per gram, or the energy density around 640 watt hour per kilogram. But the problem is my lithium battery is not good stable, because there is the influence of cobalt in this.
Okay, the influence of cobalt.
Cobalt, yeah. Cobalt can change the other metal to have a double valence. Yeah, and then become the lithium-ion battery increase the specific capacity around 260 milliampere hour per gram, and we can have the capacity of battery around 5,000 milliampere 5,000 milliampere hour, but it's not stable. This is the problem. The second is for applicable for the application in electric vehicle. My active material lithium manganese phosphate is good for the fast charging in the application of fast charging battery. I think this the merah lithium battery. Merah this can be application in electric vehicle. And the third equation is about the extract mining material, and we do with my group in the consortium the prepare of the pilot plan to make a pilot plan for the extract mining material. Yeah, this is more than X material for raw material of lithium battery. Yeah, okay.
Okay, thank you for the reply, Dr. Bambang. Please behold, I will go to Dr. Fatwa. There is some question for you, Dr. Fatwa. This is from Dr. Gerald. How much is the hydrogen can be produced by the PEC water splitting, and how its efficiency comparison to other method?
Okay, yeah.
It's very technical.
Yeah, so the problem of how much, thank you very much for the question, first of all. So how much hydrogen can be produced, that depends on, of course, the area that you actually used, right, in order to capture the energy. Its efficiency, the highest efficiency that is reported for direct photoelectrochemical water splitting is now in the order of 19%, and that's using a higher quality materials than complex metal oxide. So that's 3/5. So with complex metal oxide, the highest is at about 8%, but with 3/5 semiconductor, with silicon, it's at about I think the highest is about 15%, and with 3/5 semiconductors, the highest that's been reported is about 19%. And that is actually already pretty high. The competitor, if we want to go for the green way, like the renewable way, is actually, we can already do it like right now by combining two devices. One is photovoltaics and two is electrolyzer. So we can combine commercial photovoltaics and commercial electrolyzers and do water splitting. The highest that is reported, this is also based on high performing PV, 3/5 semiconductors, and really 3 different PEM electrolyzers, I think 3 or 2 stacks of PEM electrolyzers. The highest The highest that they can achieve, the indirect PV electrolyzer, is in the order of 30%. So it's still higher than the 19% that we demonstrated with direct water splitting, but it's not that far. And the US DOE has already they have released several targets over the years, and unfortunately, the target keeps on increasing and increasing. And we the value that we target is in the order of 20 to 25%. And hopefully, with the development of materials and further, we can actually push the direct photoelectrochemical water splitting towards that efficiency. And in order to give you a perspective of how much area is needed in order to generate the hydrogen that you need, so I have here a back of the envelope calculations of a number. If you want to generate 1 kilogram of hydrogen in an 8-hour day, assuming that we have only sunlight for 8 hours, right? So it's unfortunately in this northern hemisphere, we have very short sunlight period, right? So assuming that we can only take sunlight for 8 hours a day, and you want to produce 1 kilogram of hydrogen, you need an area of about 41 meters square. So that's like what, 6 by 6 meter, right? So that's like the rooftop of a house. You can actually theoretically think of it as a way to capture that energy, and it's enough to generate 1 kilogram of hydrogen using a 10% system. So now if we increase that efficiency, of course, this area requirements become smaller. And that is the kind of numbers that we need. And how important, or what is how much is 1 kilogram of hydrogen? So 1 kilogram of hydrogen can generate you about 30 kilowatt hours, if I'm not mistaken. And that is in the same order as the daily use of average daily household in Germany, at least. I'm not sure how it is in Indonesia, but here I think we use an annual energy of a family household of about 3,500 kilowatt hours. So per day, it's about tens of kilowatts hour. So yeah, so it's not impossible, so it's feasible, and that is sort of the. I hope that answers a little bit the question, and also the efficiency comparison. Of course, we cannot compare it very easily with the way we produce hydrogen right now. The way that we do it with methane cracking. So we take hydrogen out of methane, for example, steam reforming. Yes. That's a different technique altogether, and efficiency comparison over there doesn't really make too much sense.
On hydrogen.
Yeah.
Okay, so this is the following question. I think you, instead of comparing from your answer, I think you suggest we just make a hybrid, right? Like previously you stated, using the PV and then PMFC or PEM electrolyzer, right? In order to make a good way of the hydrogen production.
Yeah, that is the way that we can already do right now. Yes.
Okay, nice. Okay. Okay, I will go back to you later, Dr. Fatwa. I have to go to Dr. Bambang again. So, Pak Bambang, this is the question from Prof. Dani Gustaman from Batan. If compare your battery to the battery developed by UNS Solo, yeah. So, what is the difference? Please, Pak Bambang.
UNS developed the NCA battery and MNC battery or NMC battery. Yeah, this difference is like the visual and comparable in the slide. We have we develop about the lithium metal phosphate, and the other is around nickel, cobalt, alumina, or nickel, cobalt, nickel, mangan, cobalt. This is different. This is different on the lifespan and safety. Is very at the results for this. Yeah. Okay.
Okay. I hope it's answered the question, Dr. Prof. Dani. I have to go back to Dr. Fatwa. This is another question from Dr. Nugraha. Yes, Dr. Nugraha have the research interest on the DFT computational like that one. Therefore, the question I think relevant with your material development regarding the yeah. So the question is, there have been a lot of theoretical work on the potential of 2D van der Waals heterostructure for photocatalytic water splitting. For instance, MOS2ZNO heterostructure. What is this? I'm not so familiar with the symbol VDW. And
Van der Waals.
TMD.
Van der Waals.
Oh, van der Waals. Van der Waals. Yeah, okay. TMD, yes, BSE van der Waals heterostructure, driven like gallium nitride, BSE van der Waals heterostructure, and etc. So I'm sorry if I missed your presentation, but it seemed that you didn't mention such kind of material. Some of them are theoretically reported to have energy conversion efficiency higher than 99.9%, almost 20. So do you have any comment for this material as water splitting photocatalysts? Are they good for industrial scale? Please, Dr. Fatwa.
Yeah, thank you very much, Dr. Nugraha, for the question. Yeah, so I'm aware of these materials, although we don't really work on these materials in our institute. And of course, they have quite a bit of a promise, right? And the interesting thing I think about them is that the activity seems to, especially for molysulfide, the activity seems to be determined by the edge side. So if you have like, because this is a blade, so how do you say? Because of the flat nature, or like the layer by layer nature of this material, the edge of this, the basal and the edge, right? The edge side seems to be the most active sides of the material. So a lot of activities in the field have been directed towards increasing the coverage for the edge sides and decreasing the amount of basal plane. So we don't ourselves, we have not really done much on this. I think they could be interesting, but a lot of them are still much in an early development state. Some of them are more interesting than others. For example, like the combination with zinc oxide, I think is probably not very attractive because it's known to be highly unstable. It's hard to actually stabilize, and the band gap is also really large. But the other combinations or other new materials that comes within this class, I think could be pretty interesting. For example, MXenes, I think people have actually looked into this as well for carbon dioxide reduction, but it's still too early to know whether they're good for industrial scale. So I hope that answers the question.
Yes, okay. Thank you, Dr. Fatwa. I think I have the following question. Yeah, regarding the Dr. Nugraha question. So from your slide, I saw that in your group mainly focusing on the bismuth vanadate, right? Bismuth base. So, but I think I didn't see the doping for the bismuth vanadate. Your research, your group research, mostly on the compositing, like with the tungsten oxide base or other. Why you just focusing on the compositing or mixing the bismuth vanadate?
Thank you. So no, we did do doping. So we did. I think maybe I didn't show it as much, but this presentations. But yeah, we tried to composite it with sulfur, right, with higher concentration. But with
yes,
with doping, we tried using also slower concentration, and with molybdenum or tungsten, or even dope it with hydrogen. And that's in the relatively 10 to the 18, 10 to the 19 centimeter minus 3 concentration, and that does help for bismuth vanadate, but it can only help until a certain point. And people, I think all of the high performing bismuth vanadate that is reported have to combine a few of this strategy. Doping is one of them, and then combine it with the structuring or introducing the internal gradient. But we do doping, yes.
Okay. It's interesting, yeah, because previously I did this material development, but for another application, for the electrolyte for SOFC, solid oxide fuel cell.
Okay.
For the ionic conductive material, yeah, but it's similar, yeah. Yeah,
Is it good?
it can perform at the very low temperature. Yeah, but the problem,
Okay.
the electrode, we cannot find the proper electrode. The electrode good, the electrode we cannot find yet.
Okay. Okay.
Okay. I think it's very many common that I can discuss with you actually. Okay, we have to go to Dr. Bambang again, and then after that we go back to you.
Yep.
Okay, Dr. Bambang.
Yeah.
Yeah, there are several questions actually for you, but if there is still not yet any question from the floor from the participant, yeah, I can give you many questions actually.
Yeah.
Okay, Dr. Babang, what do you think about the fast charging status now in our country, or maybe in the global, in the world, the fast charging status, and how fast the charging is for the latest technology one? For the charging, for instance, for the electric vehicle, how fast it is now?
Yeah.
Please.
How fast is now?
Yeah.
Yeah. Type of lithium battery can fast charge by around 10 C. 10 C capacity. 10 capacity. But for the requirement for the fast charging battery, everyone want the active material of cathode can charge around 20 C. 20 C. Yes.
20 C.
But the
okay.
status, 20 C. Yeah. But the status of the station for the fast charging or station charging, the charging status is not so high, maybe around 5 C, because the more the station very careful for the fast charging, because the lithium battery can more fast the break of the the boom.
Yes, explode.
Explode.
Yeah, I think that's the problem due to the still in the liquid electrolyte, right?
Yeah.
Yeah.
Yeah. Therefore, in the slide is more than more factor of the fast charging, and the more states or more country develop the swap battery swap. Yes.
Okay. So the replacement, not charging.
Yeah, and the charging and the other plates. Yeah. And I take the new battery in the
replacement.
vehicle. Yeah, replacement.
Yeah, I think that's more visible. Okay, I did go back to Dr. Fatwa. Dr. Fatwa, this is a little bit about policy, not so technical. But I still many technical questions actually for you. Actually, still many. Okay,
I don't know.
We
I don't know if
have
I can
many time in here. We can finish until up to 1. No. 12:40.
Okay.
Dr. Fatwa, what your opinion about the big potential? We know that the big potential of solar energy should be huge for our country, for Indonesia, I mean, as the tropical and also in the equator line. So how did you see or suggest this solar energy, or specifically the water splitting, can be adopted for our government? Please.
So
now you ask the policy.
This is definitely outside of my expertise, and I don't know if I can actually offer. And I don't know how far this recording will go, right? So I don't really want to say something that it's going to shoot me back, right? But I'll share a little bit of my opinion, right?
Okay.
So as you said, the potential is of course pretty high, right? Solar energy, we don't have, although we're in the equatorial, we have a lot of sunshine, but it's not as high as in the desert, of course, desert area, but still it's pretty high. So if you can think, then Denmark or Germany or Sweden or Norway can actually tap on this solar energy with the amount of sunlight that we and they have, right? In Germany and also they in the Scandinavian countries have. I don't see why this is not a possibility or in Indonesia, right? We need to actually tackle that, even take care of that, use that even more. And the interesting thing about that is also it's very how do you say, it's suitable for our geographical conditions that we are actually distributed over many islands, right? And maybe the problem with one of the problem with energy is distribution, right? So we actually can when you actually have like a centralized production of energy, you then need to distribute it to various places, and that's probably fine up to a certain point. And if you go across the sea, for example, and whatnot, that becomes more challenging. And this is where I think solar energy or other types of renewable energy that we have, like the tidal waves, the wind, or whatever, can actually offer its advantage for addressing our challenge and as countries with thousands of islands. So this is something that we needs to go for, a decentralized way of producing energy that it can tackle various places. And in terms of water splitting, yes, it's of course, as a researcher in that field, I'm passionate about it, and I'd like to see it actually being developed more and used. But at this point, unfortunately, I think this is not if you want to have like a shorter term policy, this is not something that we need to focus on yet, because even it's still being developed in research. We can go for photovoltaics electrolyzers if you want to store the energy, but I would say even with the basic solar, just the penetrations of solar cell in our country, as far as I know, is not high enough. We do have quite ambitious target, as I see, but we're still behind that target. And if we fulfill that, and not only, especially focusing on regions where otherwise grid cannot reach, I think that's the biggest potential that we have, and something that we need to focus on. But I agree, there are many focus that we need to. There are many fields, or there are many aspects that the government need to look at, and I do hope that this is going to be one of them. I don't know. I try to answer it, try to be politically correct in giving a policy. That is outside of my expertise. So that's my.
That's very good. Yeah, diplomatically acceptable.
Thank you.
Now it's a little bit technical, Dr. Patwa.
Okay.
A little bit technical. So what do you think about the hematite base for the PC? Because in our country, in Indonesia, we have many bauxite. Yeah. So what your opinion about it, please?
Yeah. So yeah, hematite is, of course, it's one of the, when it came out, it's one of the dream material, right? Because it's actually basically iron oxide, right? Fe2O3, and it's rust. So you actually have it everywhere, and it's highly stable. So so I think somebody asked about stability in the chat. I can actually come to that also right now, that hematite has shown actually one of the most stable materials that we know. So we took a 1,000-hour test, not us, but our colleague in Porto, in one of our PEC demo consortium partner, took hematite, tested for 1,000 hours. That's several months of performance measurements. There's really zero decay or zero degradations on the material. So it's really really stable. Bismuth vanadate, there is not for us, but also there are other groups that showed that it also can be stabilized up to 1,000 hours. And that is, of course, the goal, right, to go even further. Now, going back to hematite, The problem with hematite, the band gap is good, band position is okay, stability is really good. The problem for about 20 years or so have been attributed to the poor charge transport property. So the hole or the diffusion, the carrier diffusion length has been mentioned to be very short. And therefore, people have done a lot of nanostructuring, and they can achieve now already the highest one. I think it's like six milliamps. So that's already half of the theoretical maximum. But recently, we're still working on a publication on that one. So we are collaborating with our colleagues at Technion, where we looked at the
Technion,
fundamental.
Israel?
Yeah, fundamental problem of hematite, and one of the main issue right now that we found is not only on this carrier diffusion, but it's actually better than expected. The carrier diffusion is better than expected, but the problem is in the photogeneration process itself. So there's a how do you say it? So it has a lot of absorption, but some of those absorption do not contribute to actually current. So we're still finalizing this and see if this is actually the case. But there is a hint that this could be a problem. And if that is indeed the case, the theoretical limit of hematite is no longer of what we can achieve with the band gap, right? So we can. There is some problem with that. We try to see it as well in the other materials if this is a general issue, but I'm afraid the verdict is still out, so I don't know whether that will still be. But yeah, otherwise it's a nice material. Yeah, but unfortunately it doesn't tick all the boxes. Basically, it doesn't tick all the.
I see. Thank you for a very insightful answer. I need to go back to Dr. Bambang.
Yeah.
Okay, Dr. Bambang, another question. So what do you think? So what we should pay attention more on the battery safety development, like on the BMS? What the technical that we have to overcome in order to make the battery is more safety? Please.
More safety.
Yes.
This is about the control
BMS.
of state of charge. Yeah.
Correct.
And state of it is small, but no this development of balancing.
Okay.
It is charging, charge balancing or discharge balancing. This. Yeah. No. And the new development is the control of the battery cell. Yeah, this you can one by one the BMS can see the battery is good work of no. Is the new development on the BMS. Maybe this is so that the battery can assure there is a safety on can ensure this is good work in the application like this.
Okay, thank you for the answer, Dr. Bambang. Maybe this is the last question for you because we have a limited time. This is not so technical, Dr. Bambang. This is your opinion about a little bit policy. Yeah. So what is your opinion about the big company, as you know, the Tesla, Hyundai, they want to invest to our country, right? For the battery industry. So what do your opinion, Pak? Please.
Your opinion. This is maybe good. And this is the big country. Is look on me.
Correct.
Of Hyundai, Toyota, and
Tesla.
Tesla, Lamborghini, and Ferrari.
Lamborghini. Okay.
Lamborghini and Ferrari. We make a plan to collaboration with Ferrari to make
Nice.
to make a electric vehicle like national vehicle with the type from Ferrari, and we want the battery from me because my battery is this kind different, especially different from the other battery, and we have the lifespan, we have the safety, and so on. Maybe we can the parable is the diameter parable. Comparable diameter comparable is maybe very good in the next future. I say.
Thank you, Dr. Bambang. Okay, I need go back to Dr. Fatwa, but this is not question, Dr. Fatwa. I need your closing statement. We will finish our session. Please give your closing statement. Please.
I don't know. Yeah. So my closing statement would be thank you very much for this nice and engaging discussion. And yeah, so I'm pretty happy with the way discussions goes and looking at the nice initiatives of this webinars. I think the pandemic actually has one of the good things that it has actually brought us is actually the nearness, right? So I've actually engaged with a lot more webinars this year that I could, if we don't have pandemic, right? So one of the nice things is that the scientific and also technological delivery have become easier, are more accessible to everyone. And I just hope that this will go forward further, right? In the spirit of collaborations and also openness of science and technology, we can continue to do that even beyond this pandemic period, right? And in terms of energy, and I think one of the things that if I look at the programs of this conference or the symposium, is that the final statement that I will say is that we can actually see how important material is in every aspects of our life, right? So we already see just in this session, we have the different applications in energy field, battery, catalytic or chemical transformations in my talk, but there are other topics that have already been discussed this morning, other applications, right? Superconductivity, ferroelectricity, and further on, right? Even going biomaterials and stuff. And I think this shows the richness of material science, and we need to further improve our collaborations, I think, within the field. With that, I thank you again, Dr. Denny, and also everyone and the organizers, and also if there are any further questions or discussions to me, please feel free to contact me or shoot me an email.
For sure, many. Thank you, Dr. Fatwa. Thank you, Dr. Bambang. And also thank you for previous our speaker, Professor Kawai and then Professor Andika. We have today learned a lot from all of them, from the ferroelectric material for the electronic material application. Oh yeah, photo session. Please turn on your video photo session before we finish.
Keynote, please. Maybe okay.
Yes, we already took the picture.
Finish?
Finish?
Okay.
Thank you.
Thank you again. So we will come back at the 13th at the 1 p.m. sharply. Thank you very much for your all of attention. That's all from me. Apologize for any shortcoming. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi.
Nanti jangan bosan-bosan ya kalau kami email Pak ya. Banyak sekali inline-nya riset tentang foto PEC yang kami lakukan juga Pak di sini.
Iya, siap Kang Denny.
Iya.
Tahun lalu kan kita ketemu di itu ya, di CKD ya? Ya, siap.
Iya, ini juga kalau nggak pandemik sebetulnya saya mau apply juga ke sana, cuman ya gara-gara ini kami jadi pending dulu.
Iya.
Banyak banget nih kami mau belajar ke Helmholtz nih ke Berlin.
Aduh, mudah-mudahan bisa. Iya, mudah-mudahan segera nih vaksinnya bisa dirilis. Jadi kita bisa.
Amin, ya.
Masih
berarti jam berapa sekarang di sana? Jam 6 sekarang?
Ya, jam 7 kurang seperempat ya.
7 kurang seperempat.
Iya.
Gimana Pak Fatwa?
Enggak, sama siapa namanya? Waktu itu Sigit. Masih ini sama Sigit? Enggak.
Sigit
ya sama Jovan.
Masih lah. Bukan saudaranya Mas Fatwa, masih kontak lah.
Ya, loh.
Enggak. Canda.
Iya.
Itu juga ada ya, yang di Komplek Dikbud ya, saudaranya Mas Fatwa ya? Yang di Jakarta Barat, di Tomang itu ya. Aduh, siapa namanya? Saya lupa. Orangnya tinggi-tinggi juga. Udah lama sekali aku nggak ketemu sama dia.
Halo?
Ayahnya dosen hukum. Tapi udah pensiun.
Siapa ya?
Saya lihat soalnya di Facebook sama-sama friend kita. Dengan orang yang sama. Bilang, ya ini lihat ini kayaknya Pak Hifni bapaknya. Pak Hifni pernah cerita ini, saya ada saudara di Jerman gini gitu ya. Oh gitu.
Siapa ya?
Ini Pak Fatwa.
Saya
Oke, nggak apa-apa.
Saya nggak ingat, tadi sampai saya cari. Pokoknya yang friend in common lah kita ya.
Lo tinggal di Komplek Diknas di Tomang.
Oh, oke. Coba nanti saya cari.
Oke lah, nggak apa-apa. Terima kasih banyak Pak Fatwa.
Sama-sama Denny ya. Saya izin off dulu, saya mau siap-siap terus berangkat. Maaf banget nggak gabung ke paralel. Besok masih ada juga kan ya?
Masih ada, silakan kalau mau gabung nanti kami kasih linknya. Udah ada linknya kan, boleh.
Sudah ada. Ya, sudah ada. Ya. Oke. Terima kasih banyak ya Pak Denny. Assalamualaikum.
Waalaikumsalam warahmatullahi.
Terima kasih Mbak Nono. Ya, terima kasih.
Okay, maybe just for the important notes that to all participants, please make sure your Zoom is updated to the latest version in order to get the breakout room service. So we will open 2 rooms for the parallel session from now. You can join from room A and room B. Please join based on your program. And then if you have problem, please contact the Ismm 2020 main host so we can directly forward you to your room. Thank you. Assalamualaikum, alhamdulillah, panel sessionnya kelar. Aku akan ketar-ketir juga ya.
Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya. Selain itu, LIPI juga mengelola data dan timbangan ilmiah dalam rangka konservasi keanekaragaman hayati. Menerbitkan tanda pengenal unik publikasi ilmiah terbitan berkala, membuat repositori ilmiah skala nasional, dan memiliki kewenangan sebagai pembina Jabatan Fungsional Peneliti Nasional, serta melaksanakan proses pengukuhan profesor riset di Indonesia. Kini, juga mendukung percepatan penanganan COVID-19, baik melalui riset berupa kajian maupun produk, maupun pengembangan SDM melalui program Indonesia Memanggil. Untuk mendukung riset, LIPI memiliki 5 kebun raya sebagai pusat konservasi flora ex situ. 2 museum yang memiliki koleksi flora, fauna, dan kesejarahan alam Indonesia, Indonesia Culture Collection yang menyimpan koleksi mikroorganisme terbesar di Indonesia, infrastruktur riset strategis, dan beberapa pusat berskala internasional, yaitu Asia Pacific Center for Eco-Hydrology atau APCE. LIPI telah menghasilkan hasil riset yang berkualitas dan bermanfaat bagi masyarakat, meliputi keanekaragaman hayati, lingkungan dan maritim, ketahanan pangan, pertanian, dan peternakan, kesehatan dan farmasi, material maju, energi, teknologi, informasi dan komunikasi, pertahanan dan keamanan, dinamika sosial, kemanusiaan dan kebudayaan, kebencanaan, inovasi teknologi dan pendayagunaan iptek, pelayanan, pengujian dan pembinaan ilmiah, serta peningkatan kualitas SDM iptek. Kerjasama keilmuan LIPI dalam negeri meliputi kerjasama penelitian, lisensi teknologi, pengembangan, aplikasi dan komersialisasi hasil penelitian, kerjasama non-penelitian, dan konsultasi kepakaran LIPI. Sedangkan kerjasama luar negeri, LIPI melakukan joint research, workshop, pertukaran peneliti dan beasiswa mancanegara, selain aktif menjadi anggota dan focal point di berbagai organisasi internasional. Melalui kolaborasi bersinergi, menghasilkan riset yang berkualitas, LIPI terus memberikan manfaat nyata, kontribusi berarti, dan turut mewujudkan cita dan asa membangun negeri kita tercinta, Indonesia. Berawal dari cita dan asa untuk membangun negeri, memberikan segenap rasa dan tenaga untuk menghasilkan pemikiran terbaik bagi negeri tercinta, kami ada untuk Indonesia. Mewujudkan diri sebagai Lembaga Ilmu Pengetahuan Indonesia yang andal, profesional, inovatif, dan berintegritas dalam pelayanan untuk mewujudkan visi Presiden dan Wakil Presiden. Indonesia Maju yang berdaulat, mandiri, dan berkepribadian, berlandaskan gotong royong. LIPI memiliki berbagai pusat penelitian tersebar di seluruh Indonesia yang berada di bawah kepala LIPI, Deputi Ilmu Pengetahuan Hayati, Deputi Ilmu Pengetahuan Kebumian, Deputi Ilmu Pengetahuan Teknik, Deputi Ilmu Pengetahuan Sosial dan Kemanusiaan, Deputi Jasa Ilmiah dan SDM Pendukung Iptek di bawah Sekretariat Utama LIPI. LIPI berperan dalam proses penyusunan dan kelahiran berbagai regulasi dan kebijakan pemerintah terkait aspek ekonomi, politik, sosial, dan budaya.
Oke, saya mulai. Bismillahirrahmanirrahim. Good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to welcome you all to this parallel session in International Seminar on Metallurgy on Material 2020. Before we begin, let me introduce myself. My name is Latifah Hanum Lalasari. I am a moderator in this session. Ladies and gentlemen, in this opportunity, we shall listen presentation from 7 researchers: Dr. Ruji Subagja, Dr. Erik Prasetyo, Mrs. Farisa Yunita, Mrs. Enggi Simatupang, Mr. Eko Sulistiono, Dr. Sudibyo, Mr. Fatan Bahku. I believe shall increase our knowledge regarding the topic of extractive metallurgy, metal forming, and steel metal group. Ladies and gentlemen, before we start the presentation, I would like to explain and remind the rule of presentation. 1. The oral presentation will be allocated 15 minutes, include the presentation and discussion, question and answer session. 2. Presenter who experience technical problem during their presentation, they can postpone their presentation and move it the end of session. 3. During the parallel session, our presenter should turn off the video feature. The last, presenter are not allowed to leave the breakout room during the session because there will be photo session the end of session. Okay, now we could start a presentation. The first presenter, Dr. Rudy Subagja, entitled Copper Dissolution into the Aqueous Sulfuric Acid Solution from Printed Circuit Board Waste Slab. Dr. Rudy Subagja, you want to presentasi live video? Dr. Rudy Subagja, you ready for live presentation? Dr. Rudy Subagja,
I want to host to unmute speaker Rudi Subagja, Dr. Rudi Subagja.
Okay, can you hear me?
Yes.
Can you hear me? Okay.
Okay, clear. Okay.
And then,
Dr.
Yeah, okay. And then I have already sent the material yesterday. And then, who will show the material? Should I show the material or the committee will be presented? We will be show the material. Bu Latifa.
Yeah. You share screen PPT. You want last presentation?
Okay.
Video. Please host share video presentation from Dr. Rudi Subagja. The ladies and gentlemen, Dr. Rudi Subagja is senior researcher from Research Center for Metallurgy and Material. We have many experience about research about extractive metallurgy.
Bu Latifa, can you see the material? Hello.
No, not yet.
Not
Hello,
yet.
not yet, Doctor.
Oh. Okay.
I see Dr. Rudi Subagja.
Okay, thank you. Okay, shall we start? Okay, thank you very much, Ibu Latifa, the moderator, for giving me the opportunity to present our research results about the copper dissolution into the aqueous sulfuric acid solution from the printer circuit board waste sludge. Okay, next slide, please. Next slide, please. Okay. The use of electronic equipment has increased along with the increasing of human properties. This condition has led to the increased production of waste electronic material, including waste printed circuit or PCB, which is one of the important components to make the electronic equipment. Every year, I think about 20 to 50 million tons of electronic waste are generated in the world. Next slide, please. The generated sludge waste from PCB manufacturing is generally contain various types of metals such as copper, iron, zinc, aluminum, and the other element metal. Therefore, PCB sludge is classified as hazard waste material. Heavy metal material present in sludge has the potential to generate a high toxic to effect on the living organism. The excessive of copper content in the human body contribute to disorder of the liver, digestive, and cardiovascular system. Therefore, the generated waste from the PCB manufacturing process should be controlled properly to prevent environmental damage that can endanger human health. Next, please. Next slide, please. The potential method to overcome the problem of PCB waste sludge is by the metal extraction to recover the metal element containing in the waste. This method, besides, can produce heavy metal content in the sludge. this method, besides can reduce heavy metal content in the sludge, it can also make waste sludge PCB to become potential resources for metal production. PCB waste sludge material become important metal resources when the demand of metal increases while the availability of mineral resources decreases. In the metallurgical industry, this gap creates a problem that is the metallurgy industry must either to use lower grade ore or secondary material from industrial waste. This situation will be challenged for the practitioner in the field of extraction metallurgy to develop urban mining to process the extract metal from secondary resources such as copper metal extraction from electronics waste. Next slide, please. Next slide, please. Okay. A common way to recover valuable metal from electronic waste is by pyrometallurgical method, hydrometallurgical method, or biometallurgical method. Next slide. In pyrometallurgy process, sludge is mixed with flux and then melt to separate copper from iron. The copper produced in the fire is then purified by fire refining and electrometallurgy to produce pure copper. But the problem in this process is that the mass of copper go to the slag, and then the pyrometallurgy process need a large amount of energy. Next slide. Another alternative method to recover valuable metal from electronic waste is by hydrometallurgical method. Various types of acid have been used to extract copper, such as hydrochloric acid, perchloric acid, nitric acid, or sulfuric acid, organic acid, and so on. In this process, PCB waste sludge is leaching by acid. The leaching solution is then sent for the purification, and then after that is the purified solution is sent to the electrowinning tank to produce pure copper metal. Next slide. Next slide, please. In order to investigate the characteristic of copper and iron during acid dissolution process, in current study, copper dissolution process from PCB phase sludge into the sulfuric acid solution is carried out with the objective to observe the characteristic of copper and iron dissolution during the dissolution process in sulfuric acid solution. Next slide. This slide shows the chemical composition of waste used in experiment. The waste is obtained from the industrial area at Bekasi, at West Java, Indonesia. And then the color of waste is brown. The waste has a water content about 70% of water. And previous. This is the results of the analysis by Sam. From this data show that the dominant element in the sludge is copper oxide and iron oxide. The other element is nickel, and then magnesium, aluminum, and then copper, zinc, but the quantity is small. Okay, next slide. This is the equipment used for the experiment. The equipment is consists of 1 liter of vessel, glass vessel, and then the reactor was covered with heating element, temperature control to keep the reaction temperature constant. This reactor also equipped with stirrer, driven by motor. And then for every experiment, 500 milliliter of sulfuric acid is put into the glass reactor. The solution was then heated using electric heater until certain temperature. After the certain temperature was reached, the wet PCB waste was added into the sulfuric acid solution in the glass reactor. The mix of PCB waste sludge and acid was then stirred and at the certain rotational speed in the glass reactor. And then at certain period of time, the liquid sample was taken out from the reactor, and then it was analyzed by ICP. Next slide. The percent of dissolved copper and iron were calculated by this formula. The percent of dissolved copper is calculated by comparing the weight of dissolved copper into the acid with initial copper content in the sludge. In the same calculation, is also used to calculate the percent dissolution percent for the iron. Next slide, please. This next slide. Okay. This slide show the characteristic of sludge during by scanning electron microscope. Yeah, we show that the PCB sludge contains some element: carbon, oxygen, magnesium, aluminum, silicon, sulfur, chlorine, calcium, iron, copper, and barium, where copper and iron become the dominant element. Next slide. This slide shows the potential pH diagram for the copper and iron system. From this potential diagram, it is shown that that copper iron in the wet slides is most
sorry, Dr. Rudy Subagja, you have 2 minutes.
Okay. Okay. Next slide. Yeah, this is the actually version of sludge before leaching. Yeah, and then next, this is the reaction taking place during the dissolution process. Yeah, next, yeah, this is the result of experiment effect of sulfuric acid concentration on copper and iron dissolution. From this figure, it is shown that copper is more easy to dissolve than iron. Okay, next. This is the effect of a solid percent on the copper and iron dissolution. Yeah, this figure also show that the copper dissolution is higher than iron dissolution, because I think because of the solubility product of copper is higher than the solubility product of iron. Okay, next slide. This is the effect of agitation speed on the copper and iron dissolution. From this figure, okay, it shows that when the agitation speed were increased from 50 to 200, the copper and iron dissolution increased, but the further increasing of agitation speed did not give any significant effect for the copper and iron dissolution. Okay, next slide. This is the effect of temperature on copper iron dissolution. Yeah. From this data, it is shown that when the temperature increases from 45 to 70 degrees C, both of copper and iron, in the dissolution of copper and iron increases. Yeah. And then from this data, we can see that the dissolution copper is higher than iron dissolution. And then at 70 degrees, yeah, I think most of copper dissolve into the acid solution. Okay, next slide, please.
Please, presentasi is very quickly.
Okay, I think go to the yeah. This is all the characteristic of the slides. Yeah, after dissolution from this data. Okay, yeah. Okay, from this data we can see that the copper has already dissolved into the solution. Yeah, before leaching we can see the intensities of copper, and after leaching the intensity of copper is lower. So I think most of copper has already dissolved into the acid solution here. Okay, next slide. Yes, the conclusion, yeah, the experiment to dissolve copper into the iron from PCB sludge has been conducted, and then from the result of experiment, it is concluded that in experiment condition, copper was more soluble in acid solution. Sorry, I can see this figure. Okay. In experiment, copper was more soluble in aqueous acid solution than iron due to copper has higher solubility constant than iron solubility constant. An increase in sulfuric acid concentration from up to 5% causes the percent dissolution of copper and iron increases, but further increase in sulfuric acid concentration up to 20% does not give any significant effect on copper and iron dissolution. An increase in solid state percent in the solution from 5% to 20% causes the amount of dissolved copper and iron tend to decrease. And then increasing the agitation from 50 to 200, causing slight increase in amount of dissolved copper and iron. However, further increase in agitation speed up to 300 RPM did not give any significant effect on the copper and iron dissolution process. The dissolution.
Sorry, Dr. Rudy, you have not time to stop.
I think this is
no. We discussion because the time is 50 minutes.
Okay.
Okay. Ladies and gentlemen, we come to question and answer this discussion. Any question for Dr. Rudy Subagja? Not yet. Okay. Maybe I have a question. What is the selectivity value of copper compared to iron? Because I see the result copper and iron in combine. And what the next step of research to separate?
Can you repeat the question? Can you repeat the question, please?
What is the selectivity?
Selectivity.
Yes. What is the selectivity value of copper compared to iron?
Yes, I think the selectivity of copper and iron, it depends on the pH of the solution. Yeah, because maybe at the pH lower than 3, we can make iron to be still in this undissolved, yeah, undissolved, and then at the pH copper has already go to the acid solution. Yeah, so I think we can selectively we can make copper to become more soluble than iron by controlling PS or the potential of the solution. Yeah. So I think that's my question, my answer. Okay. Any question?
Any question for audience? Not yet. I think enough, Dr. Rudi Subagio.
Okay, thank you
because
very much.
the time is very late. Okay, it is difficult for presenter because the presenter we have 50 minutes for presentation and discussion. Okay, we give applause Dr. Rudi Subagio.
Thank you.
The presentation is very interesting. Thank you. The next presenter is Dr. Eric Prasetyo, entitled Oxidative Fusion and Alkaline Leaching for Manganese Extraction from Low-Grade Silicate Ore. Eric Prasetyo, you
Yes,
here?
Assalamualaikum.
Okay.
Assalamualaikum. Hello?
Waalaikumsalam warahmatullahi wabarakatuh.
Oh, thank you.
Waalaikumsalam warahmatullahi
It means that
wabarakatuh.
you all can hear me. Thank you very much. Maybe I like to share.
Please, your presentation is very clear.
Can you share my videos? Okay. Everybody can see that?
Yes.
Okay. I prefer to do the video presentation, so please enjoy.
Dr. Eric Prasetyo, I don't hear your presentation.
Oh,
Video.
really? I'm sorry. Can you play my videos from there? I think I already share my screen here.
Yes.
You still
Yes.
didn't get it?
But I don't hear your presentation. Maybe can you live presentation?
Oh, okay, no problem. Okay.
Sorry.
I work on the extraction of. Okay, thank you very much. But there's still no sound there. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the chance to present our work on the extraction of low-grade manganese using oxidative fusion and alkaline leaching. My name is Eric Prasetyo from Indonesian Institute of Sciences. I'm representing our team and our college from the University of Lampung, Department of Chemistry. A little bit background why we have interest in this topic. First is compared to other ore minerals such as manganese oxide or pyrolusite or rhodochrosite manganese carbonate, manganese silicate is barely exploited in the mineral processing. Generally speaking, hydrometallurgy alone is not powerful enough to recover manganese from this type of ore due to the strong bonding between manganese and silicate in the structure, in the mineral structure. Maybe hydrogen fluoride alone has the chance to break this bonding. However, the cost of the reagent and environmental concern make this approach by using hydrofluoric acid is a little bit out of the question. And how about the pyrometallurgy? This method is practically only for high-grade manganese ore since it requires high energy input, and for low-grade ore, the energy input is not well balanced with the output obtained. Therefore, we propose to incorporate both approach, pyro and hydrometallurgy, in our research. In this case, is fusion. Fusion use much lower temperature compared to usual metallurgical method like smelting. And fusion, especially the alkaline, could break down manganese silicon bonding and transform the manganese silicate base into soluble sodium manganate based on this reaction. Further, since the fusion product is soluble base, sodium manganate, the manganese could be recovered by leaching process in mild condition without addition of the aggressive chemicals. So the objective of our research first to test the efficacy of the alkaline fusion and leaching to recover manganese from low-grade manganese silicate ore, which parameters include mass ratio between sodium hydroxide as fusion agent and manganese ore, fusion temperature, fusion time, pulp density, and also the leaching time. In this study, we use the raw materials, manganese ore from the Tanggamus Regency in Lampung province, based on the XRD analysis, report analysis. The base of the ore consists of the manganese garnet, about 21%. Manganese garnet is the manganese silicate ore also. And then the pyrox manganate as the main of manganese silicate ore in the raw material, about 50%, while the rest is silicon oxide or silica, about 64%. Typically, the fusion and leaching test about 0.5 gram of manganese ore mixed with sodium hydroxide as fusion agent in nickel crucible, and then introduced to the muffle furnace. After the fusion completed, the mixture was mixed with sodium hydroxide solution to leach out the manganese as sodium manganate. And the content of manganese in the leachate was determined using atomic absorption spectrophotometer. And finally, the recovery of manganese was calculated using mass balance. Next is result. First is the relationship between mass ratio of sodium hydroxide as a fusion agent and manganese silicate or to the manganese recovery. The constant variable in this test were the fusion temperature, 500 degrees, fusion time 1 hour, leaching pulp density about 7% using sodium hydroxide 2 molars, and lastly the leaching time about 30 minutes. The results shown in the first figure that the mass ratio between sodium hydroxide and manganese ore, one value is considered as the optimum mass ratio since the increasing mass ratio did not significantly increase the manganese recovery. In the second figure, we have graph showing the effect of fusion temperature to the manganese recovery. The constant variable in this case were mass ratio 1, fusion time 1 hour, leaching pulp density 7%, sodium hydroxide concentration 2 molar, and leaching time 30 minutes. Based on the figure, 500 degrees Celsius was considered as the optimum fusion temperature. Next is the effect of fusion time. The result in figure 3 clearly showed that 30 minutes was sufficient to attain maximum recovery, which is about 60%. First, leaching parameter optimized was the leaching pulp density. To study the effect, mass ratio, fusion time, and fusion temperature, sodium hydroxide concentration as recipient, and leaching time were set constant. The result in figure 4 clearly showed that the optimum fault density was about 7%. Next, the leaching parameter optimized is the leaching time. The figures show that the longer leaching time decreased the manganese recovery. This is probably due to the disproportionation reaction of manganate into permanganate and manganese dioxide precipitate, which could decrease the manganese content in the leachate and decrease the manganese recovery in the calculation. Finally, what we can conclude from the studies, first, the alkaline fusion and leaching successfully recovered manganese from the manganese silicate ore. Next, during the fusion, the insoluble manganese silicate was transformed into the soluble manganate, which is amenable for the hydrometallurgical processing. And next, the optimum condition based on the study, the ratio between fusion agent and ore about 1, fusion temperature about 500 degrees, fusion time 1 hour, leaching pulp density 7% using sodium hydroxide 2 molar, and the leaching time about 5 minutes. The study revealed that the shorter leaching time is preferable in order to prevent the formation of the manganese oxide precipitate. I think that's all for our presentation. Thank you very much for your kind attention and have a nice day, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, we continue discussion. Any question? Maybe ladies and gentlemen have any question? Please mention your name and institution. Not yet? Okay, Dr. Eric Prasetyo.
Yes.
I have a question. We're waiting the floor to ask you.
Sure.
Okay. Okay. Where you choose fusion temperature at 500 Celsius degree? Do you analyze TGDTA?
No, actually, why we choose the range between 300 and 700? Because we considered that the sodium hydroxide would melt around about 400 degrees. So in order the fusion agent to be effective, it has to end the melting pace. That's why we choose the range in our study between 300 and 700. And it reveals about 500 as the best temperature for that.
Can I see your SRD analysis about fusion product?
About the XRD analysis, I don't have it because I get it as the secondary data from our previous research. Research by Mr. Fajar Nurjaman in 2019. So there is already, it's already published the data, but I don't have the reference right now. I'm sorry.
What vessel do you want to create?
Mostly is the manganese silicate, like I said in my presentation, manganese silicate, Esperox manganate, and manganese garnet. So both of them are manganese silicates mineral.
Because I think it need SRD analysis to appear in your presentation.
Yeah,
because
sure.
the phase is very important to extract your manganese. Okay, the next, why you choose mass ratio of sodium hydroxide to mangan, I see you choose 1 to 4.
Oh, you mean the range during the studies why I choose 1 and 4? That's the question, right?
Yes.
Okay.
Maybe you can explain you choose
I'm sorry.
the ratio.
Okay, why we choose mass ratio between 0? 0 is the control. I mean, we have to make certain that sodium hydroxide has effect to the fusion process. So why we choose 0 as the control experiment. And then we choose between 1 and 4 because based on the reaction, we calculate the stoichiometry between ore, manganese silicate, and sodium hydroxide. If the recovery would be 100%, maybe the mole ratio would be, let me say, 1 to 2. So we convert the mole ratio into the mass ratio.
Any question for audience? Okay, Mr. and Mrs. Annie, you have question? Miss Annie, maybe you.
Oh, from Miss Annie. Why do you use the same alkali for fission and for leaching? Okay. Why we are using the alkaline for the leaching, not the acid leaching? Because if we use the acid leaching, the manganese would be precipitate as the manganese oxide. So that's why we choose alkaline leaching rather than acidic leaching.
Any question? I think enough because time up. Okay, thank you your presentation, Dr. Eric Prasetya.
Thank you very much, everyone.
Presentation is very interesting for us. Okay, we give applause for Dr. Eric Prasetya. The next presenter is Mrs. Farisa Yunita from Research Center for Metallurgy and Material. The title nickel leaching from laterite ore by combination of organic and secret acid. The time is yours.
Great, thank you so much, Dr. Latifa. I hope the video works.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Fariza Yunita from Research Center for Metallurgy and Materials, Indonesian Institute of Sciences. Today, I will present my paper, Nickel Leaching from Laterite Ores by Combination of Organic and Sulfuric Acid. Outline for this presentation: introduction, materials and method, results and discussion, and conclusions. Nickel is an important metal with major uses in stainless steel, nickel-based alloy, casting and alloy steel, electroplating, battery, and other uses. From this graph, we can see that stainless steel demand increased 5% annually. Energy Consultant predicts that nickel demand for electric vehicles will increase from 128 kilotons in 2019 to 265 kilotons in 2025. There are two nickel deposits in the world, sulfide and laterite. Currently, most nickel production comes from sulfide ores, despite laterite ore more abundant. However, owing to the decreasing of nickel sulfide ores, there will be an increasing amount of nickel laterite ore being extracted to meet increasing nickel future demand. The pyrometallurgical route generally processes saprolite into ferronickel or nickel sulfide metal. However, hydrometallurgical process is more preferable for treating low-grade nickel laterite ore due to its lower cost and its ability to separate cobalt as byproduct. High-pressure acid leaching process provides high recoveries of nickel and cobalt, low iron dissolution, but requires high capital expenditure for autoclaves, high energy consumption, and high maintenance costs. Atmospheric leaching process has lower cost but produces pregnant leach solution with significant iron concentration. It would be beneficial for further purification process if we can leach nickel selectively. Different types of acid have been studied for laterite atmospheric leaching. Sulfuric acid is less expensive and less corrosive, but hydrochloric acid and nitric acids can be regenerated. Recently, organic acid leaching has been attractive due to its advantages such as more environmentally friendly and lower cost than inorganic acid. Saprolite and limonite ore from Pomala, Southeast Sulawesi, Indonesia were crushed and ground using jaw crusher and ball mill. Concentration of nickel and other elements in the saprolite and limonite ores were analyzed using X-ray fluorescence. Leaching processes were performed under atmospheric pressure using glass reactor, which placed on hot plate stirrer. A condenser was attached above the reactor to minimize evaporation. For each experiment, acid solution was heated until 95 Celsius degree. Ore was added with 5% solid liquid ratio and be stirred at 200 RPM for 480 minutes. After the leaching process, the filtrate was separated from the residue. Pregnant leach solution were analyzed using atomic absorption spectroscopy. Based on the XRF analysis, limonite ore has higher iron content, while saprolite ores has higher magnesium content. The nickel content in saprolite ore is slightly higher than the limonite ore, or it can be concluded that the saprolite ore is a low-grade saprolite ore. These pictures show metal extraction from limonite by sulfuric acid, with this figure for nickel extraction, this is for iron dissolution, and this is for magnesium dissolution. And these pictures show metal extraction from saprolite ore by sulfuric acid. This is for nickel extraction, and this is for iron dissolution, and this is for magnesium dissolution. It also can be seen that nickel extraction from limonite ore is lower than saprolite ore. As goethite is the predominant mineral in limonite ore and nickel is mainly found in goethite, nickel dissolves with iron simultaneously from the mineral goethite. These pictures show metal extraction from limonite by citric acid. This is for nickel extraction, this is for iron dissolution, and this is for magnesium dissolution. And these pictures show metal extraction from saprolite ore by citric acid. This is for nickel extraction, this is for iron dissolution, and this is for magnesium dissolution. Organic acids dissolve metals through acidolysis and complexolysis process. Acidolysis is replacement of metal ions with hydrogen ions, while complexolysis is the formation of metal complex and metal chelates. Lower nickel extraction from limonite compared to saprolite shows citric acid inability to react with goethite. This metal extraction from limonite by combination of citric acid and sulfuric acid. This is for nickel extraction, this is for iron dissolution, and this is for magnesium dissolution. Combination that gives the highest nickel extraction for limonite ore is 0.5 citric acid and 2 molar sulfuric acid. It gives 73 nickel extracted from the ore. This picture shows show metal extraction from saprolite by combination of citric acid and sulfuric acid. This is for nickel extraction, this is for iron dissolution, and this is for magnesium dissolution. Combination that gives the highest nickel extraction from saprolite ore is 2 molar of citric acid and 0.5 molar sulfuric acid. It gives 91% nickel extracted from the ore. Previous study concluded that there is synergistic effect between citric and sulfuric acids. However, this research shows that the addition of sulfuric acid has a significant effect on the extraction of iron and magnesium. Metal dissolution from laterite is a heterogeneous reaction because it involves more than one phase, solid and liquid. Nickel laterite ore is assumed to be spherical, and its particle size does not change with leaching reaction. 3 synchronous core models are diffusion through gas film control, diffusion through ash layer of unreacted core control, and chemical reaction control. Experiments for leaching kinetic study were using best conditions that give the highest nickel dissolution. It's for limonite ore is a combination of 0.5 citric acid and 2 molar sulfuric acid. This figure shows that the reaction rate controlled by diffusion through ash layer of unreacted core gives straight fit for nickel leaching from limonite ore. Experiments for leaching kinetic study for saprolite ore using combination of 2 molar citric acid and 0.5 molar sulfuric acid. These pictures show that reaction rate controlled by the chemical reaction gives straight fit line for nickel leaching from saprolite ore. By plotting the rate constant and temperature using Arrhenius law, activation energy was determined. Activation energy of nickel dissolution from limonite and saprolite are 11.47 kilojoule per mole and 102.36 kilojoule per mole respectively. Generally, the activation energy for diffusion control is lower than 20 kilojoule per mole, and for chemical control is greater than 40 kilojoule per mole. The results obtained in this research show that there is synergistic effect between citric and sulfuric acids to optimize nickel dissolution from laterite ore. The highest nickel dissolution using combination of 0.5 citric acid and 2 molar sulfuric acid for limonite ore, and combination of 2 molar citric acid and 0.5 molar sulfuric acid for saprolite ore are more than 73% and 91% respectively. The leaching kinetic study shows that nickel extraction were controlled by diffusion for limonite and controlled by chemical reaction for saprolite. Activation energies of nickel dissolution from limonite and saprolite are 11.47 and 102.36 kilojoule per mole respectively. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Mrs. Farisa Yunita, about your presentation. We continue to discussion. Any question? Maybe Dr. Rudy Subagja, Dr. Eric, you have a question about Ms. Farisa?
Yes, I have questions.
Okay. Please your name and institution.
My name is Eric Prasetyo from LIPI. To Ms. Farisa, thank you very much. The result is very interesting because you can process the saprolite ore with very low sulfuric acid concentrations. And my question first, why the nickel recovery is much lower in the limonite, about 70% if I'm not mistaken, compared to the saprolite about 90%. And my second question is, you said that there is synergist effect between citric acid and sulfuric acid. Which one between sulfuric and citric acid has more influence in the leaching process? That's my question. Thank you very much.
Okay, thank you. Maybe Mrs. Farisa, you can answer about it.
Thank you so much for the question. For the first question, I have explained before that in lemonade ore, the predominant mineral is goethite, which is contains iron, and nickel is mainly found in goethite. So nickel dissolves simultaneously with iron, and it makes more difficult to leach than from saprolite ore. That's for the first question. And for the second question, I think the nickel extracted is the extraction, the leaching process is more sulfuric acid is more has contribution, but citric acid has effect to lower the iron and magnesium dissolution, so it can be more selective. Thank you.
Thank you. May I ask more?
Any questions? Maybe I have one question because still 1 minute again. Please explain why nickel dissolution by organic and sulfuric acid from saprolite is higher than limonite. Maybe you can explain.
Sorry, the saprolite is higher than limonite.
Yes.
That's the same question as before, because the mineral that form the limonite and saprolite is different. Limonite is predominantly with goethite, so it's more difficult to leach than in saprolite ore.
Different mineral. Okay, I think time is up. Thank you, Mrs. Farisa, about your presentation. Your presentation is interesting. Okay, we give applause for Dr. Farisa. Oh, no, I see Dr. Farisa. I have you quit to Dr. Okay, the next presenter, Dr. Sudibyo, entitled Cobalt Recovery from the Slag of Nickel Pig Iron using tubular electrode in the electrowinning process. Okay, Dr. Sudibyo, you want presentasi by video or live?
Using video, okay.
Okay.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sudibyo from Research Unit for Mineral Technology, LIPI, Lampung. Today I will present my paper with title Cobalt Recovery from the Slag of Nickel Pig Iron using tubular electrode in the electrowinning process. Laterite nickel ore is processed using pyrometallurgy method to produce nickel pig iron as a main product and slag as byproduct. The select is toxic solid waste with contain cobalt, nickel, ferrum, silica, and etc. Cobalt metal is more valuable than nickel, and cobalt can be recovered using solvent extraction method. From solvent extraction method, we can get the cobalt metal using electrowinning process. To increase the performance of electrowinning process, we can use tubular electrode. In this work, we use tubular electrode and we optimize the process using Taguchi design of experiment. Research methodology. The first, select of little big iron. We select of little big iron was cleaned, become a powder, then bleached in sulfuric acid, and then we recover the cobalt using solvent extraction process using percetic acid, and the second step of solvent extraction using cyanide, and then stripping process to get the cobalt from organic solution to aqueous solution. After that, we can perform the metal electrowinning, and the cobalt will attach in negative electrode. This is electrowinning using tubular electrode. We use graphite as an anode, and cathode is aluminum. To control the temperature, we use heater, and to control the voltage, we use multitester using voltmeter, and this is design of experiment using Taguchi. We have 9 run and 3 level and 4 parameter. The first parameter is voltage, and second parameter is time, and the third parameter is temperature, and the last is boric acid. And this is the percent of cobalt recovery from each experiment. Research and discussion using Taguchi analysis, larger the better. We can get this graph, the effect of time operation in the electrowinning process. From this picture, we can see that the optimum condition of time operation is at 2 hours. After 2 hours, we get more alcohol deposit, but many impurities attached in the negative electrode. And since the effect of voltage in the electrowinning process, we can see that the increase of voltage will increase the cobalt recovery, and the optimum condition is at 5 volt. And since the effect of additive electrolyte in the electrowinning process, we use boric acid as an additive. Boric acid has a function to avoid local pH increase, which caused by hydrogen evolution reaction. And boric acid also this as a function as a buffer in the solution, and the electrode deposit become more pure from impurities. However, if we add more of boric acid, the value, the cobalt recovery is decreased because the high concentration of boric acid will increase the viscosity of electrolyte. The increase of viscosity of electrolyte will decrease the mass transport in the electrochemical reaction, hence the cobalt recovery become smaller. And since the effect temperature in the electrolytic process, the increase of temperature will increase the cobalt recovery, but at the 60 degrees Celsius, the cobalt recovery will decrease because at the high temperature, the electrochemical alcohol become unstable and produce more hydrogen evolution. This will decrease the cobalt recovery. And see the result of Ism analysis using Taguchi method. From this table, we can get the value of delta and the range of each parameter. The highest value of delta indicates the most influence parameter. The most influence parameter in electrolytic process, the first is time compression, and the second is voltage, and the third is boric acid, and the last is temperature. And we also doing the experiment using optimum condition, and we can get the cobalt recovery was 72.79%. Conclusion: the cobalt recovery from NPI slag was successfully analyzed and studied using Taguchi method. From the result of the analysis using Taguchi method, the optimum condition were obtained using boric acid of 0.5 molar, 5 volt of voltage, and 2 hours of time operation, and 50 degrees Celsius of temperature. At the optimum condition, we can get the cobalt recovery at the voltage was 72.79%. Thank you.
Okay, thank you. Your presentation, Dr. Sudibyo. We continue discussion. Any question for audience?
Yes.
Okay, thank you, Dr. Rudi Subagja.
Okay, thank you very much, Ibu Moderator. I have the question for Pak Sudibyo. Yeah, I have to know about the concentration of copper after leaching. Yeah, how many grams of cobalt dissolved into the solution, and then after that we also want to know about the electrowinning process. Yeah, during the electrowinning process, what is the concentration of cobalt in the solution? Yeah, because you didn't show how many gram per liter of cobalt in the in the electrolyte. Yeah. And then we also want to know about the current density during the cobalt electrowinning. Yeah. How many ampere per square meter of cathode? Yeah. And then The next is the current efficiency of the electrowinding process. Did you calculate the current efficiency during electrowinding? And then the final question about the how to calculate the cobalt recovery. Yeah, you said then almost 70% cobalt can be recovered from the solution. How to calculate? Yeah, and then yeah, I think that's all my question. Thank you.
Okay, thank you. Your question, Dr. Budi Subagja. Maybe Dr. Sudogyo, you can answer about your question, Dr. Budi Subagja.
Okay, thank you. First question: the cobalt content in slag more than 800 ppm from slag, PI slag, and after solvent extraction, we can get cobalt in solution around 300 ppm. So from this, get the cobalt recovery. Cobalt recovery calculate from the cobalt content after solvent extraction reaction. And the current density in this paper, I don't calculate the current density because the current is not stable. We just stabilize the voltage. Okay, thank you.
Okay, so about Dr. Rudi Subagja.
Yes, I have to know about the current efficiency. Yeah. I think the solution for the electrowinding process too small. Yeah, because in my experience, when you use the low concentration of cobalt, the hydrogen production will increase. Yeah, so the current efficiency will be lower, and then I think will be not economic. Yeah. So I think my comment. Thank you.
Okay.
Okay, thank you, Dr. Rudi Subagja, about explain electrowinding. Okay, any question? The time still 1 minute again. One question. Not yet? Okay, we give applause about Dr. Rudi Subagja. The next presenter, Mrs. Anggi Simatupang.
Actually,
no.
Mr. Ma'am.
Sorry.
Okay,
So
okay.
Mr. Anggi Simatupang.
Yeah, thank you.
Entitled Effect of Sulfur Content in Reductant with Variation of 0.5 to 1.5 stoichiometry in the selective reduction process of saprolite nickel ore. The time is here.
Okay, thank
you.
You
Want to presentation by video or live presentation?
With PowerPoint, I think, because the video is not referred to good. Okay. Good afternoon. Greetings to all the panelists and participants of ISMM 2020. My name is Anggi Simatupang from the Department of Metallurgical and Materials Engineering of Universitas Indonesia. And I feel honored to be given a chance to present our research about effect of sulfur content in reductants with variations of 0.5 to 1.5 stoichiometry in the selective reduction process of saprolitic nickel ore. And I've done this research with Mr. Fajar Nurjaman, Mr. Bambang Suwarno, and Mr. Denny Ferdian. Here's the introduction. As we can see from the nickel distribution map, laterite nickel ores are majorly found on the equator. That's why we need to take this advantage to fulfill our needs on stainless steel batteries, casting, plating, and so on. And the reserves of laterite nickel ore in Indonesia are estimated to reach 1.391 billion tons, or equal to the 8th largest in the world. Here's the table shows the former research that use either sodium sulfate or sulfur as the additive. And this is the flowchart right here is explain how this research is going. We are using anthracite coal as the reductants, and sulfur contents in it in 2.68% and 5%, with the calculation of stoichiometry 0.5, 1.0, and 1.5. And we are using nickel saprolite ore as the sample. And we are using sodium sulfate as the additive with the composition of 10% weight. And the reduction process we use here is in 950 degrees Celsius, 1050 degrees Celsius, and 1150 degrees Celsius. And using the wet magnetic separation to gain the concentrate and tailing and analyze, and we got the conclusion of this research. Here's the results and discussion. From the XRD testing, we found 3 major compounds that are formed from the samples, such as goethite, lizardite, and coesite. From the XRD testing, we also found the percentage of each major element, such as nickel 1.82%, iron 25.2%, and silica 17.25%, alumina 1.42%, and calcium oxide 0.31%, and magnesium oxide 6.43%. Okay, here's the effect of reduction temperature. This curve presents both grades and recovery of iron and nickel with variations of reduction temperatures. This graph also shows the related effect of reduction temperature with sulfur content 2.68% and 5%. On the grade curve, it shows that nickel grade increased with the increasing reduction of temperature. The optimum nickel grade was found at reduction temperature of 1150 degrees Celsius that contained 11.45% nickel. Similar with iron that also increased on 1150 degrees Celsius that contain 73.44%. And from 5% sulfur in reductant, the optimum nickel and iron grade was found at a reduction temperature of 1150 degrees Celsius, which are 8.24% nickel and 70.71% of iron. More sulfur content addition would result in more sulfur content in liquid phase. Thus, it would promote nickel matte structure and lower the nickel grade and ferronickel recovery. And on the recovery curve, we can see the optimum recovery was found at a reduction temperature of 1150 degrees Celsius, which was 84.62%, and nickel recovery at 5% sulfur reductant increased with the increasing of temperature, while iron recovery decreased with the increasing of temperature at a reduction temperature of 1050 degrees Celsius, which is above the eutectic temperature of iron sulfide, 988 degrees Celsius. The iron oxide reacted with the sulfur to form the iron sulfide, and it caused a decrease in the percentage of iron recovery at a higher temperature, and the rate of iron reduction increases. Thus, the iron recovery was decreased too. Here's the XRD analysis, and we've got here from the formation of olivine compounds. Spinel was observed at temperature of 950 degrees Celsius and at temperature of 1050 degrees Celsius and 1150 degrees Celsius. Most peaks were still dominated by olivine, and followed by the reformation of enstatite, spinel, ferronickel, and iron sulfide. And at 950 degrees Celsius, the formation of ferronickel had not been yet formed because it's still formed as a spinel, which were reduced from goethite, and iron sulfide compounds were also not found because the reduction temperature was still below the eutectic temperature. And at 1150 degrees Celsius, olivine compound could inhibit the formation of ferronickel due to the substitution of the magnesium silicate to iron magnesium silicate in the crystallization of ferronickel formation not being optimal enough. The reduction process also found iron sulfide increasing, with the magnesium silicate compound being completely substituted with iron. Thus, it produced a high enough iron magnesium silicate compound. Besides, the enstatite compound reacted with the magnetic compounds such as iron oxide or magnesium-ferrite. Then these compounds form a group of olefin or phosphorite. Here's the same result from the effect of temperature on microstructure. And it can be observed that white areas indicate the ferronickel compounds. Then temperature increases, the reduction rate also increases. Therefore, the grain size of ferronickel is getting bigger. And here's the effect of temperature on compounds form. Gray area indicate iron sulfide, and dark area indicate. Yeah, sorry.
Sorry, Mr. Anggi.
Yeah.
You have 5 minutes left.
Okay.
Okay, your presentation is very quickly.
Okay, ma'am. And this is from the index is the dark area may be never in phase. Here's the effect of reducing amount, and in this section, the effect of amount of reductant used was based on stoichiometric calculations, and the iron grade increased with the addition of reductants. The highest iron grade was found in 1.0 of stoichiometric, and on 0.5 stoichiometric of reductant, which was 8.24% of nickel. And okay, next to the next slide. Here's the effect of reducing amount on XRD analysis. The one on the left shows the highest peak of ferronickel was found in 1.0 stoichiometric of reductant. The magnesium was analyzed as magnesium silicate or phosphorite, which could inhibit ferronickel formation. The iron could also replace magnesium structure in phosphorite to form olefin compounds. At 5% of sulfur content in the reductant, the intensity of the iron sulfide was quite higher on right figure than 2.68% of sulfur in reductant. It seems that the sulfur content also promote the iron sulfide formation as well as the additive additions. Here's the microstructure. And here's the effect of sulfur content on the reductant against the reduction process. We can see the comparison from here, and the peak formation of ferronickel compound was higher at 5% sulfur content than 2.68%. And the formation of N-saturated or orthopyroxene from 5% sulfur in reductant had a higher intensity than 2.68% sulfur. Here's the conclusion. In the selective reduction process, the optimum reduction temperature was 1150 degrees Celsius with a nickel grade, and recovery was 11 and 45% and 84.62% respectively. More sulfur content addition will result in more sulfur content in the liquid phase, thus it will promote nickel mate structure and lower the nickel grade and recovery in ferronickel. Here's the reference, and thank you for your attention.
Okay, thank you, Mr. Anggi, about your presentation. We continue about question and answer session. Please mention your name and institution we want to ask. Okay, Dr. Rudi Subagja, your time.
Okay, thank you very much, Ibu Latifah. Rudi Subagja from Research Center Metallurgy and Material LIPI. It's very interesting presentation from Pak Anggi. And then I have some question about the selective reduction process for the latrate. The first question is, what is the objective of the selective reduction? Because if we speak about the reduction in the latrate, it should be the reduction of nickel oxide or iron oxide to become metal, But in your presentation, I didn't see what the percent of metallization of nickel oxide or the iron oxide, And then the second question, during the selective reduction, you are using sulfur as the additive, And then what is the function of sulfur in the reduction process, Is to control the reduction of iron oxide or to control the reduction of nickel oxide, And then why don't you check the metallization of nickel oxide and iron oxide, And then, in my opinion, that your target is not only the selective reduction, but but your group, I think, want to get the concentrate of nickel, to get the concentrate nickel for the next process, like for the ferronickel or for the nickel production. Yeah, I think that is all of my question. Thank you.
Thank you. Thank you, Mr.
Okay, thank you, Dr. Rudy Subagja. Not many questions. Okay, Mr. Anggi.
Okay, let
you
me
get
answer Mr. Rudy Subagja
answer.
questions. Okay, the sulfur additions is we want to reduce the metallizations of iron, of course, and we found that iron sulfide as well, and with the nickel mate. So from this research, we have the conclusion that too much sulfur addition in the reductants could inhibit the nickel mate formation. So the most optimal calculations of sulfur is 2.68% from this research, I think, Mr. Rudy. I think for the research, we could do this as the one point of calculation and estimation to gain the better nickel grade and recovery, Mr. Rudy. I think.
About
yes, I think one question. I need to know about the target of the selective production process. Yeah, what is the target?
Yeah,
to get high concentrate, or to get to have the metallization of nickel higher than iron. So I have to know. Thank you.
Okay, thank you, Mr. Rudy. Selective reduction process is to target the specific element, of course. We in this research we targeted in nickel, so we must be reduce the metallization of iron instead. And from this research, we gain the most optimal temperature is in 1150 degrees Celsius with 2.68% sulfur in the 0.5 stoichiometric of the anthracite coal, Mr. Rudy.
Okay, Bu Latifa, thank you very much.
Thank you, Dr. Rudy Subagja. Okay, any question? Still 1 minute. Maybe I want to ask Mr. Anggi. Could you predict a reaction from nickel laterite with anthracite or sodium sulfate? Because I don't see your presentation. Mechanism reaction.
Okay, the mechanism reactions are from the laterite to nickel sulfide. From
PPT. Mechanism
reaction.
reaction.
The reactions is from goethite is would prohibit the formation of olefin compounds, of course, and it could be FeMgSiO4 or spinel as well, Fe2NiO4, and it could react with the sulfur and could promote the iron oxide and nickel sulfide, or iron sulfide and nickel oxide. And the increasing temperature, it could be inhibit the ferronickel formation and iron sulfide as well. I think that's the big picture of the reactions.
Yes, why I asked you about mechanism reaction, because I see your research. Sulfur is found in anthracite and sodium sulfate as additive.
Yeah.
It's very important you so explore about research.
Yeah.
Okay.
Yeah, thank you, Ms.
Okay, thank you, Mr. Enggi. We give applause, Mr. Enggi, about your presentation is interesting.
Yeah,
okay, the next presenter, Mr. Eko Sulistiono, entitled Making Nano Calcium Carbonate from Calcium Hydroxide Solution using ultrasonic wave flow with addition of CO2 gas. You want to presentation by video or live presentation, Mr. Eko?
By video, by video.
Okay, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. My name is Eko Sulistiono from Research Center of Metallurgy and Materials, Indonesian Institute of Science. My name is a paper of making nano calcium carbonate from calcium hydroxide solution using ultrasonic wave along with addition of CO2 gas. One material derived of limestone with superior properties than limestone is synthesis of precipitated calcium carbonate. Precipitated calcium carbonate synthesis crystal have different characteristics from natural calcium carbonate from limestone. As this paper, which the result experiment making of nano precipitated calcium carbonate synthesis by reacting of solution of calcium hydroxide with carbon dioxide gas and ultrasonic wave at calcium hydroxide. This experiment was made from natural limestone of calcination process at followed by slagging process. Optimal result of the experiment obtained with addition of calcium hydroxide 10 grams of 200 milli of water, 20% ultrasonic application at 10 minute ultrasonic time. Of optimal result obtained average grain size of 164 nanometer with range of 164 nanometer of in the general, the result of ultrasonic milling have not produced of nano-size compounds. Calcium carbonate chemical is compound with chemical formula of CiCO3, which the major component of the cell marine of organism, snail, pearl, and exhale the primer from limestone from the sedimentation process of small fossil coral of a million of the year. The physical property of calcium carbonate, such as morphology, size, and size distribution, called modified application. Morphology from past calcium carbonate associated with synthetic condition, such as concentrate reactant temperature time as natural addition substances. Preparation of calcium carbonate by dissolution of precipitate can be modified by the additional of dodecyl dimethyl beta-ine material, which can produce of nano-size calcium carbonate. Calcium carbonate rocks limestone hill from Klaten district Central Java, which mill from rocks of the calcium limestone by process of precipitated calcium carbonate use as pharmaceutical tire of paints of paper and cement. Raw material is the study as raw material calcium hydroxide solution of technical CO2 gas dilute calcium hydroxide solution of the natural limestone from the Bayat area, Klaten, Central Java. The composition of limestone Bayat can be entable. The raw material manufacturing start from calcinate of natural limestone, which the consideration of the calcination of calcium carbonate obtained from optimal temperature at 1 atm of gas pressure. The calcination result then added with water so that under gas slacking process, the calcium hydroxide solution, the reduced carbonate with dioxide gas, so that there is now in the carbonation process. Experiment variable change of process at ultrasound amplitudes, calcium hydroxide feed, ultrasound time. Variable state as volume, temperature, velocity, gas, CO2, and carbonization, time carbonization. Characterization of the result of the characterization analysis of the using X-ray fluorescence scan XRF equipment of the composition of particle, precipitation rate, and the scanning electron microscope SEM, and the grain size and particle shape. Result and discussion. The carbonation process of 20 minutes has been carried off the first time with the application of CO2 gas is the table. From the experiment result with ultrasonic with treatment is the product of red precipitant slow is a red precipitate of 20 grams of feet of calcium hydroxide. Is the next step of the experiment of carbonation, which process carried out of by giving ultrasound wave of 10 minutes of variable amplitudes as well as in process the result of the experiment give ultracated with the carbonation process can be seen of the fixed left. From the result experiment, which variable percent of solid raw the material of calcium carbonate and ultrasonic amplitudes using in the Stock method, the optimum process based result amplitude as 25 and 25% of the addition of calcium carbonate if times and after obtaining of optimization result of the 3 point the particle diameter measurement of the carried out using PSA nano analysis order obtain more diameter data accurate. Calculation of nano PSA analysis they also carried of the sample that have not been carried. Particle size distribution calcium carbonate precipitate. The result of PSA analysis show that the head pin will size rank the after ultrasonic milling process was carried out. As a result of SIM analysis, SIM analysis as a result also has been reduced for the granular size of the calcium precipitate after ultrasound milling process. The measurement result of the calcium carbonate precipitate contain many nanoscale grain size. The result of SRD analysis show that there has been a phase change of the natural limestone calcium carbonate to turn into a silica precipitate. The pace of change that occurs of the from calcite of syncalcite. The result of the calcination process of limestone show that there is no fixed calcite. This show that the limestone calcination process the been running perfectly. Conclusion from the using the settling rate measurement method is found the optimum ultrasonic amplitude between 20, 25 or 13. So be looking energy consumption. The optimum point of the amplitude of 25. The result of the measurement of nano PSA analysis show that the effective wave reduced grain size with best result of the process at 10 gram of calcium hydroxide to 200 milli of water resulting of the grain size of 1.02 nanometer to 342 nanometer, and the no particle size below of 10 nanometer. The same test can conclude that the particle size which says below 100 nanometer, but among the unknown from the result of same testing, I can be seen that the crystal from is cubic with the characteristic of calcium carbonate crystal. Same analysis result from so the calcium carbonate crystal undergo coagulation from the burn with water into a compound such as Kt and monohydrocalcite. The HRD analysis result so the natural limestone calcination process is running perfectly, can be seen from the formation peak of CaO and Portlandite while calcite is lost. Based of XRD analysis, the final result from the calcium carbonate consists of only calcite or calcite synthesis compound. So the carbonation process using ultrasound wave has gone perfect. In the general, the result of ultrasound milling have not produced of nanoset compound significant. Therefore, ultrasound process needs to be continued with the experiment to the prologue in the ultrasound process. Thank you.
Okay, thank you. Your presentation, Mr. Eko Susyono. Okay, we continue question and answer session. Please mention your name and institution. Any question, everybody? Okay. Dr. Rudi Subagja, as senior researcher.
Dr. Latifa, can I ask question?
Okay, Mrs. Farisa, can your question?
Is there any next process to eliminate coagulation so the size can reach nano-size particle? Next step process to minimize coagulation.
Okay, Mr. Eko Susyono, you can answer.
Next coagulation is nanoparticle. Is it one coagulant process is ultrasound is bersama-sama gitu. Jadi koagulasinya bersama dengan pemberian ultrasonik. Ya.
How about Mrs. Farisa? You is clear?
I mean, is there any other process so that the size can be smaller? The size is not reach the nano size because there's coagulation in that presentation. So how to eliminate that coagulation?
Okay, we have 2 minutes. Any question, ladies and gentlemen? 1 minute, maybe one question. Okay, we're waiting the audience to ask Mr. Eko. I have one question. How to control in the synthesis nanocalcium carbonate from calcium hydroxide using ultrasonic wave? about amplitude, time, and other parameter.
Untuk saja yang simpel aja. Jadi proses ultrasonik ini yaitu kita hanya menggunakan variabel amplitudo, kemudian sama dengan ini hanya amplitudo saja kita coba untuk berbagai konsentrasi padatan dari 10 gram, 15 gram, dan 20 gram. Di sini semuanya menunjuk ke 25% amplitudo hasil yang terbaik, di mana di sini butirannya itu adalah sangat kecil ya, untuk 40 sampai 75 nano, kemudian 46 sampai 79 dan 47 sampai 72. Jadi temperatur tidak kita utak-atik gitu. Karena alat ultrasoniknya itu hanya bisa untuk temperatur hanya untuk satu frekuensi 20 kHz. Sedangkan untuk temperatur itu bisa kita atur, tapi di sini kita hanya mengatur amplitudo. Untuk temperaturnya kita tetapkan di sini sekitar 90 derajat Celcius. 90 derajat Celcius temperaturnya. Jadi bisa diturunin, bisa dinaikin, tapi ini temperaturnya sama gitu. Jadi variabel yang berubah cuma 2, ultrasound amplitude sama calcium hydroxide umpan, calcium hydroxide umpan.
Okay, thank you your answer, Mr. Eko Sulistiono. Okay, we give applause Mr. Eko Sulistiono. The presentation is interesting. The next presenter, Dr. Sudibyo, entitled Separation of Cobalt from Slag of Nickel Pig Iron using Solvent Extraction Method. Okay. The time is yours.
Please using video.
Okay. You want to present it by video?
Yes.
Okay.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sudibyo. Today we present my paper with title Separation of Cobalt from Slag of Nickel Pig Iron using Solvent Extraction Method. Slag which is high value, such as cobalt. Cobalt separation process from nickel pig iron slag using solvent. In the study, Kakuchi experiment design is used to optimize and analyze the cobalt separation process from nickel pig iron. The parameters we study in this work is pH, extraction duration, concentration of acetic acid, and organic per aqueous volume. Methodology: first, slag of NPI was leached using sulfuric acid, and then solvent extraction process was conducted using the separation panel. This is a Takuchi experiment design, which has 4 parameters. First is pH, second is extraction time, acetic acid level, and organic per aqueous volume. And this is the experiment result. Extraction percentage of cobalt and this is the Takuchi analysis using military software. From this picture you can see the optimum level of each parameter, and this is the analysis result of SN ratio. From this table, we can see that the parameter have the most influence towards focus extraction is pH. The second rank is organic per aqueous volume. The third extraction duration, and the last is percentage concentration. This is the graph of the effect pH on the percentage of copper extraction. From this picture, we can see that the optimum condition at pH of 6, because at the pH of 6, the most of impurities such as Fa, mangan has been precipitated at this pH. And this is the graph of the effect of organic per aqueous toward the percentage of copper extraction. From this graph, we can see that the optimum condition at the organic per aqueous at the second level, or 0.6. And this is the effect of extraction duration on the percentage of copper extraction. From this graph, we can see that the optimum condition at the 10 minutes extraction duration. At the 10 minutes, the organic solution reached its saturation, so the cobalt will extracted to organic solution at this level. More than 10 minutes, many bond of cobalt which bonded in organic solution will become decomposed. So the percentage of cobalt is decreased. And this is the graph of percentage acid toward percentage of cobalt extraction. From this picture, we can see that the optimum condition is at the 10% of percentage acid. The highest, the optimum condition at the largest of percentage acid level, because percentage acid can attract the cobalt to organic solution effectively and forbid the impurities to enter the organic solution. And this is the extraction result using optimum condition. At this optimum condition, we can get the cobalt extraction at 73%. Conclusion: the cobalt extraction process from slag of nickel pig iron has been done using the Taguchi experiment design. According to the analysis, pH is the most influential parameter on the cobalt extraction process, which is followed by organic per aqueous ratio, extraction duration, and percentage concentration. The optimum value obtained from the study is 6 of pH, 0.6 of organic per aqueous level, 10 minutes of extraction duration, and 10% volume per volume of percentage acid presentation, and the percentage of copper extraction using optimum condition is 73%. Thank you.
Okay, thank you. Your presentation, Dr. Sudibyo. We continue discussion. Any questions, ladies and gentlemen?
I want to ask some questions.
Ms. Clarissa, your turn.
Thank you for the opportunity. I have 3 questions. First, the solvent extraction process consists of 2 stages, extraction and stripping. So in this paper, only extraction that you explain, or there is other next step, the stripping process itself? The second question is, solvent extraction is for purification. I only see the cobalt extraction, percent of cobalt extraction. How about other impurities? And the third questions, usually to determine organic and anorganic ratio, so for solvent extraction process, use McCabe-Thiele diagram. But you use this experimental design. How effective this experimental design compared to McCabe-Thiele diagram? Have you compared this? Which more effective? Thank you.
Okay, thank you. Your question, Mrs. Farisa. Then, Dr. Sudibyo, you can answer.
Okay. In this work, I use one step of extraction, not 2 step. I'm sorry, but the cyanide and prussic is mixed together. So we use only a single step of solvent extraction. Another work I use 2 steps. First is prussic and then cyanide. But in this work we combine the prussic acid and cyanide in single step of solvent extraction, because this prussic have a good performance to avoid the nickel to enter the organic solution, and the cyanide have good performance to catch the cobalt to enter the organic solution. And then we use Taguchi experimental design because we can optimize, and we also have a lot of we have decreased the number of experiment, because this cyanide and prussic is very expensive. So I use Taguchi because the run is very few. And then why I use Taguchi because not make the graph, because each or and a slag have a different characteristic. So I propose to make our design experiment to optimize this process. Okay, thank you.
Okay, we have 2 minutes.
Can I have another?
Okay.
So for my second question, you have not compared the McCabe-Thiele diagram and this experimental design, I think, for organic and anorganic ratio. And then I think you have not answered my question about other impurities, other metal are did you did you
Okay.
Next sorry I mean for my first question, solvent extraction consists of two-stage extraction process, which is the metal extracted in the organic phase. So it form a complex metal complex, and then it will be stirred, stripping, so it can use to other process, to the next process like electrowinning. I only see the extraction process, not the stripping process. I think solvent extraction, which I know, solvent extraction consists of two stages. So I think maybe for the next, if you have not do the stripping process, maybe it's for your next work. Okay, thank you. It's my.
Okay, thank you, Mrs. Farisa. Time is up. Okay, we give applause Dr. Sudibyo about your presentation. The next presenter and last presenter, Mr. Fatan Bahwi, entitled Study Effect of Sodium Sulfate Doses and Graphite on the Selective Reduction of Saprolite from Nickel Grade Recovery and IM Nickel Grain Size. Mr. Fatan, do you want to present us by video? Okay. Time is yours.
I'm Fatan Bafi. I'm from Research Unit for Mineral Technology, Indonesian Institute of Science. And I'm also master student in Department of Physics, University of Indonesia. Today I would like to present my research talking about saprolite in the study effect of sodium sulfate dosage on the selective reduction to nickel grade recovery and iron nickel grain size. And this is my outline introduction, and then the second one is literature review, and the third one is methodology, research and discussion, and the last one is conclusion. For introduction, why I choose nickel for my research, because of in here a lot of nickel ore in research is laterite. So if we compare with the sulfide, is different. So and then the production of laterite is a little bit low. So there is need some research to extract nickel from laterite, and then we can see the nickel using is like stainless steel until 65%, and then following with the production, you can see the stainless steel production. It grow up for the until 2022. It will be grow up again in the next year, and then it also following the nickel consumption. So we need to consider about the extraction nickel from laterite. And then the next one is Indonesia has a big chance for production nickel from laterite. You can see it's just a little bit production is just around 200 tons. So this is the chance for us to make a research about laterite. And then this is comparison for the process extraction of laterite. There is hydrometallurgy, pyrometallurgy, and also selective reduction. So for hydrometallurgy is using a lot of reagent and then using and also too many steps from process, but the result is high grade and recovery of nickel. And then for pyrometallurgy, both of them for blast furnace and copper using temperature around 14 and 1500 degrees Celsius. And this one is difficult to control for copper and low lifetime because of the ore melt particle in the process. But for blast furnace, the product is so low quality due to contents of sulfur and phosphor. And selective reduction is the middle process between pyrometallurgy and hydrometallurgy because of using a middle temperature below 1200 degrees Celsius and then can be used for low nickel grade ore and also using additive. For the target and limitation problem in this research, we want to get the nickel grade up to 5% in beneficiation profit, and then get the high nickel recovery, get the grain size. And for the limitation problem, using laterite with composition of nickel is around 1.4 until 2% for the first one. And the second one is using graphite with the composition carbon is 99%, and then the additive using in this research with the variation 5, 10, and 15%. And characterization is using SRD, SRF, and optical microscope. And this one is the I was talking about before. The selective reduction is between the hydrometallurgy and pyrometallurgy. And then for the stoichiometry, we can see in this result we want to get ferronickel increase and also iron oxide decrease. And this one is the selective reduction for literature. And then the material and methodology. What's material I use? In here I use laterite and crushing and milling and sieving until 100 mesh. This is the optimal particle size according to the reference I did it. And then I did SRF, SRD, and also OM. For SRF for getting element, SRD for getting the compound, and then OM for getting the particle size of ferronickel. So the methodology is using the saprolite, natrium sulfate, and graphite for the reductor, and then make it mixing and then make it pellet. After that, we were drying under 120 degrees Celsius for 4 hours with the variation sodium sulfate 5, 10, and 15%. With note, I use magnetic for separation in 1000 Gauss, and also the composition graphite. Composition carbon in graphite is 98.64%. And I will continue the process. This is we put in the furnace and reduction process at 1150 degrees Celsius for 1 hour, and then quenching. This quenching process is for control the iron oxide, so the iron oxide will not form in this process. And then after that, the material was drying at 120 degrees Celsius for 4 hours. After that, we were milling, sieving, until 200 mass and mating dispersion in the first step with wet condition and filtration. And we will get kettling concentrate and SRF. We will do, we have done SRF, SRD to get the element and also the composition and the phase. This one is the flow chart. We can see the variation in the natrium sulfate. So we want to get the optimal one according to the SRF data. And for the characterization now, we can see this one is saprolite from the nickel percent is 1.82, and then for the iron is low, the low one if we compare with limonite is 30.47, and then for the raw for SFD we can see the lizardite and goethite appear in here, and also quartz, and the majority is goethite is around 53%, and following with the lizardite 31%, and also quartz. In here, I would like to talk about the concentration of sodium sulfate. What is the optimal one? 5, 10, or 15%? So from the composition, we can see the SRF, the optimal one in the 15% according to SRF data. With the recovery is 64.78%. So with the and then following the SRD, we will get a lot of but in the following SRD we have a lot of the phosphatide, but also the phosphatide is bonding with the tetratinate. Tetratinate is like iron nickel also, but the problem in saprolite, a lot of nickel, a little bit nickel is joining with the lizardite around 30% according to SRD data in raw condition. So, but this is still optimal condition in the physical. And then for the following the microstructure, we can see is we will get the optimal size for a particle nickel, iron nickel. Iron nickel is the white one. We can see the optimal one is around 10 until 30%, and we can see in the 15% in the optimal condition. This is still allowed for the size because of around 10 until 30 micrometer. And for my conclusion is according to the XRD data and also the SRF data and the grain size according to optical microscope result. So the optimal one in the under 15% sodium sulfate with the size, the larger one is 40x, but in microstructure we can see the 50%. There is a lot of grain size from 10 until 30 micrometer, and then for the SRF data, we will get 5.65%, and with the recovery 64.78%. So this is optimal one because of we got the nickel until 5%. So this is my reference for this session. Okay, thank you very much for the listening.
Okay, thank you, Mr. Fatah. We continue discussion. Any question? We have 2 minutes. One question. Not yet. Okay. Mrs. Farisa, you have question?
I have,
no,
sorry,
no.
I have a question for Mr. Fatan.
Yes. Question for Mr. Fatan. Where you say the optimal in the 15% of sodium sulfate?
Yeah, cause thank you for the question. I think there is some voices like Azan voices in here. Maybe I wait 1 minute to wait the Azan, and then I can answer later. It's okay, Dr. Latifa. Right now in here, Asar time, so
Okay.
a lot of Azan voice. So I need to wait. Is it okay?
Okay.
Okay, Dr. Latifa, I can answer the question from Mr. Selamat Sumardi. And then why is the optimal in the 15%? Because of the because of according the XRF data I use in here. So the limitation problem from the research, I use the this according the XRF data, the optimum nickel I got in the 15%. If we compare with the in the 10% is still in the below 5%, but it's a little bit just different between the 10 and 15%. But and then the microstructure also the size is small one, around 10 until 20 micrometer for the 15%. Even there is some little bit the big one in the optical microscope for 15%. So maybe this is the my answer. How, Mr. Samad?
About Mr. Slamet?
Okay, very clear. Thank you, Mr. Fatan.
Okay, thank you. Okay, we give applause Mr. Fatan.
Okay, thank you very much, Dr. Latifa.
Okay, very well, ladies and gentlemen. Now we come the end of presentation in one session. I would like to say thank you all presenter for your information and knowledge, and to audience, thank you for your active participation. I hope the presentation will be beneficial for everybody. Thank you your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good afternoon, everyone.
Waalaikumsalam warahmatullahi wabarakatuh.
I think we directly move to session 2 due to some technical issue previously, so we're not going to have a break. Now we are in session 2 of this group, and I think we have 6 presenters, and the time rule is still the same. My name is Taya Chitrawati, and I'm going to be the chair of this session. And I invite all participants in this session to, if you have question, you can pose your question during the presentation in the chat window, or you can also ask your question directly to the presenter after each presentation. Without further ado, due to time limits, I would like to invite our first presenter, Ms. Nadia, to present her work. So she will present.
Ms. Nadia's presenter will be me.
I see, okay.
Saya.
Oh, so it's, okay. What form will you use? Video?
The video.
Okay. Okay, then the time is yours.
Okay, thank you.
Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. Thank you for the opportunity to present our research. First of all, let me introduce myself. My name is Agridova, and I come from Research Center for Metallurgy and Materials, Indonesian Institute of Sciences. And today, I would like to present our paper titled Effect of Chemical Reagents on Ion Precipitations of Hot Spring Brine Water from Tirta Sanita, Indonesia. The outline of my presentation will be first introduction, and then materials and method, followed by results and discussion, and finally conclusions. One of the raw materials that is currently being explored for the added value to be used in the development of processing technology is brine water. The use of brine water is still not widely utilized, even though it's known that the minerals still contained inside are some of the main raw materials for many industrial applications. Brine water mainly formed through the hydrothermal alteration process, which is a result from the occurrence of a new mineral in the rock due to reaction in between the magmatic heat source. The modification of seawater into salt form through evaporation can also create brine water in the form of a residual liquid as byproduct, which contains a concentrated mineral aside from the salt itself. For the extraction of brine water itself, Jason's West in 1970 has explored the addition of calcium or carbonate ion in seawater can increase its saturation so that calcium carbonate precipitate quickly. Sun et al. In 2015 has observed a direct relationship between calcite surface energy and magnesium-calcium ion concentration for the nucleation mechanism of metastable aragonite in seawater. Latifa et al. In 2017 has also investigated the effect of partial evaporation and the use of acid and carbonate salts in synthesis of calcium salts. In this research, we are going to observe and analyze the effect of various chemical reagents on ion precipitations of calcium, kalium, magnesium, and natrium from 2 types of hot spring brine water, initio and evaporated. Next, we are going to talk about materials and method. For the extraction process, the method used in the study is the chemical precipitation method as used in our previous research. In short, the brine water used was from hot spring Tirta Sanita, Indonesia, amounting to 10 liters, which were evaporated until 20% volume and then continued with refluxing process. The initial brine water, which is not evaporated, will be coded brine water A or BWA, while the evaporated brine water is brine water B or BWB. Chemical reagents, namely ammonium carbonate, ammonium hydroxide, and sodium carbonate with concentration of 4N, was then mixed into both solution of BWA and BWB to separate the brine water into filtrate of soluble compound and precipitate of insoluble solid form. The volume ratio in which the brine water and chemical reagent used is varied by 20:1, 20:5, 20:10, 20:20, 20:30, 20:40, 20:50, and 20:60. The resulting solution was then stirred until homogeneous, and the precipitation process is observed. After the precipitate reached the saturation point, the solution was then filtered so that the filtrate and the white solid precipitate is obtained to be characterized. The filtrate was then characterized using ICP or AS, while the precipitate was first dried and characterized by scanning electron microscope energy dispersive X-ray spectroscopy. Now for the results in discussion. For the initial concentration, the element components contained in BWA or the initial and BWB or the evaporated are seen in figure. It can be observed that the component of BWB contains more minerals compared to BWA, which means that the evaporated brine water is much more concentrated than the initial brine water. This phenomenon is due to the evaporated brine water solution, which turned into supersaturated state with its ion activation products more than that of the solubility products. Now for the effect of volume ratio to chemical reagents on precipitate. This graph shows the relationship between the addition of chemical reagents ammonium hydroxide or AH, ammonium carbonate or AC, and sodium carbonate or SC to the amount of solid formed from BWA or A and BWB or B. It can be observed that there are more precipitates produced by B compared to A. This is due to the chemical contents of B is more concentrated compared to A, so that the saturation of B is faster than A. The maximum precipitates formed in A reach its peak ratio of 20 to 40, and while in B, 20 to 5. In both experiments, SC can form the most precipitate. This is probably due to the fact that SC contain more positive ions that can precipitate the solutions quickly. Now for the characterization of brine water precipitate, table 1 shows the percentage of elements mass in precipitates resulting from A and B with AH, AC, and SC chemical reagents. Figure beside it shows the morphology of precipitates from A, the above one, and B, the bottom one, with AH, AC, and SC. The morphology consists of octahedral-shaped small particles, showing that the precipitation form contains a lot of magnesium or sodium, as in accordance to table 1. This precipitation is possibly in the form of magnesium chloride or sodium chloride. Now for the characterization of filtrate from chemical precipitation. Components contained in filtrate of each treatment showed the elements that were not precipitated. In this figure, it shows the change in calcium elements from A and B after the addition of various SC, AC, and AH ratio. It can be observed that the addition of SC or AC is what shifts the initial calcium concentration into lower state, with the best ratio is discovered to be 20 to 10 for both A and B. Meanwhile, the addition of AH does not really lower this calcium concentration for both A and B. Now in this figure, it shows the change in potassium. It can be observed in the figure that the addition of chemical reagents into A or B from 20 to 10 until 20 to 60 all shows a decreasing tendency, meaning it lowers the potassium concentration by turning it into precipitate in the previous chemical reaction. In this figure, it shows the change in magnesium elements. It can be observed that the addition of chemical reagents into A and B mostly shows a decreasing tendency of magnesium concentration. For A and B, the best ratio to precipitate magnesium is 20 to 60 using ammonium hydroxide or AA. Now in this figure, it shows the change in sodium elements. It can be observed that the addition of chemical reagents into A and B only on 20 to 50 and 20 to 60 that shows the most decreasing tendency of concentration, with the best ratio for precipitation in this case is discovered to be at 20 to 60 for A and 20 to 30 for B, with both results using ammonium hydroxide as chemical reagents. And finally, we reach our conclusion. Brine water is a solution that has a high salt concentration. This is because the brine water comes from seawater byproducts. Extraction of brine water using chemical precipitation is an easy and inexpensive method. The results of the analysis showed that the chemical reagents that are effective for producing calcium carbonate are chemical reagents ammonium carbonate. This is indicated by the chemical composition from the precipitates analyzed by SEM-EDS. With ammonium carbonate, they can produce more mass percent of calcium. The filtrate results from precipitation with ammonium carbonate has also been analyzed using ICP-OAS and showed that around 90% of the precipitate contains calcium. The chemical reagent that is effective for producing magnesium chloride is discovered to be ammonium hydroxide. This is shown in the mass percent of precipitate analyzed by SEM-EDS, with ammonium hydroxide producing more mass percent of magnesium. The filtrate with ammonium hydroxide has been analyzed by ICP-OAS and showed about 90% of precipitate contains magnesium. And finally, this is our reference. And thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Aga. Okay, first I will like to give the chance to the floor for all participants who has questions. Dr. Latifa, do you have question to Mr. Aga? Or Dr. Eric?
Maybe Dr. Latifa can help me answer any question related to this paper later.
I have short question for Mr. Aga. Is it okay?
Yes, please.
Thank you very much. I'm curious, why do you choose the precipitation as the first choice compared to other methods like ion exchange, which is, in my opinion, you could use it recyclability. I mean, you can use it more than one time. You can regenerate the steam or whatever it is. Or maybe you can exsolute that by mixing with the organic solvent like ethanol. I'm just curious. Maybe you have consideration that I don't know. Please share that. Thank you.
Okay. Thank you for the question, Mr. Eric. Probably for this research, we chose it because of the availability of the materials that we have at our disposal. And maybe we also did it because the choice of materials and also the availability already. The easiness of the process. Maybe Dr. Latifa can also help me in answering this question because it's a joint experiment that we did together. Okay.
Please, Dr. Latifa. We still have 1 more minute, maybe a short explanation.
Your objective is to decrease the calcium content in the brine. Is it correct?
Yes.
Okay. How about the other elements like sodium, potassium? It's not your objective, or just calcium is the only objective?
Okay. Actually, the objective is to get the lithium content at first, but in this
I
case,
see.
we
As
first
lithium
published
carbonate, you mean? Okay.
How to reduce the other content first.
Okay, I get it. Thank you.
Thank you.
Okay, so to answer your question?
Yes, sure. Thank you.
Yeah, okay, thank you. I think because the time is up for Mr. Aga. Thank you so much for your presentation. And now we're going to move to our second presenter. Yeah. Mr. Eric.
Yes. Can I have videos? Thank you.
Sure.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. First, I'd like to express my gratitude to the ISFM committee and all attendants here for allowing me to share our research on nickel recovery from electric arc furnace dust through leaching using amino acid in alkaline condition, including the selectivity evaluation. My name is Eric Prastyo. I work as researcher from the Indonesian Institute of Sciences. Mostly my research interests include hydrometallurgy and critical material recycling. First, the introduction. Why we have interest in electric arc furnace dust? We have interest due to its potential as secondary sources for base metal, especially zinc, copper, and nickel. Which in this case, the content would be higher than 40% for zinc, 1% for copper, and about 0.5% for nickel. And our previous work on leaching using amino acid alkaline leaching was successful to recover zinc and copper. And how about the nickel? This is the question we would like to answer in our current research. Although typically the nickel content in the dust is relatively lower compared to the conventional raw materials such as nickel nitrate, in this case it could more than 1%. The simple phrase in EF does make it attractive as alternative source material for nickel, since it makes the processing become easier and straightforward. So the objective in this research is to assess the amino acid. In this case, we use monosodium glutamate as lixiviant to recover nickel from the electric arc furnace dust, while the parameters investigated include pH, the glutamate concentration, pulp density, and kinetics, in this case time and temperature. Aside from the leaching efficiency or recovery, we also investigate the selectivity according to the parameter tested. In our research, raw materials used was the electric arc furnace dust, which major content was determined using XRF analysis. According to the analysis, it revealed that the dominant phase is zinc oxide, which about 52%. And this result is also confirmed by the XRD analysis research, which showed that the phase dominated by zinc oxide and gahnit, zinc alumina. Batch method was used to evaluate the effect of parameters to the nickel recovery and selectivity. In this case, the metal content in pregnant lead solution was determined using atomic absorption spectrophotometer. The recovery was calculated using mass balance, and selectivity is defined as the concentration ratio of two metals in pregnant lead solution. Now the result, in this case the pH effect to the nickel recovery and other metals recovery in the left figure, and selectivity of nickel over other metals in the right figures. The constant variable in pH effect investigation were the glutamate concentration 1 molar, liquid solid ratio 20 milliliter per gram, reaching time 12 hours at room temperature. In left figure, as we can see that the nickel recovery and other metals decrease as pH increase. This was probably due to the hydrolysis of metals in alkaline condition. In the case of iron and aluminum, the recovery was negligible. At the right figure, we can see here the selection factor, which is the concentration ratio between nickel and other metals. The highest selection factor was obtained between nickel and iron, and nickel aluminum. Since iron and aluminum concentration in pregnant lead solution were very low. Based on the figure, we could conclude that the optimum pH for selective nickel recovery was between 8 to 10. Next, about the effect of glutamate concentration. In the left figure, we see that minimum concentration to obtain nickel is about 0.25 molars. Well, based on the selectivity studies, the maximum selection factor to obtain nickel in pregnant lead solution occurred at MSG concentration 0.5 molar. Next, the pulp density or liquid solid ratio. The constant variable in this case were the pH 9 and glutamate concentration 1 molar, reaching time 12 hours at the room temperature. At the left figure, the minimum liquid solid ratio to obtain maximum nickel concentration is about 15 milliliter per gram. However, according to the selectivity result in the right figure, lesser liquid solid ratio produced better selectivity. In this case, the continuous process such as column leaching will be beneficial for the selective nickel recovery, since in a continuous method, the solid liquid ratio would be kept as minimum. Next, the kinetic studies, which was investigated at 3 different temperatures, 30, 50, and 80 centigrade. And the result was modeled using 6 models: shrinking core model, chemical reaction, product layer, and then shrinking particle model, film diffusion. interface transfer and diffusion, pseudo first order, and pseudo second order. Based on the coefficient correlation ratio obtained, shrinking core model through film diffusion as the best model to describe the leaching process. Finally, what can we conclude from the studies? First, nickel was successfully and selectively leached from the electric arc furnace dust using monosodium glutamate as excipient. The optimum leaching condition was the pH about 8 until 9, mSg concentration 1 molar, and liquid solid ratio about 15 until 20 liter per kilogram. However, based on the selectivity analysis result, it reveals the different optimum condition. The optimum condition was pH 10, mSg concentration 0.5 molars, and pulp density about 5 liter per kilogram. Next, the concentration ratio of selectivity factor between nickel and other metals is about 25,000 to aluminum, 380 to iron, 5 times to magnesium, and 9 times to calcium. Finally, the kinetic modeling indicate the leaching process was driven by a diffusion process. I think that's all. Thank you very much for your kind attention. And in any case, there's any question and comment, please don't hesitate to ask. Have a nice day. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Eric. So I welcome questions from all participants in this room. Okay, I just wondering if you kind of change the concentration of the MSG, how do you think the effect of pH to the Ni recovery will look like?
You mean change to the higher concentration of FSG?
Yeah,
Okay.
if it's higher or it's lower, might be something different, because I saw that the nickel is actually not significantly changed from 6 to 9 and then decrease, right, in the pH 10.
The possibilities that if you increase the MSG concentration at more alkaline condition, the recovery would increase, in my opinion, because the presence of the complexing agents such as the glutamate would prevent the hydrolysis. Yes, but in the pH study, I limit my MSG concentration only 1 molar.
I see, okay.
Yes.
But you also use the 2 molar, right?
Sorry?
You also use 2 molar in your study?
Yes, 2 molar, but the pH is constant about 9.
9, yeah.
Yes.
So with your kinetic model,
yes,
will you recover more if you kind of try to increase your temperature? Is there any optimum? Do you think there's a limitation of temperature that you can get optimum nickel recovery?
In our study, the maximum temperature we tested is about 80 degrees Celsius, and it reached the maximum recovery in 12 hours. So there is probability that we can speed up.
12 hours?
Yeah, 12 hours. Okay. So if we increase our temperature, working temperature, there is probability that we could get the maximum or saturation nickel recovery faster.
So a shorter time, you mean?
Yes.
All right. Okay. Is there any other questions from all participants?
I expect Dr. Latifa would pose questions.
Dr. Latifa, are you going to ask something? or maybe she's praying perhaps.
Oh, I see.
Yeah.
My
Okay,
apologies.
then if no other questions, I would like to say thank you to Dr. Eric for his presentation and knowledge sharing.
Thank you very much, everyone.
Yeah, and now I will move to our next presenter, Ms. Miftah, with developing of mechanical and corrosion properties through intercritical heating on DP lateritic steel modified. Please, the floor is yours.
Test, can you hear my voice, Dr. Taya?
Yes, clearly.
Okay. Okay.
Are you going to use video or?
Yes.
Okay.
I want to video.
Yeah, please start then.
In figure 1, we can see an automotive industry application of DP steel, such as a bumper beam, a front reinforcement, etc. DP steel have provided a wide range of excellent and industrially obtainable mechanical properties. The automotive industry has demanded steel grade with high tensile elongation to ensure firm ability, with high tensile strength to establish fatigue and crash resistance, low alloy content to ensure wearability without influencing production costs. Many researchers focus on a simple ferrite martensite microstructure development. DP steel are low carbon, low alloy material with 20 until 30% volume hardness in a ductile ferrite matrix. DP steel typically have high ultimate tensile strength combined with low initial yielding stress. Soft ferritic network provide good ductility, while hard particle place dilute bearing. Properties are controlled by martensite volume fraction, martensite grain size, etc. Now, intercritical annealing is the one only to produce DP steel while it's heated in intercritical temperature 750 Celsius and hot followed by water quenching for produce DP microstructure such on figure 1. Recently, the main challenge is producing dual-phase steel is to achieve grain refinement using a conventional method such as microalloying and thermomechanical process. Chromium effect is like to manganese and place as stabilities retain austenite, delay perlite, and binary transformation, elevated martensite formation due to improving hardenability and ultimate strength. Besides that, chromium enhances corrosion resistance indirectly, further giving proper corrosion protection. The aim of the research is to determine the effect of chromium addition during intercritical annealing in IC X790 modified from lateritic steel. This is a methodology of the research. Firstly, the investment casting process produced IC X790 modified from lateritic steel by adding 1%, 2%, 3% chromium at the main composition as depicted in table 1. All samples were heated in intercritical temperature about 750 Celsius and held for 1 hour in the muffle furnace and just followed by water quench for produced dual-phase microstructure. After that, microscopic examination was performed by using optical microscopy. The specimens were mounted, ground, and polished in 2000 grade and just followed by extra in a 2% neutral solution. The volume fraction of ferrite martensite were calculated using imaging software. Mechanical properties was performed using hardness and tensile tests. Hardness measurement was carried by vigorous microhardness tester under a load of 10 Newton and dwell time of the 10 seconds. The tube size of the tensile specimen was preferred according to standard STM EXM, and the tensile test was done at universal machine. This is a microstructure picture on DP steel with different level chromium. Raw material 1%, 2%, 3% chromium addition as resolved by metalography test. Generally, all samples from Figure A until D have similar microstructure, and there were vertex and martenset that sit in the absence of carpet formation. The martenset substructure is typical of low-carbon martenset. The absence of carpet is assumed to be caused by chromium. Ferrite was found along with before the austenite grain boundary that is indicated by wet area, while snappening martenset forms are clustered around ferrite grains. Chromium addition effect tends to that of martenset volume fraction as depicted in Table 2. In Table 2, it has a similar percentage of any level difference chromium. Figure 3 tells us about micrograph on the pistil with raw material 1%, 2%, 3% chromium addition. Micrograph consists of a ferrite for a gray area and martenset for dark area visible without carpet formation. In Figure A, ferrite is represented by 1 and 2 square so that a different level of carbon and chromium. In square 1 is about 0.2 carbon and 0.8 chromium, and square 2 is about 0.3 carbon and 1.3 chromium. And this is a chromium distribution for ADAX analysis. On mechanical properties, chromium addition has little effect on hardness value. The hardness of the pistil obtained after intercritical heating giving us of 62 until 66 Hz. On the other hand, ultimate tensile strength increased along with the level of chromium addition and reached a maximum point at 730 MPa by adding 2% chromium. The ultimate tensile strength and the strength does not have the same trend. The chromium addition effect then to that martenset volume fraction. The addition of 1% chromium influenced the field strength to increase about 500, then decrease as chromium content increased. There were confirmed that chromium accelerated the kinetic rate of austenite formation. The more the volume of austenite, the higher the amount of transformed martenset after rapid cooling. Consequently, it is to affect the higher strength of steel and elongation reduction. The strength of the pistil increased along with the chromium content increase, so that elongation value decreased less than 6%. The goal in the research of the pistil when viewed from elongation has not been optimal reached. It is indicating that the steel with this process become brittle due to the chromium addition affect the dislocation mechanism. Low ductility of the pistil is caused by no excess austenite retain of metastable phase in microstructure from austenite phase. It has good ductility and energy absorption for properties of iron steel. He said that the corrosion test of the pistil was carried on NaCl 3.5% by TOEFL electrochemistry measurement. We can get a ichor corrosion rate as a Table 3. Ichor had gradually decreased as chromium raised, and according to Faraday's law, the corrosion resistance of the sample increased. This result is appropriate to mechanical properties and might cause the fraction of volume martenset increase with chromium addition. The increase in the fraction of martenset brought about by higher chromium content leads to a change in the ratio of the cathode and anode in the sample. An increased fraction of the martenset of the microstructure lead to a decrease in the corrosion rate of the pistil as measurement by Ichor values. Martenset was able to resist the sodium chloride corrosion because of the amount of carbon in the martensitic is higher than in the retained austenitic. The conclusion on my research is the intercritical heating on IC X790 modified is produce dual pistil that is consist of ferrite and martensite microstructure. The critical heating at above 750 for 1 hour has no significant effect on hardness value with different chromium content. Chromium addition up to 3% weight was essential on martensite volume fraction, tensile and properties, and corrosion properties. On the contrary, the chromium addition up to 2% result in decreasing the corrosion rate of the sample. In the last, I want to say thanks to all members of Berdaulat team for their contribution in my paper. So thank you for your listening. My authors we have shared by beneficial for all of us. So thank you.
Okay, thank you, Ms. Miftah. I welcome questions from all participants in this room. Is it possible that you also show the slides here, because it's previously it's like too quick and I can't really hear clearly the description you say in the video.
Yeah. My video not include my introduction.
I see. So, you mentioned a slide, I don't know which one. Next. Next, please.
Challenge is producing dual pistil.
So this is the video, not the slides. This one. Oh no, next, yes. So when you calculate the what is this the volume fraction, what method actually you use?
Micrograph on the pistil with raw material 1%, 2%, 3% chromium addition.
Can you please stop the video?
Can you please stop? Okay. Thank you for.
Go back to the previous one. Before this slide, please. Before that. Yeah. Yes, this one.
Okay. The simulation of volume fraction of microstructure, I use image simulation. Firstly, from the microstructure analysis, I want to take a graph on the simulation, but in the simulation is the use a contrary in micrograph, so we can to evaluation of contrast on picture. So they will want to maybe it's calculate to from software.
So is it a point count or is just like the area?
Yes.
Which one?
Contrast on.
No, it's not a point count. It's just a area contrast.
Area contrast from my sector analysis.
I see. So, well, actually, it's better if you use point count method because it's already standardized, and it's just to give you a rough estimation, and not because this is statistically, and you don't know. Can you hear me?
Can you repeat? No.
Is it too low or the connection is not good?
Yes.
Is it too low or the connection is not good, or it's like stopped on off sounds, or?
Okay. I want to stop my video.
Okay.
because unstable connection in your.
All right. I would suggest that you should use the point count method for this, because this is kind of, if you use area only contrast, it's just to give you a rough estimation. Of course, this is statistically, but you cannot really see the standard deviation, whether it's correct or not, that you use the grid, the size of the grid, or the size of your microstructure to calculate.
Yes.
Can you hear me?
Yes.
Yeah.
I didn't
Okay.
expect to standard deviation, but I used to one picture in here, so I want convert to software, so this is a calculate.
Yeah, I mean the method it's there is a standard in STM for that.
Yes.
Yes, and I think you also need to put that.
Yes.
Okay. So what the modified thing you mentioned before, is it because you add nickel and chromium, or else?
Adding chromium content in
So
raw
the nickel
material.
is like already there for the what is the material before?
Yes.
Can you please go back to the previous slide, Mr. Mukhlis? Go back again. This is the last question because your time already up. Go back. Oh, this one. I see 8790 is because it's also put on a laterite inside. So I assume that you also modified the nickel inside it.
No.
So the nickel is already there.
Nickel is, yes.
I see. Okay, actually I still have lots of questions for you, but unfortunately the time is very limited. Thank you so much, Ms. Miftah, for sharing your work.
Yes.
Now I would like to move to our next presenter. I invite Mr. Permana.
Yes,
Are you going to use video or live presentation?
Video.
Video, okay. Mr. Mukhlis, maybe you can help me to open the video. Yeah. Has it started yet? No sound? It should have sound, right? I'm sorry, I cannot hear anything from the video.
Is in the to present our research result. The following is the name of the first research Permana Adi Peristiawan, the second research Bintang Ajiantoro, and the last research namely Saifuddin. In this presentation, I researched about effect of hardening and tempering variation on mechanical properties and microstructure of a more laterite steel with quench media variation. I am to examine industrial steel for military equipment, one of which is to make armor component for a more figure-tying vehicle. It takes strong and tough steel specification in the manufacture of combat vehicle components. Steel that is resistant to bullet fire so that passengers are safe from enemy attacks. The first step was taken in the preparation of the material into a test specimen. The test specimen is then cut into two parts, in the first as a raw material and the second for heat treatment at austenization temperature of 950 degrees Celsius. The second step is the quench process with variation is in the quench media in the form of water, oil, and air. The third step after the quench process is finished, the test specimen is then tempered with a temperature variation of 100 degrees Celsius to 100 degrees Celsius, 300 degrees Celsius for the more raw material specimen, and heat treatment test specimen were tested for hardness, vigor, tensile test, impact test, and metallographic test. The fourth step before metallographic testing, all specimens are mounted with resin. The sun using sandpaper type 80 until 1250 0.3 micropolitan use aluminum liquid. The specimen were then etching into percent metal etching for 4 seconds and analyzed using an optical microscope Meiji MT 7100 type. Chemical composition testing is carried out to determine the content of a chemical element contained in hot forging laterite steel. From the result of testing the chemical composition of hot forging laterite steel, it can be seen that the maximum composition contained in laterite steel is around Fe of 90.377%. From the result of this test, the carbon content C in is 0.49 or 10%. With a carbon content of this magnitude, it can be concluded that this steel is categorized in medium carbon steel, and this steel contains carbon element around 0.3 and 0.6%. In testing chemical composition of steel, the composition obtained is shown in table 1. In figure, the raw material for hot forging steel at around temperature 27 degrees Celsius is then heated to an austenization temperature of 950 degrees Celsius and held for 45 minutes as a hardening process. Furthermore, the hardening process material at a temperature variation of 100 degrees Celsius, 100 degrees Celsius, and 300 degrees Celsius. For 45 minutes, then a quench process was carried out with variation in the water, oil, and air media. The result of mechanical properties test in the hardening process with a temperature of 950 degrees Celsius for 45 minutes, followed by the quenching process in the water, oil, and air. Media are shown in table 3. The quenching process with water, air, and oil media increases its mechanical strength. As in the quench media, water hardness becomes 762.3 hardness vigor, and yield strength reach 31.8 Newton per millimeter. In the heat treatment process by quench, the water media can increase the highest mechanical properties. In oil quench media, the optimal value is elongation and impact strength. The elongation ratio that the decrease occurred due to the brittle nature form the rapid quench rate with the highest value is 3.20x Newton per millimeter on the air quench media. The result of the impact energy hot forging get 39 joule of the test result. To A until B, the highest increase in tensile strength and yield strength is at a tempering temperature of 200 degrees Celsius with an air quench media of 1320 Newton per millimeter. The lowest yield strength at a tempering temperature of 100 degrees Celsius with an oil quench media 54.3 Newton per millimeter. In this specimen, martensit paste is formed and dominate to reduce the yield strength. In Figure 2c, the effect of elongation on tempering temperature variation will increase by 18.2% at 200 degrees Celsius with oil quench media. In Figure 2d, tempering temperature variation found that the highest modulus Young value were in specimen with air quench media temperature at 200 degrees Celsius and 8.641 Newton per millimeter. In Figure 2e, the absorption of the most absorbed impact energy is 83 joule in an air quench media and temperature at 300 degrees Celsius, so that this material is more resilient than other material. In Figure 2v, the highest hardness value on tempering variation occur at 100 degrees Celsius, with the water quench media having the highest value and 743.3 hardness weaker. In general, an increase in the tempering process can reduce the value of material hardness that the increase in tempering temperature is inversely proportional to the hardness of the material. In figure this, there is an image of the microstructure result of the 950 degrees Celsius treatment process being held for 45 minutes in quench on water, oil, and air media. The microstructure of the hot forging material without heat treatment consists of the martensit paste. Then, in the oil quench media, the binded and faded alpha paste are formed. In the air quench media, specimen of the formation of the perlite and faded paste. In the water quench media, a martensit paste informs, which makes the material properties hard and brittle. Tempering treatment to reduce residual stress and increase toughness and ductility that had been lost of or reduced during martensit hardening. 4 is the microstructure of the specimen after the tempering process at a temperature variation of 100 degrees Celsius, 200 degrees Celsius, and 300 degrees Celsius, held for 45 minutes. In the quench water media shown, a martensit paste formed at tempering temperature of 100 degrees Celsius, 200 degrees Celsius, and 300 degrees Celsius. The oil quench media show of ferrite and binded paste at tempering temperature of 100 degrees Celsius, 200 degrees Celsius, and 300 degrees Celsius. In the air quench media show of ferrite and binded paste at tempering temperature of 100 degrees Celsius, 200 degrees Celsius, and 300 degrees Celsius. Based on the result of the tempering process, the microstructure is relatively the same as the result of the hardening process. However, care must be taken from the result of the mechanical properties according to Figure 4. The conclusion is 1. The heat treatment process affects the mechanical properties and microstructure of the steel. The highest hardness value was obtained in the hardening process specimen with water quench media of 762.3 hardness figure. The highest tensile strength is obtained in the tempering process specimen with air quench media at temperature of 200 degrees Celsius with a value of 1,320 Newton per millimeter and yield strength of 1,320 Newton per millimeter. 2. The highest impact value was obtained in the specimen tempering process with water quench media at a tempering temperature of 300 degrees Celsius with a value of 83 joule. Specimens that meet the hardness value of 600 G or more steel are tempering temperature of 100 degrees Celsius and 200 degrees Celsius with water, oil, and air quench media. In the tempering process, the highest hardness value was obtained at 100 degrees Celsius with a water quench media of 743.3 hardness figure. And 3. Specimens which have not met the hardness value of 600 G or more steel are tempering temperature of 300 degrees Celsius on water, oil, and air quench media. The result of the observation of the microstructure and the process of hardening and tempering are relatively the same.
Okay, thank
And
you,
finally, I
Mr.
thank
Permana.
you for your attention.
I think I have to cut the presentation because there will be no, it's quite a long presentation and a very short time for questions. Welcome question from, okay, there is a question from Mr. Fathan. Which one of the variation can be used for the armor steel?
Variation is, I think, is number 1 is variasi mediquence. Mediquence or variasi mediquence is very important. And water, oil, or air, because as water is the optimal value is to go to hardness, yield strength, and yield strength and strength, and media air media is optimum is elongation. You go and I research to armor is goal research hardness is very high. I think is variasi water media is the best, very optimum. Number 2, you research variasi hot forging, or you think it's still thinner is your methods rolling process, because add value is low, thinner is very best for your component, your armor steel.
Can I make some another, the comments?
Just very short one, please, because it's already up to
just
time.
a comment, I think. Just
Yeah,
a comment.
very short one.
Conclusion in the conclusion, I can't get anything about the which one is the best one. If you Mr. Permana, if you can compare with the another, the standard of armor. Before I did this research before using manganese steel for armor steel. So maybe there is some standard for armor steel, and then it's like according the hardness, maybe an impact, as I know like that. if you can compare in the conclusion, I mean the conclusion is like the armor steel. I think you mentioned before in the your PowerPoint. I think that's the answer in there. Which one is the better one according the mechanical properties of them? So I mean of the armor steel standard. So from there you can compare between your result, because of your result is I think it's best one if you can compare and then you get the new one, the new mechanical properties for, and then using the new methods maybe like that, or maybe the reverse engineering method like that. Just that I think Dr. Taya like that. Thank
Yeah.
you.
Okay, thank you, Mr. Fatan, for your suggestion. I think because the time is very limited for Mr. Permana, I also would like to say thank you for Mr. Permana for your time, for sharing your work.
Thank you.
And now I would like to continue to Miss Luciana for presenting her work.
Yes, madam.
Miss Luciana?
Yes, madam.
Yes. Are you going to use video or PPT?
Video.
Video, okay. I think Mr. Mukhlis, can you please help us to, yeah. Yes, you may continue, Miss Lucy.
My name is Luciana from the Metallurgical and Material Research Center of the Indonesian Institute of Science. Let me take this opportunity to present a research entitled Wear Resistance of Hot Roller Ferronickel Chrome Steel with Various Astamping Temperature. Outlines, background, experimental method, result and discussion, and conclusion. Background. Magnetic steel development for transportation, namely developed magnetic steel with nickel and chrome addition. The need to have good wear resistance because its application have friction between rod and wheel. Connection between hot rolling, stamper, and wear resistance. Hot rolling process is expected to improve the hardness of the alloy by reducing the grain size and improve the wear resistance as well. Experimental method. In the TTT diagram, it can be see how to get the binit fasa binit and CCT diagram is the basic for selecting to temperature used to get the desired harness. Experimental method, thermomechanical scheme. The specimen were heated to 1050 degrees Celsius and to hold for 5,400 seconds. Then had the hot reformation reduction 50%, 60%, and 80%. Continued tempering temperature 300 degrees Celsius, 350 degrees Celsius, and 400 degrees Celsius on hold for 1,800 seconds. Then hard cooling. Observation and testing as ruled as treated sample to microstructure observation, scanning electron microscope, mechanical properties test, at harness test, a specific wear test. Result and discussion. Scan electron microscope image 50% reduction. Martensit or ranated austentate. Martensit or ranated austentate fase is the sample is in the sample is more pronounced in the 40-100 degrees Celsius sample. Bainite plate length is longer in the 100 degrees Celsius. At 60% regression, the less elongated compared to the 50% reduction sample. Martensit or ranated austentate fasa from nearly equate Island in all the sample, with more martensit or ranated austentate in the 30-100 degrees Celsius sample among the other sample. Bainite plates are then present in the bainite in the 30 degrees Celsius sample. As the temperature increase, the bainite plates become more pronounced. Bainite at 80% reduction, the shape the less elongated compared to the 50 reduction sample. Martensit or ranated austentate fase form an early equated island in the all sample, with more martensit or ranated austentate in the 50-100 degrees Celsius sample among the other sample. Bainite fase are less present the 30-100 degrees Celsius sample as the temperature increase. The bainite plates become more pronounced. Harness trends follow all the logic resonics sense lower temperature close to martensit star. Therefore, lower bainite or martensit might form more compared to higher austempering temperature. The grain size will get bigger with higher temperature. It can be seen in the scanning electron microscope. Higher deformation cause higher dislocation formation with similar temperature and time. Therefore, the material still has stored energy from the morphation process. This become completely different for its specific results. It does not follow the hardness trend. The lower the value, the better is to withstand at material loss under specific test. 100 degrees Celsius temperature so a correlation with it has no strength. However, the case for 350 degrees Celsius and 400 degrees Celsius are not similar to the 300 degrees Celsius. From TTT diagram, it's so that where behavior of binite is different from perlite. Conclusion, variation in area reduction and variation in temperature of tempering in the TMCP process affect the microstructure and mechanical properties of ferronickel chrome steel. The higher the reduction of the area, the binding structure that is formed will be affected, so that the value of hardness will rise, as will increase will resistance. Based on the results of testing the wear resistance of the specimen of height reduction with tempering. Temperature 100 degrees Celsius with has the heightened toughness properties. With hardness for with the heightened hardness value of 50.1 HRC.
Okay, thank you, Ms. Lucy. I think I can only welcome one question, and we already have one. This is from Mr. Permana. He asked why the temperature duration of Ismm, I guess, is chosen between 300 and 400 degrees.
Thank you, Ms. Taya. Temperature 300 and 408 Mustang star, lower Mustang star, di bawah Mustang star.
Yeah, so the choice of 300 and 400, it's based on the temperature start of a phase. Is that correct?
Yes.
Your voice is not that clear. Okay?
Yeah. Okay.
All right. So, yeah, I think that's the answer from Ms. Lucy. I hope it's answered your question, Mr. Permana.
Yes.
Okay, then, because the time is already up for Ms. Lucy, I would like to say thank you so much for sharing your work to Ms. Lucy.
Understand. Thank you.
And now, and now I will move to our last presenter in this session, Mr. Aga. You're going to present with live PPT or video?
With the video.
Video, okay.
Assalamualaikum warahmatullahi wabarakatuh. Good day to everyone. Thank you for the opportunity here to present our research. First of all, let me introduce myself. My name is Agaridova and I come from Research Center for Metallurgy and Materials, Indonesian Institute of Sciences. And today I would like to present our paper titled The Effect of Heat Treatment on the Formation of Martensite from Retained Austenite of 4340 alloy steel. The outline of my presentation will be first the introduction, followed by the experimental setup, and then there's results and discussion. Finally, the conclusions. Martensite is formed through the rapid cooling of steel while it is still in the austenite phase, where it goes through imperfect transformation so that there is time for carbon to diffuse in the material grains. IC4340 steel is classified as high-strength low-alloy steel, which have various industrial applications as it has better mechanical properties and resistance to corrosion compared to carbon steel in general. IC4340 at most has the carbon content between 0.38 to 0.43% and is categorized into low-medium carbon steel. From the picture, we can observe the phase in which IC4340 steel transforms compared to the temperature and time needed. This steel is categorized as steel that mainly form martensite because of its low carbon content. Martensite in carbon steel is formed inside austenite grain which was transformed during austenization and thus called prior austenite grain boundaries. This phase transformation from austenite to martensite will be imperfect and will left a lot of retained austenite inside the already formed martensite. In a quench steel, the dislocation density increases with finer PAGB. Meanwhile, in tempered steel, the dislocation density decreases with finer PAGB. This rule applied to macro hardness as well, where the difference in austenization temperature will transform the austenite grain and results in a different characteristics. Embrittlement can occur in material when tempering process is done at unsuitable process and temperature range, such as slow cooling after tempering at 350 degree to 550 degrees C. This phenomenon is usually known as tempered martensite embrittlement, or TME. TME can cause failure in materials through the means of element segregation along the grain boundaries. The aim of this paper is an increase in austenizing temperature will increase the hardness value of the material as it can be observed in PAGB when it is tempered. In this research, the influence of austenizing temperature is observed toward the PAGB size. If the austenizing temperature is higher, then fracture toughness will increase due to the austenite grain getting bigger, followed by an increase in hardenability. Next is the experimental setup. Material used in this research is IC4340 steel, which categorized as low-medium carbon steel. The treatment process was carried out inside a muffle furnace, and from the schematic, firstly, normalization was carried out at 900 degrees Celsius for 2 hours, followed by furnace cooling. Normalized sample was then austenized at 840, 940, and 1040 degrees Celsius for 2 hours, followed by rapid cooling in water and oil. Especially for sample to be etched with picral, it was tempered again at 220 degrees Celsius. Quench sample was cleaned and mounted into castable resin for metallography preparation. Prepared metallographic sample was then etched using nitrile 2% etchant and picral 30% etchant. To clearly show the microstructure of the material, for nitrile and picral etchant, the etching process is done by dipping the sample into etchant for 3 seconds and 5 minutes respectively, followed by putting the samples through running water and cleansing alcohol to stop corrosion process of the etchant. Nitrile etchant is used specifically to show phases like ferrite, perlite, and martensite, meanwhile picral etchant is used mainly to show the prior austenite grain boundaries. Now is the results and discussion of this paper. First is the effect of normalization on microstructure. Excessive sample has been observed and showed that martensite phase is already present in the microstructure as can be seen in figure A. Normalization at 900 degrees Celsius was then carried out, followed with furnace cooling to return the phase back to fully austenite as can be seen in figure B. The average figure hardness number for the normalized sample shown a lower value of 345 compared to 362 of the as-received sample. The normalization treatments aim to increase machinability of material in general, meaning that the material hardness will be lowered as indicated in the graph. The microstructure of the sample in figure A and figure B indicate the ferrite phase is shown in white color, while perlite phase is shown in black color. Next is the effect of heat treatment on the formation of lath martensite. Samples that have been normalized are then given another heat treatment at 840, 940, and 1040 degrees Celsius, followed by rapid cooling using oil and water as quench media. Martensite phase formed inside austenite grain is mostly lath-shaped, with some of it being plate. Lath martensite is known to have much higher toughness and ductility but lower strength, while plate martensite has higher strength but accompanied with lower toughness. The formation of martensite phase is also consistent with the hardenability of material, which is the ability to form the martensite itself. It can be observed that the higher austenizing temperature, the more martensite is formed densely due to the increase in austenite grain size. In addition, the more lathe-shaped martensite is observed in higher austenizing temperature compared to lower temperature, where it still has some plate-shaped martensite. Next is the effect of quench media on the formation of martensite. Quenching media also plays the main role in influencing the formation of martensite. In this figure, the sample hardness after heat treatment followed by rapid cooling in each quenching media, namely oil and water, is shown. It can be observed that the higher austenizing temperature is given to material, the higher the hardness value of the material will be. Rapid cooling with oil as quench media gives lower hardness value compared to cooling with water, and this is due to the rate of cooling from the quench media. Oil as quench media for rapid cooling is believed to give off a slower cooling rate compared to water as quench media. And the higher the rate of cooling, the more the martensite is formed, which increases the hardness of material. And this phenomenon can be observed from the resulting hardness provided in this graph. Next is the effect of heat treatment on prior austenite grain boundaries. Samples that were given heat treatment at various austenizing temperatures are then tempered at 220 degrees Celsius before being able to be observed using picral etchant. Otherwise, it will remain undetected. The results show that the higher the austenizing temperature, the bigger the resulting PAGB, which is the main phase where the martensite is transformed. Hence, the larger the austenite size, the more martensite is formed inside the grain. The austenization time, which reaches 2 hours, provides the opportunity for steel to have uniform austenite grains with carbon content that is almost evenly diffused throughout the whole grain that will readily transform into martensite. And from the figure, it shows that the higher the austenization temperature, the larger the size of the generated PAGB. Finally, we reach the conclusions. There are some conclusions that can be drawn from this research. First, PAGB affects the amount of martensite formed, where the greater the PAGB, the more martensite phases are formed and the hardness increases. The austenization temperature also influences the formation of PAGB. The higher the austenization temperature, the greater the PAGB. Second, Nital 2% etchant functions to bring up the martensite, ferrite, and perlite phases, while picral 30% etchant functions to observe the PAGB. And then, due to the nature of the steel, the more lathe martensite is formed compared to plate martensite as the austenizing temperature gets higher. And third, quench media exerts an influence on the formation of martensite, where oil produces more controlled and or uniform cooling than water. This is due to the fact that water can produce steam blankets, which can directly inhibit cooling. And finally, the optimum temperature of the IC4340 steel heat treatment process so that it has optimum high hardness and the feasible PAGB is 940 degrees Celsius with oil quench media. This is the reference for our paper. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Assalamualaikum.
Thank you, Mr. Aga. I welcome questions from all participants. And yes, we have one question at this moment from Mr. Fatan. The question is, what's the difference between austenization and normalizing, even if the temperature is the same?
Okay. Thank you for the question. In this case, okay. Thank you. In this case, the purpose is the difference between the normalizing and the austenizing temperature and the choice of the words of the normalizing and the austenizing. So even if the temperature is nearly the same, but the purpose of the process is different.
Is that enough answering your question, Mr. Fatan, or you want to have another
differences
comment? Or
I mean the differences. Can you say 1 or 2 points?
Difference in what exactly? Because from the previous presentation that I mentioned, the normalization is to make the microstructure of the material to be fully austenite first, because after the normalizing temperature, we use furnace cooling to bring it down to room temperature. But in the austenizing temperature, we use a quenching method to create a martensite structure.
Oh, okay. Maybe the comment just maybe not normalizing. I think it's like still austenization temperature in there. There is not the words a statement about the normalization temperature. The normalizing is like the process, like quenching, or maybe like the presenter before is like house tempering, or maybe tempering house. It is like the process, not like the name of the temperature. Austenization temperature is like the temperature up to A1, I think, in the iron carpet Fe3C, if you know about the phase diagram like that. Okay, thank you, Dr. Taya, maybe, and also Mr. Aga.
Okay, thank you, Mr.
Yeah, thank you for your suggestion.
Yeah, I have one question.
Okay.
So what is actually your aim by doing, I mean, varying the austenization temperature, and can I see the video again?
Maybe I can share
Or the
my
presentation?
screen now. Yes.
Just one question. Maybe to the method one.
Can you see the presentation now?
Yes. The method one.
The method. Okay.
Yeah.
This one.
So yes. So what is actually the main aim of this work? Because we know that quenching is always going to have martensite.
So basically, this is for
what
the
kind of
metallography.
martensite do you going to obtain?
Actually, in this research, we want to show the results in the microstructure, because it's for metallography results, which is we show that the from the picral and nittal etchant, you can show the microstructure of the perlite, ferrite, and martensite, also the PAGB from this microstructure.
I'm sorry. So this is the
for this
microstructure
variation,
after you do tempering, not after quenching.
Yes.
So you
after
already
quenching, and then for the
after that you do tempering, then the microstructure is there.
Yeah, from what I read from one of the references, for the picral to show its microstructure after the process from the quenching, you have to temper it for from to 220 from what I read from the reference. So this is the results after the tempering for the picral etchant.
Only this one is tempered, not the other one, not the rest of it. Only this one.
Only this one for this for the microstructure only.
So the previous microstructure you showed us is not tempered.
Yeah, this is from the nittal. The nittal is only up until the oil and water quench.
Okay. So what kind of martensite do you expect to see?
From this microstructure, we can see that the type of the martensite is the plate and lath. So at the higher temperature, we can see that there's a lot of there's more of the lath martensite compared to the plate at a lower temperature.
So what is your aim? To get the plate one or to get the other one?
Actually, we want to observe the lath and the plate martensite in the microstructure, but to be more precise, the aim is to get more lath in the higher temperature.
Okay.
Maybe that's
Yeah. Okay. Thank you, Mr. Aga. Since the time is already up for your presentation. And now we have already reached the end of the session 2. I would like to say thank you for all presenters who has present in this session and all participants who has contributed during the question and answer session. We truly appreciate your hard work and your time. And we look forward to see you all tomorrow in the second day of ISMM 2020. Okay, goodbye. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Screen dari orang.
Oh, I'm sorry.
Maybe we need to take a
we need to take a picture together. I just got a notice from the committee. Can you please open the video? Who's going to take the picture? I don't know. The committee will take the picture, right? Mr. Muklis or who?
Yeah, I will take a picture. Okay. 1, 2, 3. Okay. Next.
Okay, done.
Okay, done. Okay. Okay, once again, thank you and goodbye. Enjoy tomorrow second day.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.